Right. Hi. This is Johannes Kepler. On behalf of organizing committee, I would like to welcome everyone to the ACM WiseML workshop on wireless security and machine learning. Yeah. I think there's an echo. So the organizing committee, consists of Deniz Gündüz, Işi, Brian Ceylan, George Stanchev, Mark Kurtz, Bernard Mauser, and myself. And today we have an exciting program waiting for us. We have 2 keynotes and 14 paper presentations. And it is my pleasure. And it's my pleasure to introduce Dr. Charles Clancy as the first keynote speaker. And Dr. Clancy is the Vice President of Intelligence Programs at the MITRE Corporation.
All right, Yalan, thank you for that introduction. I guess I will go ahead and share my screen. Right, hopefully everyone can see that. In terms of Q&A, I can't see my screen and the, oh, here we go. There we go, there's the chat session. So I guess feel free to ask questions in the Zoom chat or the Mattermost chat to make this extra complicated. I will try and monitor both. But Yalan, if you see any questions that are coming through, feel free to draw my attention to them so that I can answer them. But thanks all for either staying up late or waking up early, depending on which part of the world you are in, to attend the virtual session this morning. And my talk this morning is focused really at the intersection of artificial intelligence, 5G, and security. I think any good keynote needs to blend together all buzzwords into a single topic in order to have maximal impact. So, but there's some really interesting intersections that are happening in this space. And so today I want to talk a bit about what happens when you put AI in charge of certain aspects of your telecommunications infrastructure and the challenges that can create from a security perspective. So when we talk about AI and 5G and machine learning, I guess, as well as sort of a subset of AI, there's lots and lots of different things that could mean. 5G really is a really exciting, I would say, substrate for all kinds of interesting innovation. Because 5G is inherently software defined, it is cloud native, it's all virtual. It allows you to create networks that are designed for very specific uses. And there's a range of ways that AI is being applied to those different sorts of networks. What I'm going to spend most of my time talking about today is the radio access network, which is where we have sort of the most mature set of ideas upon which to talk about actual threats. It's perhaps less useful to talk about threats in the complete abstract sense for systems that don't exist. We can always find vulnerabilities in systems that aren't even real if you can design them in a way to have sort of unique vulnerabilities. So what I want to do is focus specifically on, spend most of my time talking about the radio intelligent controller, which is part of the Open RAN set of specifications that are emerging. But I do want to acknowledge that there are other parts of AI and machine learning as it intersects with 5G that are also relevant. Certainly, I know I expect that there will be discussion throughout this workshop around RF machine learning and the role that it has really in sort of the real-time modes of applying AI and machine learning. And then there's all the core network activities around scalable orchestration and edge orchestration. So, but let me kind of quickly go through the two columns here. So first is the radio access network. And I divide this into basically 3 different time scales. We have the non-real-time application of AI into the radio access network. And by non-real-time, I mean more than 100 milliseconds of kind of implementation, of sort of latency associated with sort of sensing and acting in the network. I expect that early deployments of this are actually going to be longer than that. That's really the lower bound, I would say, just given how the networks are architected. But there's this idea of non-real-time edge scale resource management. When we talk about edge scale in 5G, we're talking about, say, the size of a metropolitan city like Los Angeles or New York or Berlin, let's say. But the idea would be that you have edge computing resources that are sort of local to that metro scale environment, and there is AI happening there that is doing resource orchestration within the edge network, or within the RAN. I'll talk more about how that works in the next few slides. Then what we have is the near real time control of the network. So this is really kind of more tower level resource management. This is the sort of individual resource schedulers that you would find today in a typical cellular base station that's deciding which resource blocks, for example, are being assigned to which users at which time. We'll talk a little bit about how that is done in this Open RAN environment that's being developed. But the idea is that it's increasingly virtual and cloud-based rather than sort of code that lives up at the cell tower. And then what I'm not going to spend as much time talking about, but wanted to acknowledge, was really this sort of actual real-time AI application of AI. And a lot of research in this space is actually looking at using AI for replacing certain aspects of the digital signal processing or channel modeling. The idea is that you can kind of learn channel impairments in real time in order to improve efficiency and capacity. But I'm not going to talk about that as much because it's not as mature from a specification perspective, although there's a lot of enthusiasm around that area as it relates to perhaps 5.5G or 6G. The other ways you can apply AI and machine learning into 5G is really in the core. So I mentioned how everything is increasingly software defined, everything is virtual. You can sort of create and compose any sort of network you need for the applications you want to implement, as is known as network slicing. You've got a lot of knobs and levers, knobs and meters, to use Joe Mottola's vocabulary from say 20 years ago, that you can use to control your network. And the challenge is that with so many different ways to deploy and control and manage your network, essentially the orchestration of that becomes infeasible for human operators. It's not as though you have a handful of different configurable parameters for fixed function equipment. Now you have sort of this elastic cloud environment with fungible microservices that can be stood up or torn down or migrated. You have networks that you can rewire on the fly depending on capacity demands. You can add in everything from caching to content management, all dynamically, right? With the software-defined sort of premise of 5G. And that creates an environment where there's a lot of expectation that really, as we get into 5.5G and 6G, we are going to begin automating a lot more of that with AI. And the last area just to highlight is the application layer. So I talked a bit about the signaling and control plane functions so far, but then certainly you have all the user traffic that could traverse these networks. And so when you talk about different 5G use cases, certainly smartphones are one, but that's not expected to be the predominant sort of new set of use cases in 5G. When we talk about industrial Internet of Things, you talk about autonomous vehicles or drones. These all take advantage of the sort of all the new features of 5G. And that's where you get into things like MMTC, which is massive machine type communication, often associated with things like smart cities, or ultra reliable low latency communication, which is a very low latency real-time communication modes for 5G. And the expectation is the reason you're doing all this and have all these capabilities is because you want to apply AI to the edge, so that it can do things like drone flight path management and spectrum coordination jointly in real time. These are the sorts of applications that will be possible as you begin to apply AI at the edge. Let me talk a bit about ORAN. So ORAN is the Open Radio Access Network, and it is an emerging set of standards that are really looking at how do we do a few things in the RAN. Again, rather than having fixed function base stations running sort of static signal processing functions, the idea is to do a few different things. One is to kind of do what I would say disaggregation. The idea is to break apart the logical pieces of your radio access network so that they can be separated. You can put some in a cloud, a radio edge cloud. You can put some of it in hardware, let's say at the base station. Lots of different ways to kind of split apart the base station in order to gain efficiency and scale. There's some other advantages there around the ability to bring in new vendors as well. That has a lot of the carrier ecosystem excited. Another big application is vRAN, or virtual radio access network. Basically, the idea there is that pretty much everything from the absent the sort of low-end physical layer functions, all the baseband processing above that, all of the logic link control, radio resource management functions, all of those things can happen in virtualized code running on commodity servers rather than in fixed function equipment sitting at the base station. So vRAN is another big sort of aspect that ORAN can enable. And the third is really this whole idea of automation and application of AI and machine learning to the radio access network. So if you look at the overall architecture, at the bottom here, you have kind of your typical signal processing components. All the way on the right, you have really your mixed signal, A to Ds, Ds to As, amplifiers, the antennas that are actually going to broadcast and receive your signals. And those are connected to kind of the low end of the physical layer. And basically, there's an ongoing debate about exactly where you split the physical layer. You'll note that there's this open front haul that connects the low end of the physical layer with the high end of the physical layer. And if you kind of follow the ORAN debates, there's these different models, the 7.2 model, the 7.3 model. And industries, I think, slowly converging on a particular split of how you're going to break apart the physical layer to put that open front haul interface in. But basically, the idea is that you do a lot of the MIMO and array processing at the tower, and then once you've gotten through that, the rest of the baseband processing happens further back at the distributed unit, the RAN DU. All of that, like I said, you see here at the bottom, it's sitting on top of an NFVI platform, so it's all network function virtualization infrastructure, right? So it's all virtual network functions. These can be implemented as microservices running in an edge cloud. You then have what's known as the control unit. So this is operating the higher layer parts of the protocol stack, and there's a defined interface, the F1 interface between sort of the baseband and MAC and radio resource management functions and the controller things that are sitting, the control functions are sitting on top of that. And then what you have sitting at the top here is what's known as the RAN Intelligent Controller, or the RIC. There are two versions of the RIC. You'll see the one here in the middle of the slide is the near real-time RIC. This is the one that is doing sort of let's say millisecond to 100 millisecond level orchestration of the RAN resources. This is sort of got a lot of the closed loop, more real-time responsive sort of functions that are implemented within it. It connects via the A1 interface to the orchestration and the management network orchestration layer, or also known as orchestration and automation. This is often viewed as kind of more of a core network function. It doesn't have to be sitting at the radio edge. So you'll see sort of this A1 interface. But then within that orchestration and management function, you have the RAN intelligent controller non-real time. And that is essentially the longer loop, if you will, AI that can be used to control and manage your RF resources at the edge. Some interesting facets here that I think are important from a security perspective. One, we've got sort of this box here that says trained model. There specifically includes the idea of using machine learning to develop and update your resource allocation processes on the fly. You also have this thing called a third-party application, which you can connect here, which certainly if you think about apps, if you will, in your radio edge network and the provenance of those apps, that's something that we really need to take into consideration from a security perspective. The idea being, though, that you might have, in 5G, you have these ideas of network slices. So I might have a network slice that's designed for normal smartphone traffic, known as enhanced mobile broadband, or I could be a gaming company that has decided to build my own virtual reality headset that has a direct 5G interface. And I'm going to do a lot of my VR processing in an edge cloud that is sort of sitting adjacent to the cell tower in order to get my latencies really low. Or maybe I'm doing augmented reality. I want to do sort of frame markup, and I need to be able to take a camera image off of an edge device, push it to an edge cloud to do all of the augmented markup, if you will, of that image, and send that image back to the headset, all within the frame rate of a 60 hertz image, sort of video feed that you might have. Right, which means you need to meet, I think, 16 millisecond latencies if you want to be able to do frame markup and not have any lag in your video display. Right? So again, those are the sorts of applications that you might want to be able to do. And so then if I'm a gaming company and I'm designing the service, these things like these third-party applications are ways that I can actually develop an app that would go into the RAN intelligent controller that would be used for doing the edge resource orchestration of the RF resources to make sure that my users are getting the throughput that they need in a time-responsive way in order to meet, say, a 16 millisecond round-trip latency for doing AR sort of image augmentation. So with that, let me talk a little bit more about these different interfaces. So within ORAN, you have sort of three key interfaces that I think are germane to the discussion today. The A1 and the E2 interfaces, which were on the previous slide, which really are responsible for pushing policies up and down this sort of stack that we have. But we also have the O1 interface, which is the set of observables. So this is metrics that are coming off of the network and being provided in real time back to the different components of the network. These could be things like key performance or key quality indicators, for example, RSSI measurements, throughput measurements. All of this data would be used by the automation algorithms to decide how to sort of do closed loop control of the resource management in the network. So at the high level, you have the RAN intent and enrichment information. So the RAN intent is essentially it's described in sort of these high-level declarative policies, like a service-level agreement. It could say something like, I want to ensure that the users of this network slice achieve at least 10 megabits per second with 10 millisecond or less latencies 99.99% of the time, or something like that. Right, so you could express a service level agreement as a high level declarative policy, and that would go into the RAN intent. The enrichment information is sort of a knowledge base that you can use to store additional information about the network that your RIC can use to reason over the sorts of policies it would want to implement. your non-real-time RIC has access to high-level policies, enrichment information, and observables coming off of the RAN. Its responsibility is then to come up with declarative policies that then get pushed down to the near real-time RIC. So declarative policies do things like express resource. Essentially, it glues together, it defines objective functions for resources. So you have ability to express your resources, which could be things like the properties of the traffic and how you want to shape or engineer that traffic, efficiencies that you want to achieve in your network performance. And then you could have sort of the objective functions that go with that: quality of service, quality of experience, key performance indicators, key quality indicators for those resources. So it's not saying how you actually achieve these objective functions, but what it's doing is basically stating what the objective functions are and how they intersect with the resources under management. And it pushes that down to the near real-time RIC. And keep in mind that it's perhaps updating these declarative policies based on observables that it's seeing and subject to the high-level RAN intent that it was given at the beginning. Then what you have is imperative policies. So the near real-time RIC is responsible for pushing down to the actual signal processing baseband, sort of front edge of the network, if you will, these imperative policies. And these imperative policies govern the specific state of resources. And they can be event-based, condition-based. You can define actions. These are the sorts of things that are envisioned, but you can kind of develop these sort of interrupt-based imperative policies that would actually, if certain situations if certain conditions hold in the network, then you would sort of change the state or do specific things to the way that resources are allocated. So again, keep in mind there's sort of 3 levels of abstraction here: imperative policies, declarative policies, intent policies. And each one is sort of operating at a order of magnitude or so time scale slower than the one below it. But they all get access to the same observables. Another important thing is the feedback, right? There's double-edged arrows on each of these interfaces. But for the most part, the only thing that's sort of being pushed back up the stack, certainly the observables are being pushed in all directions, if you will. But whether or not a particular declarative policy meets a high-level intent, for example, or a particular imperative policy meets a particular declarative policy, is not something that's sort of pushed back up the stack. It's up to the layer above to use its own vantage point, its own visibility into the observables to do the, if you will, battle damage assessment or the independent validation that the policies that are being generated and promulgated lower in the stack meet the expectations of the policies that are being pushed from higher in the stack. The only thing that really can get pushed back up the stack is essentially if one of the nodes here basically says, well, I have a set of policies that are unachievable given the conditions that I have right now, and so I'm going to elect unilaterally to not enforce these 3 policies on the system. Then essentially it could push back feedback saying, hey, I just can't accomplish these 3 policies with all the constraints that I have in the actual operating environment. So moving on from there, a little bit about the interfaces. It's a pretty typical web services stack. You have JSON that's riding on top of basically a TCP/IP network stack, and this is sort of what you'll find pretty much across the board in 5G is a move towards these fairly simple web services-based APIs for transactions. And there's, like you say, a few different 5 sort of broad procedures that are defined over these interfaces, things like create, query, update, delete, and feedback on the policies that are being kind of pushed down the stack. So let's talk a little bit about use cases. So within ORAN, there's kind of 2 phases of use cases. The first phase of use cases are really more capability oriented, and the second phase are more application oriented. The idea being that the applications are probably going to take advantage of different types of capability use cases. But if you kind of look at the current documents right now from the ORAN Alliance, you'll see things like in phase 1, there's things like traffic steering, quality of experience and quality of service optimization. and massive MIMO optimization. Keep in mind that as you move into sort of the multi-user MIMO and massive MIMO world of 5G, particularly at millimeter wave, but certainly at mid-band and low-band spectrum as well. There's all kinds of sort of spatial deconfliction that's needed, particularly if you have a low frequency reuse factor in your network. So the ability to do all of the control of that and coordination across cell sites is something where ORAN thinks that it can have a key role in, let's say, managing the eigen resources, if you will, of a MIMO environment across cell sites in particular. I mean, you can do basic singular value decomposition at an individual cell sector to try and figure out how to do all the beam steering and in eigenspace for MIMO between tower and multiple users. But when you want to sort of look at how multiple towers near each other affect each other and users that are kind of located with visibility of multiple towers, there's a lot of optimization that you can do looking at kind of the multi-tower eigenspace across multiple array sectors. In phase 2, that's where we get into specific application areas. So one is the RAN slice SLA assurance. So if you have a service level agreement that you want to enforce on a particular network, again, the idea is that you can do that through ORAN policies. And then you can get into some of the more real-time use cases and safety-critical use cases, things like vehicle-to-vehicle handover among different cell sites, or UAV resource management. I've got an example about that a little bit later on in the deck. But the important thing here is that the explicit idea is that machine learning is going to be used to accomplish a lot of this resource orchestration. So when you think about a generic threat model for machine learning, so this is not specific to ORAN, this is just generic to machine learning, and I've got another one that sort of looks at AI more broadly. If you were to basically say, all right, here's my AI system, what does a typical cybersecurity threat model look like? Well, what you do is you say, well, let's sort of sketch out a model for my system. And so here I have a machine learning model. The machine learning model has some key attributes to it. It has its hyperparameters. This is the structure of the network, the configuration of the network, not the actual trained weights. Kind of that's often viewed as sort of a separate thing that you would be modifying and evolving over time if you're doing things like transfer learning or continuing to adapt the weights based on real-time feedback. But those are kind of the things that make up the essence of the machine learning model. There's training data at the bottom that is used to generate the weights, at least the initial set of weights, and typically labeled training data. Of course, it depends on the sort of model we're talking about here. And then you have runtime inputs and runtime outputs. So at runtime, data goes in, it gets evaluated, it kind of gets pushed through the model, outputs emerge, and then the question is, well, what can an adversary do to this? Well, essentially, when we think about an adversary, they basically have four basic capabilities. They can, when you think about it from a networking perspective, they can view, they can modify, they can insert, or they can delete data that's traversing different parts of the network. So certainly the runtime inputs that are going in, the outputs that are going out. Again, it depends on how capable, sophisticated your adversary is. Depends on if they are an insider, if they have some sort of supply chain access, if they are sitting on the other side of the world connected to the internet, their capabilities for accessing and manipulating your model may be much lower. But if they somehow are more deeply embedded or have a different level of access, then the adversary could be a much greater threat. And so when we think about this, first of all, there's no way to combat an adversary who's omnipotent, right? If our adversary has view, modify, insert, and delete sort of to every aspect of our network, our model, there's nothing we can do about it. So in any realistic situation, we have to assume that the adversary has some sort of limitations, and that we have the ability to balance that with other countermeasures that we have in the system. So then what we do is we generally talk about what sorts of things an adversary may want to do. They could want to compromise, and we break that down into sort of traditional cybersecurity lanes of confidentiality, integrity, and availability. So if you want to compromise confidentiality, some things that they might want to do would be to reverse engineer the model. For example, by providing inputs and viewing outputs, they might be able to learn something about how the model behaves, what its failure modes might be, for example, depending on what the goals of the adversary might be. There are scenarios where an adversary may seek to reverse engineer the training data through interaction with the model. particularly if you have proprietary or sensitive training data. Whether or not a particular piece of training data, like a particular, let's say, for example, this is an image recognition system, and there's, you want to know whether or not a particular image was included in the training data that was used to train the model. There's emerging research looking at how you might do that, or how you might build models that are immune to those sorts of attacks. Or again, the anticipate or estimate the inputs or the outputs. Again, maybe you only have visibility of the outputs and you want to be able to estimate the inputs. Maybe you only have access to the inputs, you want to be able to estimate the outputs. Again, it depends on the goals of the adversary and what they want to do as part of a broader system that they want to influence or exploit. Compromising integrity. This is really about causing incorrect outputs. I could have my AI model generate a random but incorrect output, or you could have it deterministically produce the wrong output. So for example, there's attacks around poisoning the training data to put backdoors into models so that if it's presented with a particular input that has a particular attribute to it that may not be perceivable to a human or some other algorithm that's looking at that input, it excites a particular corner of a trained machine learning model that causes an incorrect output in a deterministic way. And then availability. Certainly there's perhaps the objective to degrade the model performance. Maybe have if it's some sort of classifier, have the classification output be incorrect. Well, not necessarily incorrect, but degrade in its performance. Perhaps it needs a higher SNR to get the same performance, or maybe there's also performance in a computational perspective. Maybe it uses more computational resources to execute the model. All sorts of different things that you can imagine from a denial of service perspective. I haven't seen any research on like full-blown denial of service attacks against machine learning. Might be an interesting area to explore. Maybe someone could get a PhD dissertation or two out of exploring some of the corner cases, if you will, of machine learning threat models. I'm sorry. So then let's zoom up into a larger AI system. So here you'll see that the machine learning models are these little squares or rectangles. But then you have a broader set of inputs to a system. You've got models that are making sense of that input, providing that data to some sort of system controller. Lots of different ways to instantiate that system controller. It could be a controller in a typical control theoretic context, where you have some system you're interacting with that has some transfer function, and you have your system that is looking to control it and or govern some sort of control process. So this could be just a set of differential equations. It could be a more policy-based controller. Think about like an expert system or something like that. It could be a reinforcement learning that's got some sort of, say, Markov decision process view of the world, and it's trying to learn a set of policies to optimally interact with that environment. Or it could be a more statically developed and implemented finite state machine that is the system controller. And when we talk about AI or automation, kind of all of these things are sort of in scope depending on how much of an AI purist you are. Certainly when you talk about things like reinforcement learning, we're definitely in the territory of AI. Some of the more sort of dynamical system view of these, perhaps it's less AI, but I don't know, maybe it is, depending on where you sit in your AI philosophy landscape. But again, all the same sorts of threats are here as well. You can view, modify, insert, delete the inputs and outputs of the system, sort of any of or you could try and exploit the individual ML models using the techniques we talked about on the previous page. When you think about this in terms of the larger system, right, we may want to reverse engineer the system controller. Right, if it's a policy-based expert system, we may want to be able to interact with the system in order to find out what its rule set is so that we can cause it to behave in a certain way by skewing the inputs at some future date. We may want to cause incorrect outputs by and doing that perhaps in a deterministic way, or overall degrade system performance or even cause system failure. For example, imagine you've got some sort of closed loop control system in here that has some point of instability where it causes the control to go out of bounds. If you had the ability to cause that to happen or cause it the control behavior to oscillate instead of converge, there might be some interesting denial of service capabilities that you could accomplish. So again, these are all the sorts of things an adversary may want to do. So then let's actually zoom in and look specifically at the radio intelligent controller and talk about these interfaces in light of kind of the generic AI threat model. Well, what might an attacker want to do for the with respect to the RIC? Well, one could be to compromise confidentiality. There are lots of different users on the network. Those users are all sort of quarantined from each other in different network slices. As an example, you may have a network slice for smart grid, a network slice for intelligent transportation, a network slice for public safety, and sort of each of these users are sort of not all created equal. They have different levels of criticality of the data and the timeliness with which that data needs to be delivered. And so if there may be ways that you would want to try and infer not the actual data that's traversing those networks, but certainly metadata about it. So imagine being able to identify when a public safety network slice suddenly has a significantly increase in traffic going over it, right? That could imply some sort of public safety activity that's underway. So there's sort of these side channel kinds of things that might be possible that could compromise the confidentiality of other users in the network. Next would be to compromise integrity. So really this gets into resource allocations. Again, the whole point of the RIC is to decide how to outlay resources in the network and decide who gets which resources when in order to satisfy a plurality of different constraints on the network. And so integrity might be some sort of greedy algorithm that is looking at trying to garner a disproportionate amount of resources for its users in an environment where there's sort of a total fixed amount of capacity available. There might be some greedy behavior that emerges. There might be something around billing. That might be, again, another area to study a little bit further, depending on how SLAs are connected to billing. There could be some interesting ways to muck around with the resource allocation algorithms to get a certain amount of additional sort of traffic allocated to your users without having to pay for it. And again, the business models behind all of this are still very nascent. So, but I could theorize some attacks in that potential space. Or just to really cause outages or degradation. So for example, if I have an autonomous vehicle network slice and I am able to cause resource allocations to other users of the network to disproportionately increase, then I might be able to starve the autonomous vehicle network slice for the RF resources it needs to achieve the real-time communications with its users. And as a result, that could have safety critical consequences where messages that need to be delivered between devices, let's say an automobile brakes and is sending out a signal to alert other vehicles. Then if the resources aren't available to achieve that in a timely way, then that could have consequences. Kind of looking at the attack surface. So this is the sorts of things an adversary may want to do. The question is, well, how might they do it? Well, there's lots of different sort of things here. So first, some key assumptions. One, you have to assume that the interfaces, in particular the A1, the E2, and the O1 interfaces, are all sufficiently protected against basic protocol exploitation, right? If I can do a man-in-the-middle attack on the A1 interface, or I can connect to a near real-time RIC spoofing some other non-real-time RIC and basically just hijack control over the entire sort of automation stack, then that's kind of game over. This isn't an AI problem at that point. It's a basic protocol design and system implementation issue at that point. So first, I'm assuming that we're able to adequately protect these key interfaces, the A1, the E2, and the O1. Again, because if you can't protect those, then that becomes a key challenge. Now, you may think that that's an easy thing to do, but for one, the ORAN Alliance that's beginning to develop these specifications, they've only just now launched a security working group who is just now starting to think, oh, maybe we need security on some of these interfaces. So this is still a very early discussion for them. And I think it's critical that they say, well, we have in our network stack here, right, we've got HTTPS, right? That can't be the only solution, is to say, oh, we have HTTPS, therefore everything's going to be secure. Because in reality, there's a lot of PKI and key management issues that need to be dealt with in any sort of complex system like this. If I've got going back to my ORAN diagram here, right? If I'm getting a DU from one vendor, a CU from a second vendor, and my RIC from a third vendor, then they all need to be able to securely authenticate with one another. And there have already been in early ORAN field trials, examples where the public key infrastructure has really not been sorted out yet. And you've got a mix of vendor-issued certs that are put onto devices that are really only meant for provisioning. The idea is that the cellular carriers would replace all of the PKI credentials on these devices with their own, that are issued by their own certificate authority. But maybe the smaller carriers don't have the capacity to run their own CA at scale for their 5G infrastructure. And so they're continuing to use the vendor certs that are intended only for provisioning. It's basically like when you go to a website and it pops up a TLS error, and you click the little button in the bottom corner and say, continue to website anyway, right? That's kind of what's happening right now in some of the early trials, because the key management really is not mature at all in this environment. So that's an area that I think needs a lot of attention. Observables, again, if you have the ability to create artificial traffic in the network, or artificial users in the network, or artificial metadata about those users in the network, then you might be able to skew. You're not necessarily compromising the observables themselves, but you're creating an environment where observables are generated that have properties that you want to achieve some sort of application. And we talked a little bit about these third-party apps. There's a whole range of opportunities there for potential exploitation. Depends on how is their code signing, like a lot of open questions there. And then, of course, we've got all these system inputs and databases, right? This RAN intent enrichment information, right? What's the provenance of that? How is that secured? So let's talk about a hypothetical example real quick. So, and this is based on sort of actual discussions with the major vendors and carriers about how they envision rolling out these networks. And so we talk about it as a metro scale edge cloud environment. And so here I have a picture of Manhattan Island. And that's the sort of scale of edge network that is envisioned. So there'd be a data center for, let's say, Verizon or AT&T here in the United States. They would have a data center. It would be servicing anywhere from 5,000 to 15,000 cell sites in this area, right? So in my example here, I've got 100 radio edge clouds that are in this large metro scale edge cloud environment, each controlling 100 cell sites each. Right? That's one way you could decompose it. Really depends on the capacity of your ORAN infrastructure. You've got multiple network slices that are operating over this core network. You've got enhanced mobile broadband, which is just providing general packet service to smartphones. But maybe you have some real-time network slices as well. One for autonomous vehicles, one for UAS. And so each network slice has its own. And each network slice has its own apps that are responsible for controlling resource allocation in the network. So let's go with the drone example specifically. So UAS has a really interesting set of challenges when it comes to 5G. In particular, if you're looking at beyond line of sight control of drones, and you expect the drones to all just have 5G radios on them that are talking to a 5G cell infrastructure on the ground, and you want to do everything from air traffic control to path management of the drones and collision avoidance sorts of functions. Again, imagine thousands of drones flying over New York City or Los Angeles or Berlin, right? That is a sort of a frightening post-apocalyptic future, but I think it's not too far-fetched. So if you have all these drones that are doing everything from package delivery to food delivery, you have some RF propagation challenges. A drone that is airborne has a line of sight visibility to many towers simultaneously. And so its uplink channel, particularly if you have, say, a frequency reuse factor of 1 in a massive multi-user MIMO environment, right? You are essentially putting energy into the eigenspace of many tower uplinks simultaneously. And so if you want to be able to kind of manage that, then you have to account for that interference in the MIMO, the multi-user MIMO sort of channel planning that you do at an individual tower level, and it needs to be coordinated across towers so that the energy from an oversimplification would be, for example, a MIMO array dropping a null in the direction of a UAS that is interfering with its uplink because it's talking to another the uplink of a different tower, but they're all using the same frequency reuse pattern of 1, right? So this is an interesting problem that's sort of unique to drones because they are airborne and they have this line of sight challenge. But it's the same reason why they want you to turn your cell phone off when you get in an airplane, because the uplink from your phone could be hitting a whole bunch of towers on the ground and causing interference to a bunch of users simultaneously. The RAN intelligent controller, the idea is that you can actually do path-aware resource allocation. So the RIC could know the flight path of these drones, and from that be able to anticipate the resource allocation as it's going into the network. Well, if I could spoof UAS locations and paths, then I might be able to cause resources in a network to be skewed in a particular way that's not accurate, right? I could inject false path data for UASs in the data plane of the network. This isn't in the control plane, but it's data plane, where I am basically saying, I don't know, hundreds of drones are all going to go through this exact same corridor, when in fact they aren't, which would cause a major swing in the resource allocations in anticipation of the drone's arrival that would not be accurate, right? And so that could cause resource starvation to other services that might want to be able to, for sort of phantom resource needs that are generated within the network. And this is just sort of an initial hypothetical example of the sorts of things that I expect we're going to see in some of these future networks. So how do you deal with things like this, right? How do you ensure that the network has the needed integrity so that you can't spoof UAS paths to cause these resources to be skewed in the wrong direction? These are all wide open questions from a research perspective that I think groups like those convened here today would be in a unique position to tackle. So just a handful of recommendations to close out here. One, we really need to address all the basics, right? I talked about this earlier. We need robust authentication and encryption. We need to address these key management issues, which is particularly challenging in a diverse vendor environment. We need to do things like code signing for third-party apps that are going to get plugged into these radio intelligent controllers. Some sort of testing, like we want to know that there's the failure modes of these are well understood. Even if there isn't some malware baked in, like how do you know that the control algorithm isn't faulty in some way to cause problems in the network, or how do you combat that as part of a larger system design? And then as you start thinking about the AI systems that these are all going to plug into, right, we need guardrails really that can trigger either human intervention or cause some of these more sophisticated, let's say, for example, you have a sophisticated reinforcement learning, deep Q learning system that's doing the UAS resource allocation. Right, we need to make sure that we could fall back to a simpler mode if we see, let's say, shenanigans happening in the network that are unexpected, until we can debug them and diagnose them and correct them. Broader ecosystem, I talked about this at the beginning, RF machine learning, still, I expect actually later today that there will be talks about some of the challenges there around potential spoofing attacks and things like that you could exploit. And then as you start looking at the network, again, this is all still wide open. If you look at OpenFlow, for example, which is one of the major software-defined networking specifications, right, it doesn't even really have a security framework, right? So our entire sort of 5G backbone is based on a software-defined networking architecture that doesn't have a real set of formalisms around security. And that's a problem, right? So I think as we think about edge computing, both and its role both in orchestration and in our applications, we got to get all the basics done first, make sure that we have encryption and authentication of our interfaces. And then from there, we can start thinking about how will we build security in sort of systematically into the AI that sits on top of those. With that, I have, I think, about 5 minutes left to do some Q&A, if there are any questions from the audience. And either feel free to chime in verbally or...
Hi, Charles. This is Jan again. Thanks a lot for your insightful talk, and my apologies. I had a problem with my audio earlier, so I had to cut a little bit short. So, you guys can, send your Q&As in the channel, in the Q&A channel in the Zoom meeting, or you can jump in here to ask your questions. But before that, I would like to, finish the introduction of, Charles Clancy. And, he is the Vice President of Intelligence Programs at MITRE, and he is the leading researcher in the area of wireless security and machine learning with the early research papers in this area. And Before joining MITRE in 2019, he was the professor of electrical and computer engineering at Virginia Tech, and he was the executive director of the Hume Center, again at Virginia Tech, and he served at different editorial boards for IEEE transactions, and he was the TPC chair of the DICE-PAN, and he was the general chair of the IEEE CNS as well. And again, he's the leading researchers in the area, and we are very happy to have him here in this talk. And so please, send in your questions in the channel or jump in here with your questions as well here as well. I can start with some questions, Charles. One question is, we are talking right now about 5G, but it is some kind of a continuous, like a process. People start talking about 6G as well in terms of research. And do you anticipate that machine learning will start having some role in 6G, or it will increase in role, or what do you think, about 6G?
Yeah, I think so. I don't want to draw sort of any firm demarcations between, say, 5G, 5.5G, and 6G, because I think that's all still a fairly open question. And I think actually moving forward, it's going to be less important. I think now that we've built this sort of software-defined backplane, if you kind of look at the releases of cellular standards, sort of every other standard kind of does a big overhaul of the RAN, and every other standard does a big overhaul of the core. We've just done a big overhaul of the core. NR has some uniqueness over LTE, but it wasn't a huge leap. I mean, we're still using OFDMA and things like that. So I expect that as we look forward, we've built out this very robust core network that's all based on SDN and NFV. And so to a certain extent, 6G could just be sort of app updates to our core network. It's all going to be software upgradable. So it's not going to be the same leap, in my opinion. I think we're going to have more of a continuous evolution of core network capability moving forward. And I think that AI is already being injected through ORAN, and I expect that it will continue to be injected in other parts of the core network. But it's not going to be like a big major upgrade of I don't know, it's not like we have to wait for release 17 or release 18 of the standards. I think it's going to be more incremental.
There are a lot of discussions in other communities like computer vision regarding the ethical use of the machine learning, and right now a lot of private data is flowing in 5G and other networks. Do you see any issues, or is there any kind of a development right now, interest in addressing this ethical use of AI in communications?
I think there's two different things to consider. One is the application layer. Certainly, the user plane is moving data that all of the concerns of the computer vision community and all the other communities would apply to, but it really has nothing to do with 5G. 5G is just the way that data gets moved from the sensor to the algorithms that are processing the data from that sensor. So certainly when you talk about the edge, the application edge, the intelligent edge, yes, but those issues are kind of more application specific. They're not unique to 5G. I think where you could see things that are unique to 5G and then the control plane of 5G is think about things like net neutrality. Here in the United States, we spent a lot of time building sort of this idea that all traffic is created equal. We've now kind of moved away from that here in the United States. But think about sort of the way you do edge resource orchestration through the lens of net neutrality and how you might prioritize certain types of traffic over other types of traffic based on who's paid what to whom. So I think that's going to be an interesting aspect of how do we deal with things like bias in resource management, and really what is net neutrality and equality. Again, all traffic is not created equal, right? If I have real-time control messages from automobiles, I would be happy for those safety critical messages to be delivered with priority over my streaming of YouTube. But I think there's going to be a set of issues that we need to sort of deal with there as we think about traffic prioritization.
That's great. Any other question from the audience?
Okay. Yeah. Okay. Can you hear me?
Yes, I can hear you.
Okay. I have a question. You mentioned that you see some need for guardrails that can trigger human intervention. Yeah, I think this is strongly also connected to other ethical issues in human-centered AI and so on. What do you think? What do you have in mind in this direction?
So there's lots of ways that you could implement it. One of the things that we're working on here at MITRE actually is this idea of AI models having a defined operating envelope. So if you could define the environment, the assumptions that were made in designing an AI model, you could define the types of training data that were used to train that model, whether that training data accounted for adversarial inputs or not, right? You could essentially come up with the nutrition facts, if you will, of a trained AI model. And that information could then be used as part of its employment in a system. And so you could then look at things like off-label use. We talk about this in pharmaceuticals, for example. Oftentimes people prescribing pharmaceuticals for things other than the intended purpose, right? But this off-label use of a model, and you could sort of understand the risks that you're accepting when you do something like that. And so I think what we want to understand is we want to have a good baseline where we kind of trust the system behavior, but realize the system's not always going to be operating at peak efficiency. Certainly a human operator managing everything is an example of low efficiency, but a well understood network. And then you can take that all the way to the extreme of a fully right, the other extreme of a fully reinforcement learning network orchestration. And so I think you need the ability to fall back as the behavior of the network is not what you expect. All right, if certain key indicators are being violated, or you are in a network, the context of the network is in violation of the certification of the models that you're using within your system, as an example.
But what I wanted to point out is that this is strongly related to other unsolved problems in AI, whether in machine deep learning, problem of human autonomy.
Mm-hmm.
And trustworthy AI explainability and all this kind.
Right. No, I agree. I mean, there's a lot of unsolved problems here. Yeah. So I think the important thing is, this is the first. So I remember when I did my PhD on cognitive radio, 15, 20 years ago, it was all hypothetical, right? We're hypothetically talking about these networks. We had some excitement with dynamic spectrum access maybe 10 years ago. But now we actually are putting real deep learning algorithms into core functions of 5G networks. So this is all real now. And we need to keep in mind all of these challenges and a bunch of unsolved problems that really need to be thought through as we're doing these network designs.
Okay, thank you very much.
Just one other question I received over the email. So right now, your talk is being streamed in YouTube in live mode. So, all this machine learning algorithms are more or less data-driven. And so how easy or difficult to get a real representative data from 5G networks, because they are more or less vendor specific. So for researchers or developers to develop something useful for 5G or other communication systems.
Yeah, that's a great question. Certainly the ORAN specifications that I'm talking about here are so first of all, if you want to start playing with some of these tools, I recommend first of all looking up ORAN and the specifications there. Second, start looking at ONAP, which is the open source 5G orchestration tools that are being adopted by most of the industry now at this point. A lot of the carriers are planning to use them, and then also look at the ORAN source code project, which is an open source reference implementation that's beginning to mature for the ORAN components that I'm talking about. So again, they're far from complete because the standards themselves aren't even complete, but it'll give you the opportunity to start playing around with it and seeing how these interfaces work. Of course, these are very data driven. Whenever you start employing AI at scale, you need a lot of data. If I want to do some sort of reinforcement learning algorithm, right, that's going to train over 100,000 epochs of interaction with some complex network, right? That doesn't just, you need a lot of data, or you need a simulation environment where you can simulate and emulate those sorts of interactions. That infrastructure really doesn't exist today. And in terms of real networks in real deployments, we just now are starting to talk about laboratory prototype testing of these by the carriers. So I think it's going to be a few more years before we really have a lot of data and we can actually start to do some of these more sophisticated algorithms. I think early on, we talk about deep Q learning, but it's really just going to be a lookup table for the near term in terms of how these things are actually implemented.
Right. Thank you, Charles. Another question? If not, let's thank Dr. Clancy for his exciting talk and also insightful thoughts on the application of machine learning to wireless security. Thank you, Charles.
Thank you. Bye.
And we will start with the first session of the paper presentations. And this session is on the generative adversarial networks, GANs. And I think our session chairs can take over at this point.
Good morning, everyone. I'm Salvatore from Northeastern University. I'm a research scientist working at the Institute of Wireless Internet of Things. Today I will be the session chair for the first chair on generative adversarial network. So today we will have 3 papers. Each paper will have 20 minutes in total, which means that there's going to be time for presentation and question and answers in the same 20 minutes. Of course, there will be different ways for attendees to ask questions to authors. One way is to use MetaMost, so be sure to join the WiseML session 1 Q&A channel, and you can write your question there. Or directly in Zoom, you can raise your hand, and at the end of the presentation, you can ask directly your question to the authors. So I'll ask the authors to be in time, so do not exceed the available time. So try to finish in 15, 18 minutes so that attendees can ask you questions about your work. So let's see if the first author is online. Okay, I see him. So without further ado, let's start the session. And the first paper in this session is titled Generative Adversarial Attacks Against Intrusion Detection System Using Active Learning. And this paper will be presented by Dul Shu, which is a PhD student at the Industrial Engineering Department at Carnegie Mellon University in Pittsburgh, Pennsylvania, and whose research interest lies in a very interesting area about generative adversarial networks and deep learning. So if Dul is online, he can start presenting the paper, and thanks everyone for being here.
Thank you very much, Salvatore, for introduction. Can everyone hear me?
Yep, we can hear you.
Okay, then I'll try to share my screen and see if it works, and then I can start my presentation. So can everyone see the screen of the presentation?
Yeah, I think I can see it, yes.
Okay. Hello, everyone. Thank you for coming to my presentation. My name is Dul Shu. I'm actually a student from the Mechanical Engineering Department of Carnegie Mellon University at United States. I'm a PhD student, and today I'm gonna present a particular type of attack against intrusion detection systems, and namely the generative adversarial attacks. This is a work I did in collaboration with Dr. Nandi Leslie, Dr. Charles Kamoa, and my advisor, Dr. Conrad Tucker. So I will start my presentation with the introduction of the threat model. So in this threat model, we consider a computer network which contains 2 nodes. One is the attacker, the other is the host or the victim of the attack. The attacker tries to gain remote access to the host via a communication channel established in this computer network. In between this attacker and the host, we have a machine learning based intrusion detection system constantly monitoring all ongoing network traffic flows in this computer network. since it's a machine learning based IDS system, so it will compute, given a network traffic flow, it will compute a list of predefined network traffic features, and based on these feature values, it will try to predict whether the network traffic flow is benign or malicious, meaning that it is generated by some malicious activity of an attacker. Examples of such network traffic features can be duration of the traffic flow, total packets in the forward direction, or total size of packets in forward direction, and so on. In this model, we assume that the IDS model has already been properly trained to effectively distinguish malicious traffic from the benign traffic, which means that in the feature space, the IDS model will define a decision boundary, and a network traffic flow generated by the attacker, for example, as represented by this purple dot, will fall on the malicious side of the feature space. Then under this situation, from the attacker's perspective, how can she or him try to bypass the IDS system? So what the attacker needs to do is to move the feature point from its original position across the decision boundary to the other side of the feature space, such that the IDS will classify it as benign and let it pass so that it can proceed with packet transmission between the attacker node and the victim node to proceed with the attack. And more formally, this process of attack can be defined as a optimization problem where we try to minimize the difference between the original feature point and the adversarial feature point, and so that the adversarial feature point will be classified by the IDS as benign. Well, there are many ways to compute the location of the adversarial feature point X tilde. And our proposed way is to use a neural network to do the computation. In particular, we propose a variation autoencoder model to compute X tilde given X. And in terms of implementation of such attack, we basically need a traffic reshaping module that takes the actual network traffic flow from the attacker's malware and then reshape the network traffic so that the new network traffic flow will meet the values of the computed adversarial feature. The purpose of this research is to expose potential vulnerabilities of current machine learning based IDS model, and hopefully to help develop new IDS models that is more robust or resilient to adversarial attack. And here's a brief comparison of our method with some related methods according to some listed technical features. And so, as I said, we propose using a neural network model to compute the adversarial feature. And this is our neural network model, which is a variation autoencoder. And so if we can have the machine learning model of the IDS, and we can connect it to the VE model and train the VE model using this IDS model, and we did this we run this preliminary experiment, and we end up bringing the detection success rate of the IDS model all the way down to 0.2%, which is a pretty good success to begin with. However, there's some big ideal assumptions in this type of model, which is that this IDS model used here is a neural network model, which we have full knowledge of it and we have full access to it. But in the actual scenario of adversarial attack, this is in general not the case, because in general, the attacker has no knowledge about the internal structure of the IDS model, and the attacker also cannot have unlimited number of times to probe the IDS for labeling its adversarial features, because if during the training process the generator tends to generate a lot of adversarial features and send it to the IDS for labeling, then it will make its behavior very suspicious, and probably the IDS will block this communication channel, and the training has to be stopped. To address this problem, we replaced the black box IDS model with a substitute IDS model, which is a neural network model, and we have unlimited access to it, and we have full knowledge about it. Here, the key thing is that in order to get a good performance in adversarial attack, we need to make sure that the SIDS model has a good approximation or sufficiently accurate approximation to the original black box IDS model. And to address the second issue, which is the limited number of times to probe the IDS, we introduce a active learning algorithm to propose to minimize the number of IDS labels for training the adversarial attack network. This active learning algorithm is basically an iterative process of retraining the adversarial attack model listed here. So it starts with a small size of initial training dataset that consists of network traffic flow features and their labels assigned by the IDS model. We will use this initial training dataset to train our adversarial attack model, but since the size of the dataset is very small, so we won't get a very good result in adversarial attack performance. And the way to improve the performance is that we first use the generator, which is the VAE model, to generate a large number of unlabeled network traffic feature points, or the unlabeled data points. And we use a special way to select a small subset of these unlabeled data points, send it to the IDS black box IDS model for labeling, and in order to get a labeled data set, and then we add this labeled data set back to the previous training data set, so that now we have augmented training data set, and we use this augmented training data set to train this adversarial attack model. And then we start the next cycle of model retraining. So in terms of VAE retraining for adversarial example generation, this is the overall block diagram of the model training. Due to constrained time, I won't talk too much about it. I will be happy to answer any questions about it later on. I just want to talk a little bit more about the active learning algorithm. So the active learning algorithm, one key feature of the active learning algorithm is how to select this small number of unlabeled data points out of the many data points, unlabeled data points generated by the VAE model. In order to answer this question, let's first take a look at this feature space where this curve here represents the decision boundary of the true black box IDS model. At the beginning of the training, we have the decision boundary of the substitute IDS model, and it's not a surprise that this decision boundary is not a good approximation of the IDS model. And therefore, if we try to compute adversarial examples which cross this like a not so good approximated decision boundary, then we will end up having a lot of feature points that will be labeled as malicious or that will be detected by the IDS model. However, on the other hand, if we take a look at the region that is the close neighborhood of this decision boundary of the SIDS model, we know that this neighborhood region kind of cover a good amount of the actual decision boundary of the black box IDS model. Therefore, if we can sample this, or if we select the unlabeled data points from this region for the model retraining in the next iteration of active learning, then we will have a good chance to efficiently learn the distribution or learn the information of the true IDS decision boundary. And this is basically the intuition behind how to boost the training of substitute IDS model to approximate the black box IDS model in uncertainty-based active learning. In contrary, if we choose another set of unlabeled data points from this different region in the feature space, then obviously this won't help us much in estimating the complete shape of the true decision boundary of the IDS model. And then we will have to spend a lot more iterations to estimate the true decision boundary, and we will have to take a lot of more risks in exposing ourselves as the attacker. This is a more detailed description of the algorithm, active learning algorithm we propose in our work, and I'd like to answer any questions about it. So this algorithm is developed from another similar algorithm named the default active learning algorithm, or the DFAL algorithm. The main difference is that this algorithm, the DFAL algorithm, computes the adversarial examples using gradient-based method, while we use the VAE model to compute the adversarial method. And we believe that there's advantage in using the VAE model because the VAE model gives us some more randomization to bypass the true IDS model decision boundary. And this hypothesis can be verified by this experimental result. So as shown in this slide, using our proposed method, we achieve a adversarial attack success rate of 98.86%, as opposed to the reference algorithm, the DFAL algorithm, which achieves a success rate of 95.48%. And also, our algorithm uses only 25 data points, labeled data points from the IDS, while the benchmark algorithm uses 45 data points. Another group of experimental results is that it is about the average perturbation on the distribution of average perturbation on the on all the network traffic features. So I didn't mention this, but we used the intrusion detection data set, which consists of 78 features. And here is basically the distribution of the perturbation over that 78 features. And one interesting we found in our experiment is that the top 10 features in terms of the magnitude of perturbation are all related to either the arrival time of packets or the size of packets. And which means that through our experiment of adversarial attack, we revealed that the IDS model tends to be more sensitive to features related to packet size and inter-arrival time. So for future work, we would like to restrain the adversarial perturbations to only a subset of feature features in order to make our proposed method a little more practical. Actually, we've already done it, and we found that we can still maintain a pretty high success rate in adversarial attack. Also, we can use this adversarial attack approach to generate adversarial examples for adversarial retraining of the IDS model in order to make it resilient to adversarial attack. And lastly, we're interested in building an actual mobile network platform to implement our algorithm and evaluate its performance. That's all I would like to present, and thank you very much for your time, and I will be very happy to answer any questions you may have.
Thanks, Lou, for your presentation. Are there any questions from the audience? You can either raise your hand here and ask directly the questions in Duel, or you can join the Q&A channel for session 1 on Mattermost.
Okay. Can I have the question?
Yeah, sure, please.
Okay. So you're using GANs, okay, and autoencoders. In the end, with GANs, you are try to model, so to say, or reconstruct a probability distribution. Okay. So the question is, and underlying, you are using, in your case, you are using Krüppig-Leibler divergence, okay, for measuring the deviation between the distributions. Okay, but if you have different kinds of probability distributions, multi-mode, for example, then you can have some troubles. The question is the problem setting you have. Yeah, you pointed out in one of your slides some characteristic features. Okay, are these do this generalize? Okay, or is this very typical for your setting? So you applied your method for some cases. Yeah, does this generalize to, I don't know, yeah, to other settings? How specific is this? Yeah, how much can it? How generic is it? Yeah.
Yeah. So I think there's a good level of generalizability of this work, because this is basically an adversarial attack problem, and adversarial attack approach has been applied to in many applications, and most of them are just to enable misclassification of a given machine learning classifier. So I think in terms of limitation, one limitation that we are indeed encountering is that, you know, if I can show you this block diagram for training. So here we're basically assuming that the generated feature is defined in the same feature space as the intrusion detection system. So, but in reality, you know, since we do not really know how the intrusion detection system works, so we're not sure what feature space it is defined inside the model, and therefore, you know, we can't say that, we can't confidently say that we're able to perturb all the feature entries that are defined in that feature space of the intrusion detection system. And we have already done some work to address this problem. And as I mentioned, that we try to perturb only a subset of the predefined feature space, and then like a subset of the feature dimensions, and see if that can still allow us to achieve successful adversarial attack. So you mentioned about distribution. I think there's not much problem about distribution, because you know, like what does a GAN model do? It's basically a transformer that maps one. It's basically a function node that maps one PDF to another PDF, right? So as long as these two PDFs are defined in the same in the same n-dimensional real space, then I think theoretically there exists such a function or such a mapping to transform the probability distribution. Does that answer your question?
Yeah. Okay. But then, of course, there are some known problems. For example, the mode collapse problem of GANs. Okay, which is related to Kolbe-Kleibler divergence. Okay, you have here some special variant. You could also take the because it's not symmetric, the other way around. And so the problem to handle how to handle a different kinds of distributions which you don't know. Yes, so you also have not just it's also I think a problem to learn about. Yeah, how many modes there are and so on. Okay, but and also the identification of your lambdas.
Sure. I mean, like, yeah, mode collapse is still remaining as an open problem to GAN training. Yes. And there are people come up with all kinds of empirical methods to address this problem, and we also experience this process in our experiment. That I really can't say anything about it, but
yeah, of course. Okay, thank you.
Thanks.
Okay, so there is another question in the chat, but since you're running late, I'll try to ask the author and get Denise to ask those questions offline, and there will be a lot of chance for an opportunity for discussion. So I would like to move to the next paper. The next paper is titled Data Augmentation with Conditional GAN for Automatic Modulation Classification. And this is a paper that will be presented by Zuyu Wang, which is an assistant professor in the Department of Computer Science at California State University in Sacramento. He received a PhD at Auburn University in 2018, and his research project focused on Internet of Things, wireless sensing, deep learning, health sensing, RFID sensing, wireless networking, and computer vision. So I'll give the word. I believe that there is, I don't know if it's going to be live or there is a recording. So be ready for the next presentation.
My name is Xu Yuan from California State University, Sacramento. The first author is Nancy Patel, who is my student. The joint work is Shuan Mao from Auburn University. Today, I present our work, Data Augmentation with Conditional GAN for Automatic Modulation Classification. Outline, including background, system model, evaluation, summary. First, I introduce the background. Okay, in wireless communication, the scarce spectrum resource and the inefficient use of the allocated spectrum has driven a lot of research in the cognitive radio. And currently, automatic modulation classification is an important component of the CR to detect the interference, wireless interference, and also to improve spectrum efficiency. The AMC aims to classify the modulation types of the received signals without previous information of signal and a channel, which is intermediate step between the signal step and the demodulation. From this figure, we can see for the received signal, before the AMC, there is the signal detection, and after the AMC, there is demodulator. So the AMC includes the preprocessor and the classifier. So, and the AMC current is used for a lot of applications, such as the spectrum sensing, spectrum anomaly detection, classification security, and transmitter identification. And also, I discussed with work. Traditional AMC use likelihood-based and feature-based solutions. And for the likelihood-based solution, consider the base estimation for the modulation classification. This method assumes previous information like the channel and noise model, but it can get the higher computation capacity and is not used for the highly dynamic environments. And the second solution is feature-based. It requires handcrafted feature like the cumulative and maximal power spectrum density to classify modulations. Also, it requires reliable feature and manual selection. And currently, deep learning-based solution can be used for a lot of applications, such as image processing, the NLP, natural language processing, and speech recognition. Okay, and this is also deep learning can be used for the various part. And for the various, okay, for the deep learning-based solution for the classification. Modulation classification, we can see it doesn't require previous information such as channel models. And a lot of deep learning model can be used for this, like the convolutional neural network, long-short memory, and other fusion methods for the modulation classification. And the limitation for the deep learning-based solution, we can see it requires the massive amount of the training samples, and also performance depends on the quality of the samples. And the deep learning method can get the satisfactory modulation classification accuracy, but it is costly and challenging to obtain the label training samples, which limited the performance of deep learning for AMC. Our solution is we consider the data augmentation to address this problem. Currently, the simple augmentation solution like the rotation, flip, and Gaussian noise can be used for the modulation classification, but just a small improvement like the 2.5% gain can be achieved. And some researchers also use the generative advanced network, the GAN, to generate the high-quality image data set and to augment the training data for the various jammer or other applications like the spectrum sensing or spectrum generation or various signal spoofing. And currently, okay, the AC GAN is used for the modulation classification and with the simulate and ideal data set. Okay, for this solution, it doesn't consider the channel and hardware effect. So the accuracy improvement is limited for the ideal data set. In this paper, we consider the conditional gain for the data augmentation that consider the real feature of the various hardware, such as IQ imbalance, impact of various channel, which are also more challenging than the previous ideal case. The idea is we use the C gain to synthesize the high quality, the labeled various data from the given the small available real data set. This augmentation data set will greatly benefit CM-based AMC to get the improved classification accuracy. And the next one, I will discuss a system model. Okay, so for the various signal model, okay, we can see for AMC important task, so can be used to detect the various communication type like the radio, radar users, and voice radios. And also it can be used to detect a nearby emitter to avoid potential radio interference. And for the modulation recognition, we can see for the received value signal, RT is given by RT equals HT convolute the ST plus NT. ST is the transmit signal. NT is the additive, the white Gaussian noise. HT is the channel impulse response and CIR. So finally, the IQ component of various signal can be obtained by sampling the received complex signal RT, which can be used for the signal modulation recognition. And also we use the data set like the radio ML 2016 10A data set, which include 11 different modulations. And also we can see for this 11 modulation, there are 220,000 signal samples. Okay, each of which has 20,000 signal samples. And also each modulation is sampled at the 20 different SNR, ranging from the -20 dB to the 18 dB. And each of SNR, there are 1,000 samples. And for each of these sample consists of the 128 IQ data, the units. And for this paper, we used the benchmark model is the CNN model. And from this paper, famous paper. And for this model, I quickly introduce this model. And for this model, the input, that is, the size is 2 times 128. And also there are 2 convolution layer and 2 density layer. And for the output, it used the softmax, and there are 11 the neurons. And a simple solution can get the satisfies the performance. And our solution is we consider the CK model. So and for CK model is the machine learning architecture that we can see the generator and the discriminator are conditioned on the class label Y. And from this figure, we need to find there are 2 things. One is the generator part, and another one is discriminator part. And so for this one, the discriminator is to try to recognize that the input data from the real IQ modulation data or from the generate that data set. And so the generator from the random noise the Z and the class label to generate that labeled and variance data set. And then we can see the C game that can be modeled mini-max 2-player game. The value function given like this. I explain this function. First one is there is X and Z. X is the real IQ data set. Z is the random noise. And there are 2 distributions. One is data real data distribution, P data X, and PZZ that hidden layer random noise distribution. And for the DXY, that is given the true data set, and the condition of Y. And another one is JZY, that is generate function, given Z, generate, the random data and a given condition, the Y, label Y. For this function, we check out this loss function. We define that need to maximize the D. For the discriminator, that want to maximize this, the loss function. That means if we give the input data from the real IQ data X, the maximum value that want to write this value becomes the 1. And then, if we give the sensitive data Z, random noise for here, for the discriminator that want to minimize this value. That means want to output the DJZY that equals 0. Finally, that can maximize this loss function. And on the other hand, the generator J want to minimize this the total loss function. That means for the J part, for the first term, this is constant. We check out the second term. For the second term is that because that minimizes function, that means for the given generate that sample JZY, the output for the discriminator that is that also like the 1. Originally we can say discriminator want to make that is 0, but the generator makes that is the 1. So this is the zero-sum game or minimal max 2-player game. After training, if we get the after training part, if the discriminator cannot distinguish that the true data or generate data, that means that the distribution of the D is equal to the 1/2. After this one, that means we can get output generator, the good generator. It can generate the high quality label data given this. Then let's see that the generator model and the discriminator model. For the generator model, we can see we use the 4 hidden the dense layer And each of these layer, we can see with the different, the neurons. And then we use the leaky ralo as the activation functions and follow the batch normalization. Okay. And the last layer, that output layer, there are the batch size that is the size is 2 times 128. For the generator, we need to generate that the IQ that samples. And the other one is the discriminator. And for this one, input is with size 2 times 128. And there are 3 dense layers and follow the dropout layer. And the last layer, just one neurons. And with sigmoid, to clarify that is the 1 or 0. Okay. If we train this model, finally we can get the best generator. Based on this rich model, we can produce that labeled high qualities IQ data set. Okay, this is our model. Last part is we discuss about experiment part. So for the data set, as we mentioned before, we use the radio ML 2016 10A data set with 11 different modulations. And we consider the range SNR, there are 20 SNR, and also for the training and test data are divided by the 80% to the 20%. And also we consider our platform. We use the TensorFlow, Keras, and other library for the training, thinking, and the same models. We also use the Google Cloud. Is used as the free cloud surface to train our model with GPU. And for the performance classification accuracy, we used F1 score. And we consider the benchmark model is the same model. First, let's see the result for the synthesis data set. And for this figure, for left figure, that is original data. The right figure, that is synthesized data. And from the synthesized data, we consider SNR equals 16 dB. For the different modulation, we can see we can generate similar modulation data set. Like the BPSK, we can see for generate BPSK, that is similar with original BPSK. Just for some area, like this part and this part, is a small difference. And for other complex modulation, like the CPFSK or the GFSK, we can see our solution also can generate that similar the shape of that the modulation data set. Even though for the this QM64 modulation data set, IQ modulation data, also our solution get similar the shape for that data. After we get the sensitive data set, next one, we need to use the same data set for the train our same models. And this shows the training performance. And the left part is we consider different sensitive data. Left part is 1 solid, right part is 5 solid sensitive data. And we can see the training curve. If we consider the more training data set for this one, after 15 epochs, it can converge. And for this one, it requires 40 epochs to converge. And next one is we show, we use adding the different synthesized data set from the 1 solid to the 5 solid samples. And also we compare with the original data set with all the CDM. And we just show SNR equals 16 dB. And from this performance, we need to find, the figure 1 for here, if we use the 5 solid synthesized samples, we can get the darker diagonal, that blocks, for here. That means it can get a very high classification accuracy. Then we can see, the original data, so there are several scattered, that samples predict labels in other modulations, especially for the 8 PSK, QAM16 or the QAM64, QPSK or WBFM. Next one, also we show the confusion matrix over the different SNR. So one is SNR equals the 10 dB, another one is SNR equals the negative 4 dB. And for this, we needed to find, okay, the SNR, when SNR equal to 20B, the classification accuracy is slightly better than the SNR negative 4 dB. That means, okay, the augmentation solution with the C-gain is helpful to the lower SNR. Okay. And then we can see this classification accuracy. But over the different SNR, okay, from the negative 20 to the 18, we need to find, okay, our generated data set can get the higher F1 score than the original data set. Another thing is, as we increase the generated data, we can get the higher F1 score. And also, if we check the higher SNR, okay, the performance, that is, F1 score is about 0.9. It can get the 25 % gain in the F1 score. But the lower SNR from negative 20 to the 14, negative 14, we also can get the 16% gain in F1 score. That means our proposed solution get a better performance with the augmented data set. Okay, that part is we summarize this work. In this paper, we propose the C-gain-based data augmentation approach for the SAM-based AMC. The idea was to use the C-gain to generate high-quality label data set with small amount of the saved data, thus overcoming the high quality and challenge associated with getting the various data set. And with the public data set, we show the SAM-based modulation classification could benefit from the proposed data augmentation approach. In the future, we will investigate other different models like the LSTM or the bidirectional LSTM for AMC with the C-gain-based data augmentation. Okay, thank you. If any question, okay.
So, thanks, Professor, to you for the presentation. Are there any questions for the authors? So, is there someone asking a question? Okay, I have just like a quick one. So when augmented data, do you have any tool to kind of preserve the decodability of the signals?
Yeah, we use that the radio that data set. Yeah, so that is generated from the GNU radio. So our idea is use C-gain to generate more diverse data set, so to improve the classification accuracy for this.
Thank you. So if there are no other questions, I think we can move to the third presentation. The presentation is titled Encrypt Rich Data Steganography Using Generative Adversarial Networks. And this will be presented by Dilshu, who doesn't remember him, is a PhD student at Carnegie Mellon University in Pittsburgh, and whose interests are in generative adversarial networks and deep learning. So Dil, please go ahead with the presentation, and thank you. I think you're muted, Dil.
How about now?
Yeah, that works.
Oh, okay. Let me just quickly share my screen and I'll start my next presentation quickly. Can everyone see my slide screen?
Yes.
Okay. So, hello everyone. This work that I'm going to present is about image-based steganography using generative adversarial network, and this is work I did in collaboration with William Hong and Jamin Chai from Pennsylvania State University, as well as my advisor Conrad Tucker from Carnegie Mellon University. So for those who's not very familiar with steganography, so steganography is just another way of achieving secret communication. It's very similar to encryption, except that instead of encrypt the secret message, we embed or hide that secret message into some other form of data, which we call the cover data. We send the cover data containing that secret message to the receiver and allow the receiver to decode that message from the Stego data. And in this work, we're interested in image-based steganography, meaning that the cover data we choose will be image data. And the reason for us to choose the image data as the cover data is that these days image is everywhere. They are widely used in various domains, especially in social media. So if you want to send a picture to someone else and hide some secret message in it, most likely nobody will feel suspicious about it. Also, the message, in order to hide secret message into an cover image, all we need to do is to convert the secret message into small perturbations of pixel values of the cover image, add those perturbations to the cover image, and then we obtain our Stego image. Another advantage of image-based steganography is that after message embedding, we obtain a Stego image which is exactly the same size of the original cover image, and therefore, we're not introducing extra consumption of the capacity of the communication channel. And again, this is a brief comparison of our work with some other related work according to some technical features. And so I just want to, and the steganography model that we choose is a neural network model. And the reason for choosing neural network as a steganography model is that neural network is good at processing various type of data, particularly a large volume of data, and also neural network model, we believe that it is good for secrecy of steganography, because neural network model its complexity can prevent the steganalizer from easily getting the embedded message from the cover image. And here is the overall overview of the neural network architecture of our steganography model. So it's actually an GAN model, which consists of a generator and a discriminator. So the generator consists of an encoder and a decoder, and the discriminator is a small module which we call the adversary module. So what the encoder does is that it takes the original message as input, also the cover image as input. The original message can be from one of the three data types: the text message, the audio message, or the image message. And these secret message and the cover image will be combined in a certain way inside this encoder, and the output of the encoder will be a Stego image. And we introduce this adversarial module in order to kind of perform the role of play the role of the steganalizer, which detects, which tries to detect the Stego image from regular images. And so in doing so, this adversarial module helps to create an adversarial machine learning settings. And through adversarial learning, hopefully we can improve the performance of this steganography model. And after we obtain this Stego image, we sent it to another module, which we call the noise layer module. And this noise layer module is designed to simulate the information loss during data transmission. And the information loss includes dropout and cropping of the stego image, as well as the JPEG format blurring. And these are just some closer look at each individual module in our network architecture. So the encoder, as I said, produces a stego image, and this is the architecture of the encoder. And similarly, we have the decoder and this specified architecture. And our adversary module is a simple convolutional neural network for stego image detection. And finally, this is our noisy layer. So note that before we can combine the original message and the cover image, we need to do pre-processing to both of these two inputs. So for the original message, we need to use a feature extraction module to convert the message of its original form to a feature vector representation. And we combine this feature representation with a feature map that we get from the cover image using convolutional neural network. So after we obtain this combined feature map, we make it pass some more layers of convolutional neural network and eventually obtain our stego image. And we pass it through the noise layer, get a noisy stego image, and then we use another convolutional neural network to decode the feature representation of the secret message. And then finally, we use a message reconstruction module to recover the original form of the secret message. And now I would like to talk a little bit more about the design of these two modules, the feature extraction module and the message reconstruction module. So, and their design depends on the type of input secret message. So for sequential secret message, meaning either the audio message or the text message, we use a sequence-to-sequence model consists of an RNN encoder and an RNN decoder to achieve this bidirectional mapping between the original data space and the feature vector data space. And for the image space, the task is a little bit simpler. All we need is a CNN encoder and CNN decoder. And we also actually, in order to add another layer of secrecy to our steganography model, after we obtain this encoded feature vector, we perform a random permutation to the entries of this vector. And we pass this permutation to the receiver as a decryption key, so that even if somehow our adversary managed to decode this feature vector, he or she won't be able to recover it to the original data format without the permutation key. So with those being said, let's take a look at the loss functions we use to train this steganography model. So the loss function consists of 4 parts. The first part is the encoder loss, which basically defines the difference between the cover image and stego image. The second loss function defines the basically is the binary cross entropy function that evaluates the performance of the adversarial module in detecting the stego image. Third one is related to the second one. Is basically a penalization term to penalize the encoder for stego image being detected by the adversarial module. And lastly, we have our decoder loss function, which consists of 2 parts. The first part measures the difference between the encoded feature representation and the decoded feature representation, and the other part measures the difference between the original message and the recovered message. So the overall loss function, without not a surprise, is just the weighted combination of the 4 terms mentioned before. So here are some experimental results that we obtained by running this steganography model. So what we're seeing here are some comparisons between the stego image and the original cover image. As we can see, they look pretty similar. So that if we let a human user to determine whether an image has been encoded with secret message, most likely the human observer won't be able to make a correct guess. And this is just some further zoomed in comparison between the cover image and stego image. As you can see, even at a much zoomed in level, they still look pretty similar. And this is the comparison of steganography performance of our method with some other related methods. I just want to emphasize here that our method achieves a higher message encoding capacity compared with some other related methods. And also, we achieve a lower detection rate by the steganalyzer. So like with a detection rate as close to like 53% or 52% is not much different from random guess. And these are some comparison between the original message and the reconstructed message or decoded message. And for the text message, we achieve a decoding error as low as 0.017 word per sentences. As you can see, most sentences can be recovered accurately. And for the audio message, I don't know if can someone hear? I guess not. But basically, we have recorded the original audio sample and decoded audio sample. So they are someone's pronunciation of a certain English word. So basically, by listening to the decoded sample, you can clearly tell which word that person is saying in its original audio. And lastly, let's take a look at the decoded image data and the original image data. As we can see, the reconstruction seems to be pretty accurate, and I personally don't see any reconstruction error. So that's all I would like to present for this steganography model. And for future work, we're interested in developing a multi-layer steganography using our proposed neural network model, and see if if we can still achieve a sufficiently accurate reconstruction of the secret message. We believe that multi-layer steganography will greatly increase the level of secrecy in steganography. That's all I would like to talk about this work, and I'm happy to answer any questions that you may have.
Thank you for the presentation. Are there any questions for the authors? Okay, I have one myself, actually a bunch of them. So you mentioned that there is a private key that you send to the receiver to decode the message because you do the randomization of the information. So is this something that you do per message, or it's something that you do like once and then it stays there? And if it's per message, what if this is lost or the adversarial discriminator gets this information? Have you considered those problems?
By randomization, do you mean the permutation I added to the feature representation? Oh yeah, this sequence of permutation, it serves as a encryption key. So as in encryption, so we need to have both the encoder, both the sender and the receiver in this steganography model needs to have accurate knowledge about this encryption key. Otherwise, the receiver won't be able to decode the secret message sent by the receiver by the sender.
Okay, thank you for clarification, Duo. So if there are any other questions, I suggest the authors and other attendees to meet in the Mattermost and address their question directly there. So thanks everyone for being here. This is the end of session 1. We have some great papers, and thanks to the authors, and thanks you for attending the session. See you later. Bye, everyone.
So welcome to session 2 for attack detection and defense. I'm Michael DeLucia. I'll be the chair for this session. I'm from U.S. Army Research Laboratory. And so we want to keep the talks to about 20 minutes, but probably about 15 to 18 minutes to leave some time for questions. We have about 4 different talks. So the first talk is a network security classifier defense against adversarial machine learning attacks. It's by myself, and Chase Conton will be presenting this. And he's from University of Delaware. He's a professor there. So go ahead, Chase.
Sure. Well, good afternoon, everyone, if you're in Europe, and I guess good morning if you're here in the States. Today, I'm going to describe a set of experiments that Mike and I did in the network security domain. And by that, I mean, think in terms of packets and flows of packets. And this work basically applies both to the wired and wireless domain. So I'm gonna, as these talks are short, I'm gonna skip the standard outline, but what I wanna focus on is this picture shows a typical layer defense found in a modern enterprise network. And there's no wireless in here, but the modern enterprise does have lots of wireless, and increasingly 4 and 5G eventually. Our focus today is really about the challenges that we face as machine learning gets incorporated into our intrusion detection systems, our intrusion prevention systems, and then later into our network and host firewalls. And not shown on this diagram is that machine learning will also find its way into our SIEMs and our threat management systems. What I'm going to cover today is a set of experiments. One is an experiment in network security classification with an associated, test set database. And this is, again, the same function that I show above in the IDS systems. And then I'm going to talk about a matching adversarial machine learning attack that Mike invented to thwart a machine learning classifier. And we're not going to talk about that today, but you can read about it. And then what really the focus of today's talk is how do I defend as a machine classifier against such an AML attack? And we're going to do it based on a hierarchical ensemble detector. So clearly, machine learning is going to be introduced into our systems. It's largely research now and a bit of snake oil when it comes to commercial products, but it's going to find its way into our systems. And once we have machine learning in our systems, the bad guy is going to use adversarial machine learning to either defeat or degrade our machine learning based security systems. Most of machine learning today, the really great success have occurred in images, the 2D CNN work, and it's very inventive and it's very successful. Network security classifiers are quite a bit different. They are largely based on carefully engineered derived features that were engineered by a subject matter expert. And in this particular case, as opposed to modifying an image so that my aircraft looks like a toaster or is classified as a toaster, the attacker is going to have to perturb my features so that I misclassify his attack. So we're going to talk specifically about an original attack, not an AML attack, but a classifier that's trying to detect network scanning. Network scanning, something that an attacker does to assess the attack surface of the defender's infrastructure, what machines are there, and what services they are offering. And the ubiquitous nature of wireless networks makes these techniques applicable to wireless as well as wireline. And what's more importantly, and you saw this in the keynote speech, or at least alluded to, is that we have extremely poor security history in the introduction of most all of our wireless products, whether in Wi-Fi and LAN or whether in mobile security. So I'm going to briefly go through kind of the related work in terms of AML defenses, but I'm not going to spend a lot of time on it. The references noted here in this slide are at the end of the deck. There are three major paths. One is adversarial training. Your classifier fails under an adversarial machine learning attack, and then you basically retrain your classifier with either captured AML attack samples, or you generate those samples yourself to be representative of what your attacker is sending you. And this is very common. A second method is called detection and rejection. And basically, this is an attempt to rule out samples and don't feed them ahead of time to the classifier that are statistically different in some major way from the training samples, either due to their features or some statistical basis. And then the last is something called classifier ensembles. And our work today this most closely resembles this technique. And in the classic case, an ensemble basically combines multiple diverse classifiers that then vote on the selected classification, and they work in parallel. And if possible, it is often useful if they've been trained on different sets of training data. So let's talk about our defense approach. Let's assume that there's a traffic set that it could be benign or malicious. We've built a classifier to detect it, and the bad guy has created an adversarial machine learning attack that is fooling our classifier. The model that we propose, as opposed to a parallel ensemble, is a hierarchical ensemble in which the attacker, and in the schematic below, I've got a botnet, and I've got a classifier called H1 that's based on TLS record sizes. TLS being those records that make up all of our encrypted web traffic using HTTPS. That classifier is working. The botnet attacker has added some AML traffic, and the H1 classifier is failing. And I'm going to add a second, or maybe a third, or maybe a fourth hierarchical classifier. In this case, I'm adding a second one called H2. And in this case, this classifier will be based on a different set of features in hopes that the traffic that the botnet AML attack, which has been carefully crafted to fool the H1 classifier, will not fool the H2 classifier, and if necessary, other classifiers after that. So the basis of this work is a data set and a classifier done by another researcher. In this particular data set, the classification is to detect scanning. Again, that activity that an attacker will use to inventory my attack surface. And oftentimes that's done with Nmap. And so this data set is a set of benign traffic and a set of Nmap scanning traffic. And the classifier that goes with this is rather simple. It's a feature-based classifier with 3 engineered features, and it's based on an SVM. And basically in this, the 3 features are the percentage of unsuccessful TCP flows, because scanning often has flow failures, TCP connection failures versus the number of TCP connection successes. And then a percentage of the network flows that are UDP and a percentage of the flows that are ICMP. And this detector, this classifier works perfectly, 100%. And in this particular case, you can see I've I've got a new schematic of what the layered hierarchical ensemble detector looks like. The traffic comes in from the left. The H1 scanner represents the features that I've just described in the original experiment. And now we're going to add a second scanner, H2, and we have to decide what that scanner will be so that it can deter an attack on H1. As part of this, we have other work that actually defeats that scanner and defeats the H1 classifier. So let me talk a little bit about the difference between the creation of an AML attack in what we're all familiar with in the image domain versus the network domain. On the left, a classic image recognizer, hand-drawn digits. We scan those pixels. They, in fact, become the features themselves. We build some kind of handwritten digit classifier, neural network or otherwise. And then the way that we would create an adversarial image is we would perturb that feature in such a way that a human being might not notice that it was perturbed, but it would be perturbed at a layer that is at a fairly low change amount. We would do this until the adjusted image, the perturbed image, causes our classifier to malfunction. And in this particular case, cause the image that's obviously a 3 to be misclassified at a 7. So what's actually done is I've actually adjusted the pixels of the image to cause the misclassification. Network security is quite a bit different. The front end's the same. I have network traffic. I compute features, and in this case, these features are based on traffic flows. I have a classifier, the one I mentioned, that successfully detects scanning attacks. Now, in order to build an AML attack, I have to perturb the features, not the traffic, the features. I have to perturb the feature values until those adjusted perturbed feature values cause the classifier to fail. And that would be fine, except for this is not an image. I can't pass those features onto the network. I actually now have to map those adjusted features to actual traffic. That is not quite, it's not horribly difficult. I can add some traffic to help me do that. But what I have to do, however, is whatever traffic I add to the flow with my original attack, that traffic must continue to be legal protocol-wise, or it'll set off all kinds of flags in all of my security sensors around the network. So in the adversarial machine learning attack that we constructed, by adding traffic to the existing attack traffic, the scanning and benign traffic, we were able to cause the classifier to fail 100% when classifying scanning traffic. So it still was correct classifying benign traffic, but all of the malicious traffic, the scanning traffic, was classified as benign, as you see in the red 57. Okay. So now we're at the point where we want to create the second classifier in this hierarchical ensemble defense system. And so one of the things is that when you scan, once you've identified the machines, you scan for open ports that represent applications that are running on those ports listening for connections, because you can then use those applications as targets for attack. And the hope is that the defender has left systems up which can be attacked. Security practices today require us to limit those open ports only to the ones we need for the mission of the server. And so maybe for a web server, we're going to keep HTTP open on 80, HTTPS open on 443, and maybe SSH for maintenance. But the scanning, the attacker is going to scan far more ports than they're going to be found. And so in this set of features that we've constructed for H2, we're going to look at the unique number of destination ports that were scanned. And then we're going to look at the distribution of those destination ports by using an entropy measure. And then last, again, we're going to fall back on a metric related to the unsuccessful TCP connections, which is a big indicator of scanning attack. Okay. Again, this represents the original traffic, the original classifier H1 shown on the left, the added AML traffic that I described, but we didn't go into that, but I didn't go into in any detail. And then the second classifier based on these unique destination ports and entropy, the H2 classifier. And as you can see, the cascaded nature of these two classifiers is return the results of this classifier back to what it was prior to the first AML attack. The 51 benign traffic are classified benign, and the 57 actual scans or malicious traffic are classified as malicious. Okay, in summary, clearly machine learning is going to become a component of our network defenses. And that means we're going to have to defend the machine learning because, as we all know, machine learning, whether it's statistical or neural, is a little bit fragile. It can be fooled by pushing samples around across these decision boundaries. In our case, we've proposed a hierarchical ensemble of classifiers using disparate feature sets. The defender uses AML to discover vulnerabilities of classifier, and what we've shown is 2 successful AML defenses. And one of the things this buys us is, one is it's not in parallel. It saves us some computation time. It increases the cost to the adversary because he must continually defeat each of our successive classifiers, and that requires a significant amount of work. And then going forward, we're going to continue to look for additional defensive techniques that we find in this kind of adversarial network security environment. And then we also will take a look at exactly how this hierarchical defense mechanism should be structured. These are the references as I mentioned earlier. And now I'd be delighted to take any questions you have.
Thank you, Chase. You can, any questions can be through the Zoom chat or Mattermost, or you could just jump in. Any questions?
You may have to read me the Mattermost. I've lost them.
Okay, it doesn't look like there's really any questions. So thank you again, Chase.
Okay. Thank you, everyone.
Our next talk is machine learning driven intrusion detection for Contiki NG-based IoT networks exposed to NSL KDD dataset. It's being presented by Jixin Liu and Barak Kantarsi from the University of Ottawa in Canada. So you can go ahead and start your presentation.
Okay. Hi everyone. How can I share my screen?
At the bottom, there should be a share screen.
Okay. It said I cannot start screen sharing while others is doing it. Okay. Okay, so hi everyone, my name is Jixin Liu from Mexican Lab in School of Electrical Engineering and Computer Science in University of Ottawa. And its title is Machine Learning Driven Intrusion Detection for Contiki NG-based IoT Network Exposed to NSL KDD Dataset. So this work is carried out collaboratively by Professor Kantarsi, Professor Adams, and me. So today I will talk about a brief introduction and some related works and our methodology, how we generate normal and attack trees, and how we extract features from our network flow. And then we will feed our dataset into multiple machine learning algorithms to classify their intrusion types. And finally, I will conclude our work and provide some future direction. So IoT has been widely used in our life in smart environments, but due to rising criminal incidents, security of IoT system has gained more attention in recent years. Some researchers have tackled this problem by using machine learning algorithms to detect IoT network intrusions. But due to the lack of IoT dataset, some work had to be tested on an NSL dataset. NSL dataset is a widely used dataset, but the thing is, it doesn't involve too much IoT settings. So we think we can maybe introduce part of the attack techniques from NSL-KDD to IoT network by reproducing the attacks in Kentucky operating system and simulate our network via Kuja, which is an IoT simulator. And this related work. Zhang et al. Employ Kuja to generate DDoS and define it by checking network consistency. And another work simulates normal traffic using MQTT protocol and apply Kali to generate botnet attacks. And another one, Gara et al. Utilize Kuja as a simulator and simulated black hole and gray hole attacks targeting routing protocols in 6LoWPAN. So, and as we talked before, NSL-KDD dataset has been widely used in numerous studies to validate NIDS and machine learning algorithms. And there are 4 different attack types in the NSL-KDD dataset, including DOS, R2L, U2R, and probe attacks. So we implement part of DOS and probe attacks since other attack techniques require application layer protocols like remote desktop protocols or email protocols, which are not as commonly seen as network layer protocols, i.e. TCP, UDP in IoT settings. So to summarize our motivation, the current IoT network can still be threatened by traditional attacks such as those in NSL-KDD dataset. And we introduce attack techniques in NSL-KDD into IoT environment. And this is our methodology. As the flowchart shows, we first create normal traffic and attack traces, and then we export these network packets from Kuja simulator, and the features will be extracted from these network flows. And now we can have a data set. Once we label our data set, we can fed it into machine learning algorithms. And finally, we'll evaluate their performance. And this is how our network system looks like. We have one sync node, which aggregates network traffic and can receive both UDP and TCP traffic. And we also have 10 sensor nodes run TCP protocol and the other 10 run UDP protocol. And we also have a malicious node, which can generate attack traces in different time period. And this is the attack types, which has been implemented in a Kentucky NG system, and they have been verified their impacts on that OS. So for DOS, we have SIM flood, LAND, UDP flood, pin of that, and Smurf. For probe, we have IP sweep and port scan. Once we have our network traffic, we can use an existing work called Network Intrusion Dataset Creator to extract features, and their work has been stated in the footnote. And we slightly modify it to well-supported IPv6 and 6LoWPAN protocols. So this tool will extract some statistic network features in each layers, such as the number of packets and the length of packets, something like that. And this figure shows our dataset distribution. So as we can see, the majority class is the normal traffic, and the number of samples is varied because the characteristic of different attacks and how long we run this attack. And then we utilize multiple traditional machine learning algorithms to test and classify these intrusion types. So for supervised method, we try decision tree bagging, random forest, Bayes night, SVM, naive Bayes. And to tackle this imbalance problem, we also try to add a boost and RUS boost. But unfortunately, their performance is slightly lower than other supervised method. And for unsupervised method, we tried expectation maximization, dbScan, and k-means. And this is a summary of performance of supervised method. So as we can see from this table, tree-based method like decision tree bagging, random forest, and XG boost achieve better performance than others. Their accuracy range from 96% to 97%. And among which XG boost has the best performance. However, naive Bayes at a boost and SVM may be not suitable for this problem. Not only in terms of accuracy, but also MCC and UC area. We also tried an unsupervised method, and the number of clusters is not exactly the same as the number of class in the dataset. So we tuned the number of clusters or other parameters to maximize the accuracy. So EM outperforms the other two unsupervised methods, achieving 67.2 accuracy, and dbScan and k-means result in relatively lower accuracy. So finally, to conclude our work, we introduced possible DOS and probe attack in an SLKD dataset into an LT network. And we use Kentucky-NG operating system and CUJA to simulate our network. And the generated dataset is fed into 11 machine learning algorithms, supervised and unsupervised included, to explore their abilities to classify different attack types. And among the machine learning algorithms, actually XGBoost provide the best performance, and the other tree-based method also offer 96% accuracy. And EM as an unsupervised method achieves 67 in terms of accuracy. So in the future, we plan to integrate more different attack types, such as routing protocols, firmware update, and application layer attacks. And we also plan to try other unsupervised methods, and we maybe investigate the HMM or GMM in the future research. And that's it. Thanks for listening. Any questions?
Hello, I have a question.
Hi.
So first one is that you use the supervised learning for the detection. So what's the feature from that network data set for this supervised learning? This is my first question. The second one is that how to know the number of the cluster for that network data set for the unsupervised learning. Yeah.
Okay, so for the first question, the features we used in this dataset is some statistic features like how many packets within a network flow, or how long this traffic is, the duration of this traffic. And for the second question, we tuned the number of clusters to maximize its accuracy, so it's not exactly the same as the number of class in our data.
Question is that you automatically to choose a number of cluster or manually to choose that?
Oh, I'm manually tuning the number of clusters.
Okay, okay, thank you. Yeah.
Thanks for the question.
Actually, I have one question as well. Talking about the features, did you do any scaling or normalization on the features?
Oh, yes. When we run the machine learning algorithms, we first normalize these features.
Okay. And then for the unsupervised learning, do you have any ideas on how you might maybe improve to try to get a little bit better accuracy, or do you think that just unsupervised is not good for this type of problem?
I think unsupervised may maybe not have higher accuracy as other supervised ones, but the advantage of that unsupervised method, it doesn't need labels. So maybe when we face the real network problem, we can use this unsupervised method. Thanks for the question.
Okay, thank you. Any other questions?
Actually, I have a question. So for the unsupervised methods, did you do the clustering using the input features directly, or did you do any other feature learning directly from those input features?
We didn't try the feature engineering method. We just directly send these features into these algorithms.
Okay. Do you think you'll get any benefit or boosting accuracy if you are able to find any like more abstract feature representations from the raw input features that you are using right now?
Yes, I think in the future we may try different, more advanced methods to detect it. Currently, we just use some traditional method to test our data set.
Thank you.
Thanks for your question.
Okay, if there's no more questions, thank you for the presentation. We'll go on to our next talk.
Thanks for everyone.
So our next presentation is Algorithm Selection Framework for Cyber Attack Detection, presented by Mark Chale from Air Force Institute of Technology.
Hi, can you hear me okay?
Yep.
Okay, I'm just gonna work to get my screen shared if that should only take a second. So I have a message here. It says you cannot start your video because the host has stopped it. And I don't know what it means.
I'm not sure about that one.
And what I could do is I could log off and then come back on immediately. That might help.
Okay.
She said try again.
Oh, yeah, now we see your video.
Okay, great. So now I just need to shift to the screen share. Okay, I think we're good now.
Yep.
All right, well, I'll start my timer. I can be as short or as long as you like, but I was planning on about 20 minutes, including questions.
Okay, that's good.
Okay, well, definitely thank you to our host, our committee chairs, and to the host university. I also want to acknowledge my advisors, Dr. Bastian and Dr. Weir, who have guided me through this project. I'll quickly introduce myself. I'm Mark Chalet. I'm a data science student at the Air Force Institute of Technology in Dayton, Ohio. And if you have any questions after my presentation, of course, don't hesitate to reach out to me directly. And what I want to do now is I want to start to understand why I chose this as the research question for this venture. And what's interesting to me is, well, we continue to see more and more, all the research says there's more and more cyber attacks every year. And we have seen some success of meta models, or also known as machine learning models, to detect the anomalies in the network traffic. As our last couple of presenters alluded to, there's been quite a lot of success in that field. And at the same time, our actual machine learning algorithms are advancing. We're getting better at classifying anomalies with machine learning and meta models. And we're also experiencing this societal shift towards the wireless domain. And for example, my cousin, he lives in Las Vegas, and from his cell phone, either through Wi-Fi or 4G, he can control the shades in his home, the lock system, the garage door, and the heating and cooling system. But with all of these aspects of our lives becoming digital and wireless, we really need to make sure that they stay safe and private. And that's why I want to introduce my problem statement, and that is to perform the algorithm selection for the intrusion detection system in the wireless domain. And we're going to transition now into a little bit of the background, starting first with a quick background of machine learning to those who aren't intimately familiar. It's sometimes defined as training algorithms to parse, learn from, abstract, and act on data. So we're building models from the data itself rather than from our theory or our knowledge of a system. And I'm just going to present some of the big turning points to me in the recent history of machine learning. In the 1940s, cybernetics was this movement in artificial intelligence where we combined the theory from math and biology, psychology, engineering, and other sciences to try to have machines make decisions like humans would make. And in 1943, McCulloch and Pitts, they presented this mathematical model of a neural network, kind of like what we have inside our brains. But we weren't able to use this directly to solve problems for many decades. And in 1969, there was a very influential book by Minsky and Papert that said that machine learning, and specifically the neural networks, would never really be able to solve any useful problems. And that publication took on some traction, and we lost a lot of references to this neural networks for many years. But a couple decades later, in 1986, Rumelhart, Hinton, and Williams proposed the backpropagating neural network training algorithm. And that was the first time that we had really good practical success with these artificial neural networks and the perceptron model. And really it was this, to me, it was this renaissance in the field of machine learning that we're experiencing today. And here we are in 2020, we use machine learning pretty much ubiquitously, from defense analysis, energy exploration, in medicine, and in cybersecurity. Cybersecurity is obviously the domain that I want to focus on for the rest of this presentation. I really do appreciate the introduction from our last couple of presenters who introduced what a intrusion detection system is and how it's essentially a unique phase of a cybersecurity system in a network that actively monitors the traffic for anomalies. And I'm going to talk about how we want to pick the best machine learning algorithm for this particular domain. I just think it's so cool how in the field of data analytics, data science, machine learning, we have so many different techniques to choose from. And that's part of the excitement that makes me want to wake up in the morning and do data science. So let's pick the best data science technique for our question of algorithm selection. I love this quote by David Wolpert. He says that by any measure, all algorithms are equivalent on average. And what that really means is you may find that some algorithm works brilliantly to solve a particular problem, but then when you're introduced with a new problem, you can't really, without a priori knowledge, expect that your successful algorithm is going to be successful on unseen problems. And that's, again, why we want to do this algorithm selection for the intrusion detection system. I'm going to just visually show here that if you have a set of problems, we call X1, X2, and XM in our problem set, then there's only a subset of all our available algorithms that can really work well to solve those problems, and even a smaller subset that are going to work well enough to actually choose. Maybe there's only one that's the best performing algorithm. John Rice from Purdue University introduced this formally as the algorithm selection problem, and he also proposed this framework, and he said, if you have a space of all your problems and many different algorithms to choose from, candidate algorithms, if you will, maybe you have a performance metric. And in my case, since I'm doing classification, I talk about classification recall. Now, if you enumerate every single combination of problem with every algorithm in this problem space, and you report its performance through a metric, you can, with complete certainty, say which is the best algorithm for your problem. But the issue here is that to actually perform every single algorithm on every single problem, it's just computationally intractable. And we want to save some time. And now we introduce this field called meta learning, and that's learning on the learning process itself. And we can actually use meta learning for algorithm selection. That was demonstrated by Kui et al. In 2016. And what she did in her paper is she took these problems and she trained a model that related features of your problem to the performance of your algorithm on that problem for many different algorithms and many different problems. And now we could predict the performance of unseen problems before we actually use these algorithms in real life. And I just do want to mention that this was wildly successful, and she, in 94% of cases, predicted the best possible algorithm from the candidate list to solve before actually using the algorithm, which just kind of took the algorithm selection went down from many minutes to just several seconds, and it was extremely useful. So I'll show a new methodology, an expansion on this framework for algorithm selection, and how I did algorithm selection for the intrusion detection system on a wireless network. All this slide shows is that for any analysis process, at some point in your process, you have to do algorithm selection. And we propose that algorithm selection consists of 3 levels. That's the determine the analytical objective, which is essentially the type of insight you're looking to receive from your analysis work. Then to determine the analytical approach, where the analytical approach is, just think of like some subset of all of the techniques out there. There's a handful of approaches to choose from, and your techniques fall under these approaches. And finally, we need to determine the specific analytical technique, that one algorithm or one analytical technique that is best for your problem. I propose that there's three drivers for this algorithm selection. That's the assigned task, usually given from like a decision maker or a corporate executive. Then you have to consider what resources you have to do your analysis, which may consist of things like time, money, hardware, software, perhaps personnel to do your analysis. And the data, if you in fact have data, what does your data look like? Is it tabular? Is it some sort of media? Or is it maybe a bit more abstract form of data to do your analysis? We also proposed that to do this algorithm selection, we should organize all of our candidate algorithms into a taxonomy. And we show that taxonomy should be a bit hierarchical and multi-layered, so we could expand it as we need. And we also show kind of this object-oriented approach to building our taxonomy. So if our algorithm selection requires knowledge of whether a particular technique can be trained online or offline, we could add that to our taxonomy. Or for instance, maybe there's some other data requirements or resource requirements like hardware for a particular algorithm. And this new paradigm to think of a taxonomy is something that I want to build on in the future, and we use it in this research. So step one of the algorithm selection is we take the assigned tasks from our decision maker, and maybe they tell us that we need to do some prediction task. And we show in this graph here that the prediction falls under the categories of analysis called predictive analysis and prescriptive analysis. And these categories of analysis come from the Inform's Handbook of Analysis. And depending on what category of analysis our task falls under, we can map to specific analytical approaches. These are kind of familiar terms. I think I've also seen them referred to as functions in some texts, the functions of analysis. But those are things like regression, classification techniques, multivariate techniques, or reinforcement learning. But all in all, we're starting from a task and we're leading towards a subset of all our algorithms, what we call the candidate algorithms for our analysis. Now in step two, what we're going to do is use meta learning to rack and stack the candidate algorithms by their expected performance. And we initially did this using a black box meta learner, specifically support vector regression. And we predicted the classification recall that a particular algorithm would yield on an unseen problem. And that's pretty cool. I'm going to introduce the data that we used for this experiment. It's actually a great transition from our last presenter because I also used the benchmark data set called the NSL-KDD data set. And on this data set, we're going to look at records of network traffic and predict whether or not they're malicious actors or normal users. So I used the version of the data set with 12,000 records, 43 attributes that were categorical, binary, and discrete. And I binarized the target to just look at whether the actors were normal or malicious actors. And to train the meta learner, we also used some of the NSL-KDD training data set. And what we did is we ran our algorithms on various problems and recorded their actual performance. So this is what the actual performance is what we're using to build our model. Additionally, I added some other data sets to add diversity to my meta model. And this shows visually what we did is we have from each data set, we have some features from that data set. And we also have the observed recall from that data set. And when we put the observed recall and the features from many different data sets together, that gives us the training X matrix for our meta learner and the targets for our training set of our meta learner. And that's how we trained our meta learner. And I'll just go into what we specifically did in our experimental design. Well, what we did is we took the baseline of support vector regression as a meta learner, but we also wanted to explore some more interpretable meta learners, such as the random forest regression and the lasso linear regression. So we built 3 meta learners, and we used our training set to perform the recall performance on the test data set, which were the unseen data. I showed the pseudocode on the right-hand side of the slide, but we can always refer back to that if there are any questions on it. And by the way, the candidate algorithms from step 1 were decision tree, random forest classification, naive Bayes classification, support vector machines, and we actually used support vector regression to classify each record as either malicious or normal. And what was cool about that one is we want to see if an algorithm that wasn't designed for classification could successfully classify. So we did this several times for each of our meta learners. We did 3. And we got some results in. And this graph, I think it's pretty cool in this chart. We showed the observed recall for each of our algorithms on the NSL KDD test set. And I think you could see pretty clearly that our meta learners do have some correlation with their predicted recall versus observed recall. And some of our algorithms, we were able to predict very closely what the recall was going to be, and others, we were not always consistently correct. But what we did find is that the random forest classification was the best classifier for malicious actors in our NSL KDD data set. How did our meta learners do to predict that? They did pretty well. So the recall efficiency is how well we classified with recall compared to the best observed classification. So it's like how well we did compared to how well we could have done. And the support vector regression meta learner did not classify as well as random forest regression or the lasso regression, the lasso linear regression meta learner. But what was also pretty cool is we started to get this correlation in our ranking of our meta learners performance. So we were able to predict the order of these algorithms compared to the observed performance pretty well with the lasso and the random forest regression. Sorry, I'm trying to pull up my timer. Okay, I'll be quick to results and conclusions. We also determined through the lasso and the random forest regression that our most important attributes of the data set were this kind of similar in both models. So the average number of factor levels was the attribute that was most important for the lasso meta learner and the second most important for the random forest meta learner. What we're able to conclude from this is that the random forest and the lasso meta learners actually outperformed our baseline meta learner of support vector regression. So we want to continue to tune and improve those meta learners. We also noted that there was some variance in the performance of these meta learners. So we want to start to add some statistical rigor to these results and use some bigger test sets so we can really quantify what that variance is with good confidence. Then again, we recognize that the average number of factored levels was the most pervasive feature in our meta learner, but we do want to explore some additional meta features. And I know many people probably have some inputs. If you're a domain expert in wireless communication, perhaps you can help me select some better meta learner features. We think that not only is the algorithm selection specific to a particular domain, but we're starting to think that the meta learner that we use could be specific to a domain. For example, the random forest regression worked great as a meta learner in this domain, but some people might have better success with other meta learners for other algorithm selection problems. And finally, we need to start to expand our performance metrics to other things besides just classification recall, because some decision makers may require other types of insight besides just the recall, which I chose to use in this analysis. So I'm just about at 20 minutes now, and I'd again like to thank our hosts and our chairs, our host university, and my collaborators, and I'll open up the floor to any questions.
Hey, Mark, this is Chase.
Hi, sir.
Did you do the framework all by hand, or did it find its way into a common tool set?
Yeah. Yes, I did make an R-Shiny app that attempts to implement both step 1 and steps 2 of the framework. I'll find that slide for you.
No, it's all right. Is it in GitHub?
Sorry, sir?
Is it in GitHub?
Yes, I do have the GitHub, and I'll share it with you when I log off today.
Okay, thanks.
Glad to answer any other questions.
For about one more question, I'd say. So I do have one question, and if there's no other questions, is that I know you mentioned about like the resources and part, do you also take into account like the resource constraints in terms of like hardware that the classifier would be running on?
Yes, so the concept is that we want that to be part of this algorithm selection, but for this particular case study, I did not see that hardware was constraining our performance because the runtimes of algorithm selection were, once the model was built, the runtimes for algorithm selection were pretty negligible, and then the actual algorithms ran like almost instantly. But in maybe a larger case study, we would need to consider the hardware and computation time for a part of that resources factor.
Thanks.
I have a question. So for the meta learner, so you need to determine to choose some algorithm. So my concern is, what's the training time or time capacity to use the meta learner compared with original supervised learning, like SVR or others?
Right. So your question is about the runtime of the meta learner, and
to compare the original, what's the time capacity to this?
Right. From my experience, I don't have the numbers on the screen here, but I did look at them a couple of weeks ago. The time to train the meta learner was pretty substantial because we just ran so many instances of the base learning that it took a lot of time. But once the meta learner was trained, the algorithm selection or the recommendation was instantaneous. I mean, it was thousands of seconds on this laptop workstation that I have, compared to the actual base models. I would say algorithm selection was in the order of thousands of seconds, and the base learning with each algorithm was more like between 1/10 of a second and maybe 2 and 5 seconds. Typically, there is a lot of variance because.
A quick question is, for the meta learner, the recommendation result, that is stable or not based on your data set?
Is it stable? I would say no. I would say we just didn't do enough trials to see variance stabilization. If that's the metric you're looking for.
Okay, thank you.
Yes.
Okay. Thank you for the talk on that.
My pleasure.
So we'll go on to our last talk of the session. And this one actually will be a video. It's on detecting acoustic backdoor transmissions of inaudible messages using deep learning, from Sylvia Kojak Flipovich from Perspecta Labs. If you have questions for this one, you can ask them in either the chat or the Mattermost.
Hello, my name is Sylvia Filipovic, and I'm presenting our work on detecting acoustic backdoor transmission of inaudible messages using deep learning. This is joint work between my company, Perspecta Labs, and Rutgers University. We start here with an overview of the backdoor ultrasonic exploit, give an attack scenario, then proceed to describing our implementation of the backdoor channel, and then how we evaluated the impact the backdoor delivery of acoustic data has on deep neural networks. We conclude with some of the open questions. We here give an overview of our work on the backdoor ultrasonic exploit. The backdoor ultrasonic exploit was introduced in reference 1 by Roy et al., and it's about playing of inaudible signals at frequencies above the human hearing threshold that are recordable by an unmodified receiver microphone as if they were played audibly. This attack is a potential threat to voice-activated smart devices, as it can discreetly perform privileged commands or divulge personal information. So here in our work, we are trying to answer the question, what is the exact interaction with the machine learning algorithms that constitute the brain of voice-enabled devices? In addition, we are trying to figure out if we can use the statistics derived from the machine learning algorithms to detect the backdoor attack. We present here preliminary results that indicate that such a detection can indeed be implemented. The backdoor scenario, attack scenario that relates to our work is about imperceptibly sliding a command word into a smart device with a microphone. Majority of smart devices such as iPhones, Alexa, Cortana, and so on have been found vulnerable to this attack. The picture here of the backdoor exploit of a person's smartphone in a bar emulates the experiment that we conducted where the microphone was about a foot away from the ultrasonic speakers. The backdoor speakers, the backdoor system that we put together can be made portable, which is under construction, and can inconspicuously slide a command word into a smartphone in a public place, such as a bar. You see here in the picture the voice commands delivered over the backdoor channel to a deep learning algorithm that can classify the audio clips as one of the commands to be delivered to different IoT devices at home. So from a bar, you can potentially open the garage door and steal the car, or you can disable the alarm for someone to break in, not to mention unwanted orders or just a denial of service attack. Okay, so we are done with scares. Let's see what the backdoor channel is. Acoustic receiver design is standardized among almost all consumer devices. Sound waves create vibrations in the microphone's diaphragm, which converts these variations in pressure into variations in voltage on the order of tens of millivolts. In order to process this signal, it must be amplified, passing through the microphone preamp with a gain factor usually about 10. Next, the signal is filtered to 24 kilohertz cutoff frequency. As the next stage, the ADC operates at the rate of 48 kilohertz to ensure the Nyquist frequency is above 20 kilohertz cutoff for the human audible hearing range. Finally, the digital samples at the output of ADC are processed by processors, for example, packed into WAV files for playback or fed into neural network algorithms. So ideally, the preamp stage of the microphone should amplify the input signal by some linear gain factor A1. In reality, however, imperfections in the analog circuitry result in nonlinear amplification that can be expressed as power series of the form shown here, where each subsequent AK term is weaker than the previous. Cubic terms and higher are really negligible, but the quadratic form here is non-negligible, and that's the basis of the backdoor attack. By creating an input signal that is described as the sum of two tones, where both tones are above the 24 kHz cutoff of the low-pass filter, we can transmit it through ultrasonic speakers, and it will be inaudible to humans. However, after being non-linearly amplified, as shown in the previous slide, and filtered, the result will be an intermodulation frequency at the difference between the two tones. As a result, by transmitting, for example, 40 kHz and 50 kHz tone, both will be inaudible when played back, but will be recorded as an audible 10 kHz tone. This way, we can map audible frequencies back, inaudible frequencies back into audible spectrum and record inaudible tones with an unmodified acoustic receiver. So here we demonstrate the entire backdoor process on the example of a 4.5 second voice sample of a male speaker. The original voice signal is shown on the left before it is modulated by a 40 kHz carrier tone to produce the modulated signal in the middle, centered at the 40 kHz frequency, and with sidebands reaching approximately plus minus 5 kHz. This is then played through an ultrasonic speaker at the same time as another secondary tone at 40 kHz, so as the same as the carrier frequency. And the result is then recorded by the receiver microphone and is almost indistinguishable from the original voice sample. You can see it on the rightmost spectrogram and temporal waveform. So the attack scenario. We imagine an attack scenario in which an acoustic receiver typically receives audible voice messages, but an attacker sends an inaudible voice message ultrasonically through the backdoor channel to manipulate the device into recording some other message. So far, we only tried time multiplexing of audible and inaudible delivery to determine if it's possible to detect whether an incoming signal is an authentic voice message or an inaudible backdoor one. We here see the time multiplexing that we use to test this detection process. This is a physical implementation of the backdoor system. In the upper row, you see the voice signal is modulated and prepared in lab view. And then a National Instruments MyDAC device creates analog voltage. It goes through an op-amp driver. And the ultrasonic speaker plays the modulated signal. In the bottom row, you see the function generator that creates the secondary tone at the same frequency of 40 kHz, which is played through another ultrasonic speaker. So this is the delivery of an inaudible message over the backdoor channel, and let's see how we evaluate the impact of the backdoor delivery to deep neural nets. We used particular neural nets here that we have experience with evaluating adversarial acoustic examples. The neural networks are composed of convolutional layers but are trained in two different frameworks. One is the typical training by back-propagating gradient of the loss function, and another is based on pre-training with an autoencoder. The idea of using autoencoder here is because of its known properties to increase robustness of the neural network to data corruption, like corruption by computed adversarial examples or by the adversarial examples in the physical world, similar to backdoor channel. Now we put these two neural networks in the service of two tasks. Keyword spotting is the first task, which aims to build simple and efficient models for identification of keywords in utterances, particularly for the purpose of deploying such algorithms on mobile platforms. A familiar example would be iPhone and Alexa devices, recognizing the wake-up commands, Siri and Alexa respectively. The other task is the recognition of the speaker's gender. For the first test, the keyword spotting, we are using the speech command dataset collected by Google. And for the second, speaker recognition, we are using the audio set dataset, also collected by Google, which contains longer speech samples of various speakers, male or female. So we use two datasets for these two classes, for these two tasks. For keyword spotting, we present it on just two keywords from the data set that we just mentioned, wow and stop. This is done so that we can compare the results with the binary classification of the speaker gender. The keyword spotting data set contains about 1,500 utterances per keyword, and utterance is one WAV file and the associated label, and the duration of the utterance is 1 second. For the speaker recognition data set, we have 30 WAV files of duration 7 to 12 seconds each, and 15 are male, the rest is female. So we then extract bursts of the duration of 1 second from these long speaker recognition WAV files to create more data points for speaker recognition, but in essence, speaker recognition data set is much smaller than the keyword spotting one. Now we create two data sets from both keyword spotting and speaker recognition. An audible version of each sample played through a speaker and re-recorded, and the backdoor version played ultrasonically and recorded. We use the standard method of pre-processing WAV files, except for the last step. So the sample rate is 16 kilohertz, and those 16,000 samples in an array are then transformed into a spectrogram, which is a two-dimensional matrix 40 by 101, whose elements are color-coded MEL coefficients. So basically, we had 40 MEL frequency buckets per each temporal window of 20 seconds that slides over the 1 second long recording of the keyword, and that resulted in 40 by 101. The last step is different than usual. We flatten, unfold the spectrum, and so we get 4,040 features in one-dimensional vector, and we then express it in the data in dB domain. Okay, we mentioned that we have two classes of neural networks, one that are trained through an autoencoder or variational autoencoder, and another one that is just a typical classically trained convolutional neural net of the same architecture as the encoder part of the autoencoder. So to explain it better, here's a picture of the autoencoder that contains the encoder part, then the bottleneck part, which is here 105 neurons wide. And then we have the decoder that mirrors the encoder. The data point of 4,040 features is fed into the encoder, and at the output of the decoder, there's another 4,040 samples long vector, and we are training to minimize the mean square error between the input and output. Once the autoencoder is trained, we attach additional layers at the bottom below the bottleneck layer and freeze the encoder layers, and then just retune this now classification neural net, minimizing cross entropy or any typical loss function. So just to mention the architecture, we are using blocks of a convolutional layer followed by max pooling, where each convolutional layer has 8 channels and varying kernel size, so that we present this block as parameterized by the kernel size. The encoder has one such block with kernel size 10, then 2 blocks with kernel size 5, 2 blocks with kernel size 3, and finally some fully connected layers at the bottom, and that's the entire architecture for the encoder. The decoder, as we said, mirrors the same architecture. With such an architecture, we achieved the following results. This is the male-female classification, and you see that the neural network accuracy for both training frameworks is, meaning both the autoencoder-based and the classically trained, is 100% for legitimate data points, those 1 second long clips of male and female voice recordings, and for the backdoor delivered data points, we have a drop of less than 50% for the autoencoder pre-trained classifier, while the classically trained neural network drops, the accuracy drops by 40%, almost to random decision. On the right-hand side, you see the loss function that we use for detection of the backdoor data points. And you can see that the autoencoder loss presented here, or the log evidence in the case of variational autoencoder, shows consistently higher values for backdoor delivered data. And so despite the robustness of the autoencoder in terms of accuracy metric, we can still detect the intrusion by using this log evidence that is consistently higher than the log evidence for legitimate voice recordings. So here we present those statistics that we use for the detection. In the case of the classically trained network, we simply use the evidence entropy. So we use the pseudo probabilities, the output of the softmax layer, pseudo probabilities of classes, and then we get this entropy function, which is used for the as a detection statistics, whether it's a backdoor delivered or legitimately delivered data point. In the case of variational autoencoder, we use this decoder log probability evaluated on the data point in case, and then the difference with respect to a legitimate data point for that class. This is just an illustration of the autoencoder's robustness. You see that the pseudo probabilities between the two classes for different data points, backdoor data points on the right-hand side and legitimate on the left-hand side, those probabilities are well separated for the autoencoder, even in the case of the backdoor, while for the classically trained neural network, those probabilities in the case of the backdoor are all over the place, which indicates high level of uncertainty. Some open questions and future work for the end. We will explore more than 2 classes, larger distance between speakers and receivers, multipath, simultaneously playing back backdoor and audible voice recordings, and finally answering some questions like why is the backdoor accuracy on keyword spotting worse for the autoencoder. That's all. Thank you.
So I see some questions here. Can you hear me?
Yep, we can hear you.
Yeah. So there's a question. Did you use hardware like speaker and microphones to obtain real-time data set for backdoor attack? What I don't understand, what's the real-time data set? We played back every single WAV file that we had, and we were testing it through our system, both through ultrasonic speakers and regular acoustic speakers. And that's how we collected the data sets to detect using our statistics.
Okay, so my question is, because for backdoor attack for the speaker, they require some special hardware to implement this.
Just small, commercially available, very inexpensive ultrasonic speakers.
Okay. Okay, thank you. Yeah, I know this.
Okay, I think if we have any more questions, we can you could also do them via the chat or Mattermost as well. Thank you for the presentation, Sylvia.
Thank you.
So this concludes the session. Thank you to all the presenters and also for everyone that was watching us, and there's good discussion during this session. And again, you can ask any other questions via the group session or also in Mattermost if you have any more questions. Thank you again. This concludes this session.
Hello, everyone. So I hope everybody's there, even though I can't really see anyone at the moment. Okay, so let me open the second part of our workshop with the second keynote of the day. So the speaker will be Mauro Conti from University of Padua. Mauro received his PhD from La Sapienza University in Rome, also in Italy. But in the meantime, he has been to quite a few places across the world as a visiting researcher. And so he has also held several fellowships, including a Marie Curie Fellowship from the European Commission. And also, so he's a very active researcher in the general areas of network security and privacy. And also as so he acts as an editor of several journals in this area, and also organized several events. So let me not take much of his time and let him present his keynote talk with a very interesting title of Side and Cover Channels, the Dr. Jekyll and Mr. Hyde of Modern Technologies. So go ahead, Mauro, please take over the screen. Perfect.
Can you hear me?
Yeah, I hear you and I see the slides. Please go ahead.
Very good. Thanks, Dennis, for the introduction, and thanks to all the chairs for organizing this nice workshop. I was also listening to some of the previous talks. So good morning, everybody. Good afternoon, depending whether you are in US, Europe. If you're in Asia, maybe you should be sleeping. Hope this talk will not help you to sleep. I will try to make it crispy and interactive. Of course, if you feel you want to ask any question, please feel free to stop, to interrupt me, and you can also write in the Zoom chat. I will try to pay attention and take a look at the chat if you have questions. So again, this talk will be about side and cover channels. Will not be about adversarial machine learning, even though we are also working on that topic with my research group. But this is more again batch of works we have done around the side and cover channel area. So let's start. So if this was a real, let's say online, not online, but live talk, I could have made a joke. I'm not sure this would have worked because of this Windows version, but I could have asked, okay, I could have made a joke that now my laptop was logged, and then I have to put my password, and then I can ask you, in such a scenario, what could be the risk? I don't know whether somebody want to quickly write on the Skype chat, what could be the risk of logging in into your machine while you're doing a presentation? There are a bunch of videos, of course, online in YouTube, but there are a lot of scenarios where professors, often go to the classroom, they open up their laptop, they log in, and they do their lecture. So nobody is proposing anything. So we'll see what are the threats behind this kind of behavior. So again, all of this talk will be about cover and side channels. So we'll start with a quick introduction about cover and side channel, just to make sure we are on the same page on what we mean by cover and side channels. Then we look into quickly into again some of the results we have on building cover and side channels, also thanks to basically machine learning tools in different aspects. You can see here we have a list of network traffic analysis, energy consumption, device movement, keystroke timing, and acoustic emanation. So from one point of view, you can look at this talk as going through several physical properties that we leverage to build side and cover channel. But on the other side, there is a subset of work we have done, all of them focusing on a very specific topic, which is basically trying to infer the typing, particularly on mobile devices. So what are side and cover channels? So all the effort that researchers and practitioners put in the cybersecurity is about making the access of a machine secure and making the communication secure. So for an adversary, should not be easy to get access inside a given machine device or get access to unencrypted, unclear communication that are exchanged over a channel. But we all know that everything we do practically has a side effect, okay? And of course, also using our fancy devices from regular, let's say, laptop to smartphone and all other devices as a side effect, at least on physical properties. So the side channel means being able to read somehow from a channel which was not intended to be here. So from, let's say, a side effect, even a physical side effect of the behavior of using a computing system, we can somehow read some information. So infer information that may be private information. A slightly different concept is the one of covert channel. In the case of covert channel, the channel is not there by chance, but is there because one or more parties made intentionally a channel which is again covert. So it's not intended to be there. Okay, so who is looking after the security of a system is not expected or will not look into this this type of channel for threats. So the typical example, actually, which is done, let's say, in the books, is the one of two prisoners that have a guard in the middle, so they can exchange messages, but the guard will inspect the messages that they will exchange. So you can imagine that if they will write something bad in clear in the message, the guard will not pass the message to each other, but they could pre-agree that the real message is not the clear text message, might be reading only the first letter of each line of that message. In that case, I mean, the guard might even inspect the message, but if he doesn't know what is the covert channel, what is the channel that the prisoners are using, they will not be able to read the message at all. Okay, so let's start with one of the first things we were looking at, that was network traffic analysis. In this case, we look at the network traffic to build a side channel. So this is a work now dating several years ago, and thanks to the old coders here. So the idea was this. One of the side effects of any, network communication is, of course, that we need to send and receive packets. So we can observe the traffic. This is the assumption that the adversary can observe the traffic, the encrypted traffic. Okay, so we don't have to break into the machine, or we don't have to break any encryption protocol. We just get access to the communication channel, and you can imagine this is all but unusual thing that can happen. Every time you connect to an access point, Starbucks, or any other place in the world where you don't know who exactly is behind an access point, there might be somebody listening or eavesdropping to your traffic. So this is not the first work, of course, doing traffic analysis. There have been other works trying to infer information, like there have been work trying to infer, for example, the SSH command that are being issued on a network communication. So if I ask you what we can look if the traffic is encrypted, what we can what you can understand. Of course, we cannot again decrypt the traffic, but still we would be able to see the packet, incoming and outgoing packets. We can see the length of the packets, again, the direction and the timing. Okay. So our question was, okay, what can be done, or is it possible to look into this traffic and infer what somebody is doing, particularly on a mobile device, which is a very used device, and we connect with the smartphones on all possible kind of networks. So one possible hypothesis could be, one possible attack scenarios could be, imagine the Arab Spring, where people were calling for revolution using anonymous profiling social networks. if somebody was able, let's say telco operator or a government behind telco operator was able to infer from the network traffic the action that somebody is doing, like you see on the left of this slide, of course, you can somehow de-anonymize the anonymous social network profile. This is just an example of specific action on Facebook here, but you can imagine all kind of, let's say, also maybe positive application of this kind of mechanism. So there can be, behavioral profiling that you can use for good, let's say, marketing reason or profiling of users and so on. So the question was exactly this. I mean, is it possible from looking at only encrypted traffic to tell what a user is doing on a mobile device? And the outcome, as you see in this slide, yes, it is possible. And now we'll see exactly what we have done. So basically, we started by the observation that every action we do on our mobile device is basically a set of basic interactions, so touching, swiping, writing some text, and so on. So a bunch of interaction makes a user action, and so each user action generates a set of network flows, so a bunch of packets exchanged between pairs of IP ports and IP ports. So what we have done, basically, we attached a phone to a USB cable to send to the phone commands as if it was operated by a user. And then we had that phone connected to an access point that was in turn connected through the internet through the same machine, also to have a very synchronized timing. So what we have done basically is collected network traces, network traffics based on a set of actions. So here, just as a illustration for we human, just to see how a possible action that we do on a mobile device results in terms of network traffic. Here you can see several network flows which are generated by one single action. And here you can see on the x-axis basically the sequence, the time, if you like. And on the y-axis, you see the total size of incoming and outgoing packets. So all we aim to do basically is to try to categorize actions by a bunch of network flows, and then, of course, try to re-identify action based on unseen or unknown classification. So again, we do traffic preprocessing and user action classification with the training and the testing. In particular, what we do is, first of all, we use the DTW to build clusters. So out of all these possible flows, we group them in clusters. And as we will see, this is, of course, a possible number of clusters is a possible parameter for our solution. And then basically for each action, we have a vector, a binary vector of 0, 1 telling us which clusters are triggered by the flows belonging to this action. And of course, in the test, what we do is just we let, let's say, user do some action. We collect the flows. And then from the flows, we see what are the clusters that are triggered. And then with the random forest, we try to classify this vector based on one of the known action. As I told you before, of course, the number of clusters is a parameter, but I don't think this is particularly interesting for us. The take-home message for this part of the research is that basically, with this mechanism, it's possible to know with a very high accuracy what a user is doing on a mobile device. And by what user is doing, we mean specific actions on specific apps. As you can see here, for example, we have the traditional operation you can do on Facebook, on Twitter, and other popular applications. After this, another thing that we have done, not only assuming we have the traffic and we try to identify the action, We also move toward the identification of specific set of apps that somebody has installed on a mobile device. The techniques that we used is very similar. Also in this case, I mean, you can imagine what are the threats behind this. One possible threat is, of course, profiling users. Another possible threat is consider this as a first phase of any attack. You know, in the first phase, which is the reconnaissance, people usually try to see what is the status of the systems, what is the configuration, what is the set of apps which are installed on a system to know possible vulnerabilities. And here is an example where, for example, an app has been, a radio app has been used in some other work we have done to inject some malicious payload to the RDS functionality. So in this case, again, what we have done is trying to infer what are the set of apps installed on a mobile device. Also in this case, we are considering encrypted traffic. And in general, again, it's not easy just by looking at the IP address to know what are the apps installed. Because very often you might have not just proxy in the middle, but as you might know, a lot of popular applications, even from, let's say, Google or Facebook ones, they use services like Akamai, or even if you have an IP address that you can say, okay, is a Google IP address, then you don't know which app by Google is being used. So basically the point is that we have to use again encrypted traffic, not relying on IP. In this case, we came up with several methodologies, multi-class binary classification, look at one specific app, and so on. But the take-home message also here is that looking at the performances, also in this case, we have SBC and random forest. We have quite high performances, and also we compared our solution with other state-of-the-art solution, but those other solutions, I mean, the comparison is a bit unfair because the other solutions are more looking at profiling websites. It's not some solution, are not solution focused on profiling apps. And last but not least, of course, we can also use a given probability to increase the accuracy. So as you know, I mean, the classifier will tell us basically what is likely to be the app behind some flaws, and what is the probability of prediction. If we put a cutoff of this probability, let's say quite high, and we expect a very good probability, so it means the mistake will be lower. But on the other side, the classification mechanism will need basically more flows before being able to run a classification. In this case, of course, as you can expect, I mean, the accuracy can also increase. Another side channel is the one of energy consumption. I will try to be very brief here. So what we have done is looking at the energy consumption while we use, in this case, was a laptop. Okay. So the idea is that basically we want to identify a combination of laptop, I mean, a very specific laptop of a user. So it comes with a set of application installed, of course, starting from the operating system. And this, of course, goes together with the users that use them. So the setting here was, and the data collection, I mean, this was a bit preliminary study that we have done some years ago, was to try to profile some volunteers that we can also call PhD students. So we assume we have 7 users, authorized users, and plus we have a class of unauthorized users. In this case, we were 20 also volunteers, master students. Of course, they all were aware of the fact that we were profiling the traffic and so on. And again, here the target was given some pattern of energy consumption, trying to tell whether we were able to identify one of these 7 user, or to tell that the user that we were observing was outside the authorized set. So this was the experimental setting. We used a device which was actually quite old. It was already some years ago, but even the device was even older. Was a sampling rate on 1 Hertz. So you can find much better. But even with those, let's say, very rough experiment, this is an example of observation. These are the results. And basically, even though being this very preliminary, I would say that this is extremely promising and seems that somehow it is doable to profile users. So as you can see, in particular with the random forest, we have an F measure of some 85%. So in this case, this was specifically a side channel, because we as user, of course, need electricity to run our fancy devices. And so as a side channel, we consume electricity. And somebody with all this smart building and so on, it might actually get access to wall socket energy consumption. Another case is the one of building a cover channel. In this case, the attack scenario is basically the one that, I mean, now with COVID, we are less exposed, but otherwise, I think we all go through airports. We all need, of course, to recharge our smartphones. And then the idea is that the adversary might get access to the energy consumption of the device. This is doable in many scenarios. You can imagine when you go through airports, you're always in need of charge, and then you plug your USB, or last but not least, we all probably use power banks, and you might ask, okay, what is inside the power bank? Okay, our, I mean, demo and our experiment was related to this. Okay, let's imagine we are malicious and we want to build something bad inside a power bank and try to steal information. So what we have done is actually this. So we have an app which is colluding with the adversary, but the app doesn't ask any permission, okay? So basically no internet, no Bluetooth, nothing. But you have this app installed on your mobile device, and the app, let's say, has access to your pictures or your contacts. As soon as you go to the airport or you plug your power bank through the USB, this app starts basically encoding the information it has access to in some specific burst of energy consumption of up and down. Long story short, I mean, this is all we know about 0, 1 and how they are encoding. Who is providing you energy, which is basically the power bank or the power station at the airport can observe the peak of energy consumption, and by this you can reconstruct what the user, I mean, the private information inside the mobile device. I mean, to show the feasibility and the size of this thing, we actually built a prototype with Arduino Uno and some other extensions. Last but not least, I want to talk about the device movement. In this case, again, the side channel is on the movement of the mobile device. So we all, and of course, keep in the hand our smartphone while we use them. And of course, for example, when we type, we move slightly our mobile device. So you might know that I mean the keystroke timing is a well-known authentication mechanism. So first here, what we did is we looked at the movement sensors as a side channel for user authentication, and here the results were good but not that good. As you might know, again, the keystroke timing has to do with basically measuring the time between one key press and the other key press, measuring the time also the holding time for each character. There are a lot of, let's say, features that you can get, and from this you can do inference. So in this case, augmenting the keystroke timing with the information that you can collect with the movement sensors can only slightly increase the performances. actually, yes, it can even get worse with the equal error rate. But what we found out that if you, let's say, put this authentication mechanism against a statistical attack where you just don't use zero effort, but you try to learn from a population of users, and then you try to attack the system, then in this case, using the sensors rather than the traditional keystroke timing has much better performances, and in some cases, even using only the sensors is even better than using sensors and keystroke timing. Again, this is the joke, let's say, I used at the beginning of the presentation. What can be the threat here? Still, there are no possible proposal in the Zoom chat. So let's see what could be the threat if somebody give a talk and type the password in the login while the beamer is on. So what could happen? Somebody, people, of course, can say, oh, we can guess the length of the password, which definitely is already a threat. But more, what we looked at is the timing. Okay, so of course, even if you don't know what are the actual characters I'm typing, you still see the timing I use from one key press to the other key press. Okay, so our question was, is it possible to infer anything about the password or any text that the person is typing only by knowing the timing? And of course, if this is doable, there might be also another chance that might be interesting to look at, which is the ATM pin. Now, again, here the scenario is that we can learn from a population of users, and basically we can ask people to type something, to type some password on the keyboard, and observe the timing between key press, and then we have a victim that we can observe. So in this case, if we have a machine classifier that is learning on a population, and then we input the timing of a given victim, then this machine can tell, okay, look, based on what I learned, and maybe the password is whatever, password out of view, and so on. I mean, to assess this, I mean, the performances of this attack, what we have done is we compared ourselves not with a, agnostic adversary that doesn't know anything, but we compared ourselves with an adversary that knows the frequency of the distribution, at least on a popular leak of database of password. As you might know, there have been over time a lot of leaks. I mean, if you're curious, you can look, have been pwned or those other websites to know whether your email or your password has been leaked in the past. But based on these databases, we know, for example, the most frequent password is password. The second most frequent is I love you, and so on. So if you have to do an attack against some password for a user for which you know absolutely nothing, maybe it might be smart to go through the most popular password first. So we compared our attack against this a bit smart adversary. In this case, we picked 4 passwords. And for example, the randomly chosen are William 1 and some other password. William 1 is one of the weakest because in terms of frequency is in position 187. So probably if you have to attack this password, you better go with with the order of frequency of the password rather than our attack. In fact, this is the outcome of our attack compared to the baseline, which is this, let's say, adversary that just scroll the password by frequency. And of course, for 123 Brian and William 1, which are quite popular passwords, you better use the baseline, okay? But if your victim that you are going to attack use a reasonable password, a bit better than William 1, like GLEAD02, which doesn't sound that much stronger even. In that case, as you can see, the improvement is significant if you have to run a brute force attack. Okay, here we have some other numbers. We try to move this attack also to the PIN, basically with the same methodology. The outcome were not very good. Particularly, you know, I mean, if you want seriously to steal money from an ATM, you need to guess the PIN within 3 attempts, which is not what this graph is showing. So we're trying to improve our work, somehow making it easier, somehow making it more difficult. From one point of view, we don't have the timing, but so in this case, we assume the attacker cannot observe anything on the screen, but can, for example, stand behind you, simulating that he's chatting with somebody while he's recording a video. From this video, of course, he has the audio, and from the audio, he can extract with some error the timing. Plus, we assume the attacker can have a thermal camera, which is I mean, $200 stuff you can plug actually on your mobile device, and has access to the pins that I mean, to the digits that the victim pressed. So in this case, again, long story short is that within 3 attempts, we can actually guess some 40% of the pins. So this is a bit more interesting. And if you look at how pins are assigned, I mean, depends on banks or Europe, US. They can be either chosen by users or automatically assigned by banks. In both cases, all pins are not created equal. And particularly, there are some pins which are particularly unlucky, like 1220, which doesn't sound like much stronger than, much weaker than 1212. They are actually, at least against this attack, very different. Last thing I'm going to talk about, and maybe I will do by showing you a video. This attack again was presented in HSCCS and then Black Hat USA 2017, and then we published also on transaction dependable secure computing. What we have done here is assuming a scenario, I mean, similar to actually this one, where you are having a Skype call with somebody and somebody else is typing on his own keyboard. This is quite, let's say, unusual in a keynote, in a talk, because usually all other people are muted, but you might have experienced that during a Skype call for work, for discussing some research work, as we often do. Sometimes people, I mean, just leave the microphone unmuted, and sometimes people start taking notes or maybe doing some other business outside the call. And actually, in exactly this setting, we came up with the idea for this work. We started with a joke during a conf call with some of the authors of this work. We were discussing something completely different. Somebody was typing, and then joking, we say, "Oh, please pay attention." "Oh, no, but I was taking notes." And then somebody was questioning, "Oh, maybe from the audio, we can reconstruct what you're typing and know that actually you were not taking notes, but maybe, I mean, chatting on Facebook somewhere else." And basically, long story short, we actually did this. We have done this work, we published, and after the discussion, the presentation of this work at HSCCS, I got a phone call by a journalist from Forbes asking whether we could set up an interview, and so we did. But before closing the call, this journalist told me, "Okay, professor, but when we have the call, I would like to actually try myself and have you telling me what you're typing, what I'm typing." So I will maybe show you directly the video that we have done with him. It should be this one.
If I start with maybe a sentence from 1984?
Yeah, whenever you're ready.
Okay. Moment of truth.
So I got 2 letters space, 3 letters space, 3 letters space. So let's try that middle word. Okay, so maybe that word was himself.
So the first thing we do is
so the last one,
split the words.
the word is brother.
You probably heard that the space.
Now that I know we're talking about the book, and I know the book, and I know that this word is brother.
Yeah.
Well, I can see that before this brother there are 3 letters. 3 letters I can see a B, and then there's a G. So maybe it is bigger, you know.
Yeah.
Those 2 letters between himself and lover. Let's say it's lover. I'd say it's he.
Yeah, that's right. Yeah.
Now I guess it's game over because I can tell you I'm running the attack and actually googling the book part. So it's up to you to trust me.
And the second challenge was a single word which could be a password.
1, 2, 3, 4, 5, 6, 7. Well, in brain.
Yeah, that's the right word.
Okay.
And this challenge becomes very tough. You put up loud music on the smartphone, go to the laptop.
Did you get that?
Not at all.
In this case, of course, we cannot recognize, but I can imagine that if you are doing the Skype call with somebody
that's definitely the
that
most
will put up loud music will not be
there are at least some private information or even bank accounts or this kind of high privileged information and data, but in some commercial environment or in other environment, even knowing content of messages might be very valuable.
Okay, with this, I would stop the talk here in the interest of time, also to take some questions. I can still use my slide.
Yeah, thanks, Mauro, for the very interesting talk. Okay, so any questions? Let me also check the. Okay, so let me ask one question. So for this energy consumption side channel attack, so it's quite interesting. So I've been actually working on this smart meter privacy. So it's a different level of kind of energy consumption. But so I was wondering here, for example, for the laptop case. So you're assuming that the laptop is connected to the outlet, you know, the charger, and the battery is full, right? So that's kind of the assumption, basically, whatever the energy is consumed is coming from the plug directly.
Yeah.
So if so if somehow we are using from the battery, like charging through the battery, you know, like so that would cover, right?
I mean, there are periods where basically when the battery is fully charged, it depends on the laptop and the point of charge of the battery, but basically you can observe the actual consumption.
I see. So basically, yeah. So I was kind of curious about that. That if the battery is not full, so where does exactly the energy come from? So can you still kind of understand how much of that is energy is charging the battery, how much of it is going through the app? But I'm guessing that your experiments were for a full charged battery, and that the energy is coming. Yeah.
Yes.
And yeah.
We have a similar problem on the covert channel on the smartphone, because there are points of the batteries where the energy is directly taken from the plug, let's say.
Mm-hmm. Okay, and also I have another question about with this kind of timing the channel for the password or whatever typing. So you compared with this kind of let's say brute force attack with some prior distribution based on the frequency.
Yeah.
So did you try combining that? So basically use that as a prior and then actually improve based on the frequency rather than just doing either of the two?
Yeah, sure. That definitely let's say the ensemble solution would be that one. I would get a password then check whether it's present, let's say, in the first whatever number of positions. If it's there, then probably you just go and try by check. So I would do first, I try by frequency up to a given point, and then give up a switch to our solution. That would be the combination that you could use in practice.
But I guess you can even use that prior kind of to understand, because it's sort of like you're having this kind of like time series of data, and after every entry you can actually kind of update your prior, like to kind of change the rank order instead of doing like kind of a falling back kind of after using your scheme and then checking the frequency. Instead, actually, so you have a prior over the kind of over all possible passwords, and after every entry of the keystroke you can actually update that distribution. And eventually, like, probably like computation, it might be.
I see what you mean. We didn't think at all. We didn't work on this. So we only compared, let's say, the basic building block with a let's say naive or a bit smart approach, alternative approach. The best you can do without our attack. Let's say. In that case, an idea could be to use that and the other one. But I see what you're proposing is to blend them together.
Yeah.
To try to get some information from the machine learning part, and then maybe fall back to check some popular password and back and forth. That might be nice to to work on.
Okay. Yeah. Thanks a lot.
Thank you.
Any other questions?
I have a question. Yeah, I have a question which is basically a follow-up to the first question. I want to know if the charging work can be extended to wireless charging, and if so, what kind of challenges would you expect?
That's exactly the same question we asked ourselves. We wanted to do that, but we didn't do. I believe it should be doable, but again, we didn't do any even preliminary test. But there should be not much different in terms of battery behavior. Of course, there might be, different practical challenges. This might be definitely interesting for phones that has these capabilities.
Thank you.
Thank you.
Okay, I have a question. So first, thank you for your interesting talk on the side channel. So my question is there the general architecture can merge all the technical, for example, the network traffic or device-based or keystroke or sensor-based? So there is some general architecture to merge all the technique together for the side channel. The second question is that is there enough data set? So is it the better to use some deep learning model to improve the performance for the detection or classification, like the to guess that gesture or like this? Thank you.
So I didn't hear very well. So I guess the first question was whether we have a general architecture for the several attacks, right?
Yeah, is there the uniform or general architecture for the different technique? I think you introduced a different technique as the side channel, right?
No, it's not a general architecture because it's very domain dependent. And also, when you have to do with the audio, you have to do some preprocessing, of course, which is specific to the domain. There are some, common, approaches that you can use, like, imagine whatever statistical attacks, or imagine, let's say, the non-zero knowledge of an adversary, like in this example of the password. But there is nothing that. I think it's very hard to do something which would be generalized to different attacks. And the second question was?
Yeah, second question is that I check out you use the traditional machine learning for the detection, for the classification. Do you consider deep learning model can improve that performance on larger data set?
For these attacks I presented here, I don't think we have moved on with any deep learning, but I mean, there are other attacks, of course, you can, in general, I expect you can improve. I mean, the core here was to show, I mean, somehow the feasibility, not to, let's say, improve the performances from whatever, 80 to 85. But I believe, of course, you can improve performances by tuning, I mean, deep learning techniques, tuning the parameters and so on.
Last question, quick question. So, so we know based on a sensor-based set channel, for example, based on the accelerometer or gyroscope to recognize for some user estimation or other gestures. So do you think to merge different sensors can improve some performance? Yeah, as a set channel, like the acoustic and the sensor together to do this.
Again, I also didn't hear this well. You're asking whether there are sensors that can improve the attacks or can improve the defense?
Use the sensor to improve other set channels, like the acoustic or the traffic.
I mean, definitely, I believe that, I mean, any sensors that we have, I mean, not only on mobile devices, but also on laptops, I mean, in the sensors in the, let's say, generic term or definition of sensors, whatever you can somehow measure is likely to leak some information. The point is whether this information is enough. So what we try to do is to use, I mean, regular sensors which are available on traditional COTS hardware. Okay, so if you can do an attack with a, let's say, a microphone which is embedded on your laptop or the Skype and type, probably you can do that attack which with a, I mean, a very professional microphone put inside your office in a very specific position and so on. And there have been actually even work in the past on this. But the challenge, I think, is or the awareness that we should contribute to raise for users is to show the feasibility or the threats that there are behind the regular hardwares that they anyway use.
Okay, thank you.
Thank you very much.
Any other questions? Okay, so I don't see also on the chat. Let's check again. Yeah, no more questions. Okay, so thank you very much. Thanks, Mara. Very nice talk. Thanks everyone for attending the session. So now we have a, let's say, about 13 minutes break, and we'll continue with the third session of the day. Thank you, everyone.
Thanks.
Good day, everybody. We'll be starting in just a moment here. Okay, so good day, everybody, and welcome to session 3 on adversarial machine learning for wireless. We have 4 really good presentations here. I am one of the session chairs, William Chris Headley, Research Associate Professor at Virginia Tech as part of the Hume Center for National Security and Technology. I will be leading the Q&A and introductions for the first 2 papers, and my colleague Barak here will be doing the second 2. I'll let him quickly introduce himself.
Thank you, Chris. Hello, everyone. Welcome to the 3rd session. I'm Barak Antarsi. I'm an associate professor at the University of Ottawa, and my research interests mainly lie in machine learning for security and privacy and trust. So I hope you enjoy the session.
Thank you very much. Okay, so our first presentation today is called Over-the-Air Membership Inference Attacks as Privacy Threats for Deep Learning-Based Wireless Signal Classifiers. The presenter will be Dr. Kemal Davasligu, and sorry for the phonetic spelling here. I'm sure you can correct me here in a moment. He actually works for IAI, and his research areas are green cellular networks, energy efficient optimization for wireless body networks, and physical layer security and robust key management. So with that, I'll actually hand it over to Kemal here.
Thanks, Chris, for the introduction. Let me share my screen. Can you see my screen?
I sure can.
Great, thank you. All right. Hi everyone. My name is Kemal Davasligu. Today I'm going to be presenting our work on over-the-air membership inference attacks as privacy threats for deep learning-based wireless signal classifiers. This is our joint work with my colleagues from Intelligent Automation, Dr. Yishi and Dr. Johannes Kepler. So before moving on to presenting our slides, I would like to talk a little bit about what possible attacks are possible for against machine learning systems. And then I'm going to talk briefly about membership inference attacks and what are the challenges in wireless, and then we'll jump into our presenting our paper. So machine learning is a very powerful tool, but it comes with several vulnerabilities that it is susceptible to various attacks. Here in this paper, we are seeing a taxonomy of 4 different types of attacks that are often studied in the literature. For example, evasion attacks. The adversary tries to craft samples in order to alter the behavior of a machine learning system by introducing small perturbations. Another important attack against machine learning systems is causative or exploratory attacks, where the data is poisoned. We often see this in crowdsourcing applications. The third one is Trojan or backdoor attacks. This is similar to the causative attacks, but here the poisoning of the samples are done carefully by introducing some triggers in order to be activated in the test time. So here you see a few examples that I quickly did for the SciFi dataset, and these are the little triggers that I introduced in order to fool a classifier. In this talk, we are going to be focusing on the privacy attacks, and there are maybe we can say there are 2 branches of it. membership inference and attribute inference attacks. And specifically today we are going to be talking about membership inference. So this type of an attack is very important because as we see machine learning increasingly used in high stakes applications such as health analytics, pharma, location, finance, personal records, and cybersecurity, the importance of preserving the privacy of your training data becomes more and more important. So in this type of an attack, the goal of the adversary is to infer if a given query was a part of a model's training data or not. That query can come in different shapes. For example, in our work, it is in the shape of a signal, if a given signal is used in the training of a classifier or not. However, other applications include the faces of employees dataset, personal records, finance records of individuals. For example, in cybersecurity, your traffic, network traffic in your infrastructure. These are all important features that you ideally want to preserve in order to preserve the privacy of your data. Compared to the, for example, evasion attack that we discussed before, learning the privacy of the data can open up subsequent attacks which make your system more and more vulnerable. All right, so we talked about overall, adversarial machine learning, but what are the challenges in wireless domain? Wireless domain comes with a lot of challenges. For example, it is open and shared. Adversaries can easily eavesdrop the channel, or furthermore, can even manipulate the channel by jamming or introducing physical obstructions to the signal. Another challenge is that the channel can change over time. Radios can have different mobility, different traffic patterns for different applications. And a recent very interesting case is that technologies share the same spectrum. They might be creating interference. They might need to obey some rules. So that also creates additional challenges. And in certain settings, such as electronic warfare, the spectrum can be jammed by an adversary. Right. So just to give you as a synopsis of our work, we are going to be looking at a novel privacy threat where the adversary launches a membership inference attack and wants to infer if a given signal of interest has been used to train a wireless signal classifier or not. You might be wondering what kind of a privacy is embedded in a waveform or in a signal. This type of an attack can leak information on the waveform, device, or the channel characteristics. These are all embedded in the signal, in the signal's footprint or the fingerprint. Certain possible applications include physical layer user authentication in 5G or IoT applications. As I mentioned previously, the adversary can launch this attack, leak information, and then generate subsequent signals in order to bypass an authentication system. Right? In our slides, we are going to show that the adversary first needs to build a surrogate system, a shadow model, by collecting features over the air, and then needs to monitor the spectrum and see if a user has been granted service from the service provider or not in order to learn the label of each sample. We will show that how this attack can be launched, and we're going to show that leaked information can be used to exploit vulnerabilities of the models. Right. So this is sort of the outline of the talk. We're going to be looking at the main idea. Then we're going to be looking at the wireless problem. We're going to go into more detail about the deep learning classifiers, formulate the problem, and evaluate the performance. Right. Okay, so here you can see that the membership inference attack, as a figure. This problem has been previously studied in computer vision and health analytics. However, it's not understood for the wireless domain yet. Again, the adversary can generate a sample and wants to figure out if this sample was used in the training data or not. This is our system model. We have a service provider that's providing services to authorized users, and there are other users in the spectrum as well. And in the meantime, an adversary is listening to the broadcast channel and listening to the communication between everybody, basically. So the service provider uses a deep learning, we assume that uses a deep learning classifier to authenticate users based on their device and channel properties. And if a user is authorized, service provider accepts the service request and starts serving the user. In the meantime, the adversary hears everything and can build his own surrogate classifier. Here, it's important to note that what the service provider sees and what the adversary sees are not the same. The adversary cannot overhear the same signals unless it is on top of the service provider, which could be the case, but we are not making any assumption on where the adversary is located at. As long as it can hear the authorized user, this is sort of the only assumption that we are making. Right. So let's take a look at the deep learning based classifiers at the service provider and at the adversary. Right. So we consider that there is a deep learning based classifier at the service provider that includes phase shift and that uses the phase shift and receipt power as features. I note that phase shift includes the device and channel effects due to the RF impairments and also the channel between the service provider and the user. And the receipt power is mainly determined by the channel, path loss, or the other shadowing effects. In our simulations, we kept things simple and used QPSK at authorized users and BPSK at other users. We are considering a deep neural network that consists of 5 layers. The input layer uses these 32 features, the phase shift and the receipt power. That is followed by 3 hidden layers of 100 neurons each, and 2 output layers for authorized and non-authorized users. And we are using the cross entropy loss using the ADAM optimizer. Okay. So the adversary uses the same features, the power and the phase shift, and doesn't have to necessarily use the same neural network. The adversary will build a surrogate classifier, and we denote that by C hat. That is not the same as the target classifier. And it doesn't have to be the same as long as it is determining the users correctly as authorized or non-authorized. So let's go into the formulation. Here, the adversary wants to build an optimal inference model. Let's denote that by M, using the samples X and Y hat from some limited representative training data that the adversary is building. For each sample, the adversary wants to predict the label Y hat using his surrogate model and determine if this sample is a member of this training data set or not. A training data set of the original classifier or not, a target classifier or not. So in order to do this, we are going to introduce a few more things. For example, let D denote the training data of the target model, and D bar denote its complement. Right? So the ideal membership inference attack gain for an inference model, M, on sample X to predict a class Y hat is simply the average of 2 expectations of some log terms. Here note that PD of XY hat is the conditional probability that denotes if X and Y, if X and Y hat are in the training data or not, or if it is in the data set, it is PD, and if it is not, it is PD bar. Right? So as you might imagine, this information is not readily available at the adversary. Right? In order to do this, the adversary needs to collect some data. In order to do this, let's assume that there's a representative data set that he listens to over the spectrum and builds gradually. Right? So we are going to be denoting the representative data set at the adversary as DA, and the A bar is going to be its complement. So we can update the previous equation in this slide using this expectation of this data set. So this will be an empirical gain that we can calculate. One thing to emphasize here is that if the training data is exactly the same as a random population from of this system, then this is literally the worst case for an attacker, meaning that if the training data set overlaps with the random population or the generic population, there is almost no information that the adversary can extract. Therefore, in that case, if there is no this difference between the distributions of DA and its complement, the adversary can as well be flipping a coin, because at that point the inference gain can only be up to 50%. So overall, the essence of the membership inference attack is that if you have trained your data on something private, meaning that this is not the same as a general population, this is something unique to your training set, this is embedded in a way in your model. And this is exactly the information that the adversary is trying to extract and learn from your classifier. Right? So we have performed several tests in order to launch this type of an attack. The classifier, although the classifier is trained on QPSK for authorized users and BPSK for other users, QPSK is still used by all your users in the membership inference attack. Initially, we considered a high SNR value of 10 dB and wanted to see if this attack is really possible. Right? We considered 3 cases, and we were very curious about, which features are more important in order to for the success of this attack. For example, in case 1, we used the phase shift and the receipt power, both features. In case 2, we only used the phase information. In case 3, we only used the received power. Right? Here are the confusion matrices of 3 cases. As you can see, as you might also expect, case 1 is the one that has the best, that leaks the most information, because both phase and receipt power information are used in the classifier. It achieves 88% accuracy. Compared with the phase shift versus receipt power, we saw that receipt power actually reveals more information. So power is more important for the success of the membership inference attack, from the attacker's perspective, obviously. So then we were able to say that, okay, at the high SNR value, this attack is successful. But what happens if the SNR is low? This means that if the attacker is farther away from the user, what happens under that case? Sorry. In that case, we were able to see that when the SNR is weaker, around 3 dB, the accuracy drops down to 77%. And here is the confusion matrix. So this shows that the attacker prefers to be closer to the transmitter in order to have a higher accuracy. But it is best for the attacker to use the phase and the magnitude or the receipt power information together instead of selecting either one of them. So overall, we studied the membership inference attack, which posed a novel privacy threat against machine learning-based wireless applications. In this case, the adversary launches this attack in order to understand certain properties of the waveform, and potential applications are user authentication in 5G and IoT systems. We show that when the authorized users have stronger SNRs, the adversary becomes more successful. This goes to 88% accuracy. Compared with the power versus phase shift, we saw that power is more important. And when we have a weaker authorized users, between the channel between the authorized users and the adversary is weaker, the adversary loses its advantage, and the accuracy drops down to 77%. But again, this is still better than blind guessing. As a follow-up to this work, we have a subsequent journal paper that is under review that we actually looked at what we can do as a defense mechanism at the service provider in order to be more robust, more resilient against such attacks. And you can find the current paper on arXiv, but I think also in the on the chat you can also see the papers here again. So that concludes my my presentation. And if you have any questions, feel free. Thank you.
Thank you very much, Kamal. I'm looking, I don't see any questions quite yet, but feel free if you have any questions to either speak up now or message on the Zoom group chat or on the Mattermost. So with that, does anybody have any questions?
Okay, I have a question for you. Yes. Yeah, thank you for this interesting talk. And my concern is there are several questions. First one, how many members for the system? Another one is, did you test for the different modulation for your system?
Yeah, so we considered a diverse system that we took 8,000 different 8,000 different users, half of which are authorized users and other half are not authorized users. So this is to build the classifier at the service provider. The second one is that the attacker, for the attacker to build such a system, we consider that it actually hears 500 authorized and 500 non-authorized users. So we are making an assumption that it is actually a little bit, balanced data set, right? As you also suggested, looking at different modulations, but also looking at imbalanced data sets for this type of an application, and I think are also very important for next steps, because as of many real applications in deep learning, you might end up with an imbalanced data set that you always see, for example, unauthorized users more compared to the authorized users. So at that point, we need to be a little bit more careful in how we train the neural network because of the data imbalance.
Yeah, last question is, from your formulation, so you choose the subset of D. So how to choose that for your simulator?
Exactly. That's a very, very, very important question, and thank you for bringing it up. So what does representative mean is still an open question, even in computer vision domain. In our work, we did it randomly because we really wanted to see the randomness effect. We didn't pass anything through because we want to make sure that the adversary represents a realistic scenario for an adversary, right? So therefore, we consider a random subset of this of the main data set. But the question of what does a representative data of a given set is there are very interesting work that are coming up, mostly in the computer vision domain, like a model extraction kind of an information, or maybe network pruning is another possible solution for that. But we did not look at any certain case because we are primarily concerned about if this attack is feasible, and if it is feasible, what does privacy mean and what kind of information it can leak, rather than how to find a good representative data. So in this case, also, if you look at some random subset of a set, it's actually the worst case for a adversary to have, right? Rather than an adversary smartly looking at certain samples and extracting them.
Thank you.
Does that answer your question?
Yes.
Excellent. Thank you. Thank you for the questions.
Great. So there's a question in the Zoom chat from Sylvia that says, did you normalize the signal magnitudes? And how about higher order statistics? What does it mean for real protocols that use time multiplexed modulations? And then she corrected herself, said, I meant higher order modulation, not statistics.
Yes. I need to check the paper in order to see if we have normalized or not. I believe that we did normalize them. But I do not recall on top of my head if it is normalized with, let's say, like a random normalization. We did not compare it with regards to the high other classical machine learning approaches use higher statistics. That might be actually a very good comparison between an adversary that has a classical machine learning capability versus a deep learning capability.
I actually meant higher order modulations, not statistics, sorry.
Oh, gotcha. Okay, sounds good. That's actually a very good idea. We will take a look at that one to see what happens if the adversary can actually learn more, or if it is actually pose a different question, or like reduces performance. That's a good further step.
Thank you.
Thank you.
Okay, great. I think we might have time for one more quick question if anybody has one. Okay, great. Well, thank you very much, Kamal, and for your great presentation. And we'll move to the next presentation.
Thank you, Chris.
Thank you. Okay, our second presentation is generalized wireless adversarial deep learning. And the presenter, I think this will actually be a video by Dr. Salvatore De Oro. And he will be following up with questions after the presentation. A little background on him. He's an associate research scientist at Northeastern University. Yeah, so why don't we go ahead and get started with the video.
Hi, good afternoon. I'm Francesco. I'm a research scientist in the Department of Electrical and Computer Engineering at Northeastern University. And so today I will present this paper called Generalized Wireless Adversarial Deep Learning. This work has been done in collaboration with my colleagues at Northeastern University and with sponsorship from DARPA. So just to give you a very brief overview of the motivations for this work, we've seen recently a lot of interest in wireless deep learning from both academia and funding agencies. Recently, we've seen a plethora of papers during the last 2 or 3 years in top venues such as Infocom, MobiHawk, and so on problems like modulation recognitions, radio fingerprinting, physical layer learning, and so on. And also, funding agencies such as NSF and DoD are spending a lot of money on these topics, such as, we have seen the ML WINS programs with RTML, and also the DARPA RIF program to which we participated. But at the same time, we haven't seen much interest in adversarial learning issues, which is, however, critical in many technical applications. So what is the target of adversarial machine learning? In traditional machine learning, we have that, the target of the classification process is to, getting some input, going through a classification process and classifying correctly the input. Whereas in adversarial machine learning, we have that an adversary tries to add some adversarial noise to the image, and so that the classifier misclassifies the input as incorrectly. And so the objective overall is to generate mixed classification. And so why is this problem relevant in the context of wireless systems? So for example, I want to mention this example. So for example, let's assume we're transmitting 2 PSK IQ samples, and at the receiver side, we use a modulation classifier to demodulate the incoming waveform. But so if the classifier classifies the modulation correctly, we will have a successful demodulation. But if the modulation is not classified correctly, we will have the modulation errors. At the same time, perhaps even more worrisome, if we're using machine learning model to classify radios, for example, as in radio fingerprinting, we will have that actually an adversarial device can identify itself as a different device, and this is very, very worrisome because this could cause serious security concerns. Okay, so it's a very relevant problem. So why is this problem, particularly in adversarial wireless deep learning, challenging? It's challenging because if you think about what happens in traditional machine learning, you have that you apply directly noise vectors to the input, and you feed that modified input to the image classifier, and you have your adversary example. But in the wireless domain, this is not exactly the case because an adversary not only has to account for the input, which in this case is a waveform, but also the impact of the channel, which is added to the noise and the waveform. And therefore, the problem becomes much more challenging. for the adversary. And so just to give you another very concrete example as to why this is the case. So in this example here, we trained a machine learning model to identify 5 different radios using our own arena testbed at Northeastern University. And so as you can see, we trained this model, and we achieve on the average 60% accuracy, as you can see on the top left portion of the slide. So when we take an adversarial device which does not belong to the set of 5 different to the set of 5 devices, we achieve accuracy of 20%, because it's the model is trained to recognize those 5 radios, and the adversary achieves just 20% fooling rate. But what happens when the adversary tries to replay somehow the waveforms and tries to imitate that particular device? So what happens is that we would expect that by replaying the same waveform, the adversary would achieve an accuracy that is somehow similar to what a legitimate device would achieve. But in this case, we're only able to increase the fooling rate by 10%. Okay, which tells us what? It tells us 2 things. It tells us that AML for wireless is not straightforward. We cannot just simply, replay the waveforms and, doing very straightforward things like these. We need to think more carefully about what the adversary can achieve. At the same time, the adversarial attacks strongly depend on the channel conditions that the adversary is experiencing at that moment in time. And so this tells us that we need a systematic and generalized analysis and evaluation of adversarial machine learning in the wireless domain, which is the topic and the main contribution of this paper. So just to briefly mention related work, we have in the first paper here at the top that where the authors propose to apply operation of the FGM attack to create adversary examples to moderation classification systems. In the second paper here, they propose the usage of a GAN to spoof a targeted device, but the evaluation is missing a real dataset, which we use in our evaluation. In this paper here, Sdegi and others proposed 2 FGM-based algorithms, and they tested the algorithm on the 11-class RadioML dataset. In this paper, instead, we consider the much larger RadioML 2018-01A dataset, which has 24 classes. Okay, so just to provide a brief overview of the main contribution of this paper, we propose 2 adversarial attacks called adversarial wireless jamming, where the adversary tries to jam already existing waveforms to create misclassifications. So for example, we jam device 1 transmission such that the device 1 is classified as device 2. Instead of the second type of attack, which is called adversarial wireless synthesis, the adversary creates fake real RF waveforms in such a way that, for example, transmit QPSK signals, which are instead classified as 64 QAM. Okay, so very, very different types of attacks. So we also propose a generalized wireless adversarial machine learning problem, which encapsulates both of these problems. And we model the attacks with constraints such as bit rate, radiator power, and so on. And these attacks, the great things about this GWAP problem is that it's derived for arbitrary channels, waveforms, and neural networks. We evaluated the proposed attacks on 2 different large-scale datasets, on the 1,000 device dataset of Wi-Fi and ADSB transmissions provided by DARPA, and on a very widespread modulation recognition model by DeepSeek, where we decrease accuracy. And we show that with these attacks, we're able to decrease accuracy up to 3 times with minimum wavelet distortion. Of course, this depends on the channel conditions that we see at that moment, but we'll talk about that later during the experimental evaluation. So the first attack is called adversarial waveform jamming, where again the objective is to generate an adversarial waveform XA that leads the XL waveform. So here on the top you can see a legitimate device transmitting a XL waveform, which goes through the wireless channel, and it's received at ZL by the receiver. At the same time, we have an attacker that generates an XA fee, where fee is the attack strategy, goes through its own wireless channel, generating a waveform ZA that is summed with ZL, producing a received signal Z, which is then classified by the target neural network. Okay, so the challenging thing here is that A has no control over HL, HA, and XL, which definitely makes the problem extremely challenging. And so what is the mathematical formulation of this problem? So the target of this problem, so we designed two different problems, which is the untargeted problem and the targeted problem. So in the untargeted problems, the objective of the attacker is to minimize over the set of all possible attacker strategies, and on the average over the set of all possible slices, which are input waveforms to the classifier. So to minimize the activation probability corresponding to a given class L, which is the legitimate class, and also minimize the activation probability of the attacker because the attacker doesn't want to get caught. Subject to, of course, a bit error rate constraint over the set of all possible slices, and having the normal strategy, the normal signal less than a given quantity Emax. In the targeted attack, we want to maximize over the set of all possible attacks the target, and over the set of all possible sizes, the target class of the classifier, and minimizing both the legitimate class and the adversarial class, okay, with the constraints C1 and C2 defined above. In the adversarial waveform synthesis problem, we want to generate an adversarial waveform that is classified as a targeted class. For example, when we want to spoof a fingerprint. So in this case, we have, again, an attacker generating the transmitted signal, which is received as ZA, which is in this case equal to Z by the receiver. And so in this case, the attacker has no control over HA, which is its own channel between him and the receiver, okay? So in this case, the mathematical formulation is to defining a CT, which is a target class, and in this case, we want to maximize over the set of all possible strategies and classes, over the set of all possible strategies and the slices, the activation probability of the target class, and minimizing its own class subject to the constraints defined before. So we noticed that these problems are pretty similar in target, and therefore we designed this GWAP, generalized wireless adversarial machine learning problem, where we want to, when we formulate this problem in a very general way, where we maximize over the set of all possible attack strategies over the set of all possible slices, WC, FC, ZS, where the problem is subject to a set of constraints which are very general in nature. Okay, WC takes values which change according to the considered problem. Okay, so to compute the attack strategy, the attacker can compute the gradients using this formula here. And of course, so basically, since the output is a composite of the input, can derive the Jacobian matrix of the input with respect to the attacker strategy and compute the real and imaginary gradients parts using the formula below. You can find all the details in the paper. So what's the problem? The problem is that this problem formulation here is not trivial because the function f, which is the classifier function, is not linear, not complex, and there is no closed form expression. And so it's hard to apply standard optimization techniques to derive the solution. And so what we did was to design gradient-based optimization algorithms for the white box attacks, where we compute an effective attack strategy phi. So basically what we do is to relax the constraints GI with an augmented Lagrangian, because the problem is not linear, and then we find an approximate solution to the GWAP using a variation of the stochastic gradient descent algorithm. So regarding the experimental evaluation, we basically here we show the results for the AWJ untargeted attack over two possible data sets. Again, the modulation classification data set, which is composed by 24 classes, and the RF fingerprinting data set, where we have 500 Wi-Fi and ADS-B data sets. So here, as you can see on the left, we show the accuracy of the target neural network as a function on, as you can see on the x-axis, as a function of the fading level that we experience on the channel. And we compute the accuracy as a function of the jamming signal length, okay, which is either 2 or 8, or the jamming power. So we constrain the jamming power, and so this is what the maximum that the attacker can do. Okay, so we notice that on the left graph, you can see that the accuracy of the TNN reaches, in some cases, about 20%. Okay, so it's 3 times less than what is original, which is originally 60%. Okay, which happens, not surprising, when the adversary experiences no fading. Okay, and we also notice that the impact of the jamming power is much more important than the impact of the jamming signal length. Okay, and so we see that the attacker is able to perform this attack, but of course the performance is much better when the fading level is, of course, lower. So moving on to this is still the AWJ targeted attack, and so here we show you the basically here we show the confusion matrix of the classifier. So what do? We chose 20 classes, the bottom 10 classes, and the top 10 classes. Okay, so the adversary tries to imitate the bottom 10 classes and the top 10 classes. Okay, so in this case here we see these attacks here were brought under the AWJ attack in low SNR regime for different epsilon values. So as we can see, when the epsilon value is low, we have pretty much a diagonal matrix, which is good for the TNN, is bad for the attacker. But when the epsilon increases to the value of 30, meaning that the adversary has more leeway to disrupt the signal, the matrix is not diagonal anymore, which is bad for the TNN and good for attacker. And so as you can see also in this graph here, in this histogram, you can see that the accuracy of the TNN decreases by half as we increase the epsilon value. Here we show the results for the AWS attack under different fading regimes and as a function of the number of taps. And so, as you can see here, the main diagonal is very close to 0, which means the attacker can successfully hide its own feature. And so, when we have a no fading regime, the row classes, okay, can effectively imitate a large set of target classes. Okay, and so what happens when we are considering the reader fingerprinting data set? So we notice that, first of all, the increased number of FIR taps increases the fooling rate. But we also see that in this case, the bottom 10 classes, which are the classes that are worst from the beginning, from a classification standpoint, are the ones that the attacker is not able to imitate. While the top 10 classes, from 11 to 20, they can be imitated with high probability, which means that if the classifier is able on its own to classify these devices, for the adversary, it's easier to imitate them. And so in this case here, we see that there is a problem. We see that the attacker is not able, in these cases here, which I marked in the slide, they're not able to probably imitate some classes. For example, in this case, the class, of course, the class is between 1 and 10. But also these two classes here, they have problems. Why? Because here we are assuming a particular set of taps, m equal to 4, and a given epsilon equal to 0.5. But however, we cannot find a unique setup of epsilon m that will be able to work for all classes, both rogue and untargeted. Okay, and so this tells us that we need to find different parameters for each class that we're trying to imitate. And so if we change, for example, here the number of taps, we see that in this case, we're able to increase the fooling rate to a significant extent. In this case, 97% and 88%, just by changing the parameters that the adversary can change. So I also wanted to plot here the modification that actually the adversary imposes on the waveform. As you can see, in this case here we have the ADSB dataset. The phase doesn't change significantly because it's an on and off keying scheme, and therefore this is good because it's not disrupting the signal, it's just changing the amplitude. Okay, so the features that the adversary goes and attacks are related only to the amplitude. Okay, which is good, which basically does not disrupt the signal too much. So to conclude, basically we demonstrated the wireless adversarial attacks are feasible, but they're not very successful when the SNR is low. Obviously, there is no unique configuration to attack the classifier. Different classes can have different features. And the attacks must recreate these features in order to be successful. And it's very hard to target classes that are already misclassified by the TNN. So the adversary cannot do magic. TNN, because the TNN is already confused, it's not easy to replicate features that TNN hasn't learned in the first place. So this concludes the presentation. If you have questions, I'll be happy to answer. And you can find at this address the preprint of the extended version of the paper. Thank you.
Great. Thank you very much. So Salvatore is here to answer some questions. I'll start with there's 2 questions on the Zoom chat that we'll start with, and then I'll open it up. The first one is the 1,000 device data set available now?
Hi everyone. This data set unfortunately is not available to people outside the DARPA RIC Mills project. The problem here is that due to contractual issues with DARPA, the data has been available only to some performers, and this data set probably even for the performers, because the project is now over, will be deleted. So unless DARPA changes that, it's going to be hard to share this data set, which is like a big loss for the community, because it's probably the biggest data set for RF fingerprinting out there.
Great, thank you very much. And then the second question on Zoom is, what is the difference between AWS and modulation obfuscation? Both try to make, say, QPSK look like 64 QAM.
Yeah, so here the AWS is intended to create IQ samples that are synthesized, so that they are not really IQ samples that are generated from, for example, a QPSK modulation, but they just look like a QPSK. In this case, if you want to look like something to be a 64 QAM, you just need to create IQ samples that the classifier recollects as 64 QAM. It doesn't mean that you need to transmit something of one nature and you make it look like something else. You can transmit something that makes no sense, for example, even for the receiver, but it still gets recognized as a one specific modulation. By leveraging the output of the CNN, which is pretty much something that goes from 0 to 1, and there will be one class that will be classified as the winning class. So yeah, that's the biggest difference. That here we are not transmitting one waveform and trying to look like something else. It's just we are transmitting like the actual target class.
I have a question. I would first like to suggest that you correct the references in your paper, because we have prior work on this, my company and myself actually, about 4 to 5 references that tackle many of the topics you approach here, and also Dennis Gundo's on the constraint, BR constraint adversarial attacks. So yeah, I think it should be corrected. But also I'm interested in what is the sampling rate of your IQ bursts that you're using in the case of RF signature detection versus the DeepSig data set that you're using.
Yeah, so yeah, just so first respect to the first thing about the reference, just like you can drop me an email or write in the chat like with the list of, and then because this is just like a small size paper that has to fit in a few pages, but there is going to be the extension one, and we'll be glad to add that there. So for the sampling side, for the sampling rate in the DARPA dataset, which has in this case 1,000 devices. The sampling rate is, there are 2 different sampling rates. One is 200 megasamples per second and 20 megasamples per second. Because in one case, DARPA used a spectrum analyzer, which has a very large resolution, just a very fine-grained resolution, while sometimes they use like USRPs, software-defined radios. Those have like a very small sampling rate. So the signals are diverse, and sometimes for the same class, you get both sampling rates. To overcome the problem of just feeding the same input to the neural network, what we did is we used like a sliding window of input. So we only extracted 1,024 or 288 IQ samples at a time, just to overcome the problem of different sampling schemes and a different number of IQ samples. Because we don't feed the all IQ sample sequence.
Yeah, but I wanted just to draw the attention to different sampling rates. Do you know what is the sampling rates of the DeepSeek data set that you use for this paper?
Yeah, it's for the sampling rate, I don't know exactly the sampling rate, but I know that there are 1,024 IQ samples for each example.
Yeah,
and that's what we
no,
feed.
I'm not asking about the length of the burst, which is 1024, 256, whatever. It's just the sampling rate because it does affect the actual attack because it represents the waveform more better or more accurately or not.
Yeah, so we don't change that. So we just modify the waveform we attack. So we generate the attack that, for example, in the jamming case, we generate a very few IQ samples and we keep transmitting them for a long time. So we cover like a large portion of the waveform in the DeepSeek ML in the DeepSeek dataset. So we don't really change that. And the jammer only generates a small amount of IQ samples that is replicated. It's one of the parameters of the problem. You can make it longer or larger or shorter. Yeah, but that's definitely one of the things that we investigated, that the sampling frequency is going to definitely impact, and it already impact, the accuracy of the classifier.
Thank you.
Well,
great. So I think we have time for one more question. Chase, you mentioned you had a question.
Salvador, I know you're gathering features from the RF channel itself, and do you also get features from the subsequent upper layers from a logical standpoint? Do those layers enter into features that tell you that the digital data is properly formatted or it has the appropriate CRCs, etc.?
So for the dataset we have, those are just plain IQ samples. And the only higher level thing that they contain is the MAC address that is translated into IQ samples. And we basically remove that part because we don't want the network to learn the MAC address. We just look at the bit error rate in terms of, and not in the specific version of the paper, but in the extended one. In terms of bits, but no, we don't look at the preamble or the CRC or the MAC address and all that information, which is definitely something very interesting to look at. It's a little bit more complicated because you need to create packages rather than small IQ sequences, but it's indeed something that we want to, that we would like to investigate. So the main problem is that the feature that we feed to the classifier is a very short IQ sequence. And that's what we consider. So we don't feed the whole packet. So when we randomize, for example, to test and train the network, we don't really look at the whole packet as it is, but we just slice it and we randomly pick a portion of it. And that might not contain any practically usable information from a higher level point of view. But that's indeed something you're saying.
Yeah, I realize that. And you know, from a SIGINT perspective, that's fine. But as if I was defending against adversarial attacks, I would definitely be using the upper level data, the higher protocol data, and it would basically point that out very quickly.
Yeah.
Although it might although your attack might mess with spectrum allocation algorithms.
Yeah, of course.
Thanks.
Thank you.
Great. Well, I think we're out of time here. Thank you, Salvatore, for answering the questions and giving a great presentation. I will pass it over to Barak for the next two papers. Thank you very much.
Thank you very much, Chris. So we have two more papers in this session, and we'll proceed with the third paper. And the paper is titled Adversarial Machine Learning-Based Partial Model Attack in IoT. And the paper is a collaborative work between University of South Florida, Intelligent Automation, and University of Miami. And it's going to be presented by Jimmy Liu, who is a third-year PhD student at the University of South Florida. So Jimmy, please go ahead. You can share your screen.
Hello?
Yes, we can hear you.
Oh, okay, okay.
Please go ahead. Thanks.
Okay. Okay. Thank you for the introduction. And I'm Zhenping Luo. You can also call me Jimmy, and I'm a third-year PhD student at the USF. And my presentation about topic today is about the adversarial machine learning-based partial model attack in IoT systems. As the IoT systems has been become more and more popular in nowadays daily life, the vulnerabilities in the IoT systems are also become an emergent problem in the research community. So at the beginning, I want to give you an impression about the generalized layers of the IoT systems. Usually, an IoT system can be like grouped into the 3 layers. The first layer, or the bottom layer, is the IoT themes layer, which is consists of by all kinds of sensors, actuators, or like that. We call them as IoT device sensing devices. And the second layer is the IoT network layer. Usually, it is consists of all kinds of computation, like the fork. We name it as the fork computing or the edge computing usually happen in this kind of network layer. And the network infrastructure includes such as the wireless sensor network is also kind of can be integrated into the IoT network systems. And the upper layer is the IoT cloud and application layer, which consists of all kinds of the visualization tools and representation tools, or it is more like user-friend oriented tools and analytics. So in our paper, we focused on the bottom layer and the second layer, which is the IoT data fusion problem in the IoT systems. We can give a simplified sensing and decision model of the IoT systems as shown in this figure. In a general scenario, there are many kinds of IoT devices will be deployed in the real world environments, and especially in a wireless sensor network scenario, multiple devices they will be deployed, and they will connect information from the environment and then report to a fusion center, and the fusion center will process it, or either be classification or do the regression or the aggregation like that operations, and then report the results to the upper layer. Here we denote it as the IoT cloud, which is more is like a larger data fusion center that can be processed and present the results to the user. So the motivation of our paper is that in this kind of data fusion process in the IoT systems, the sensing devices that deployed in the real world environments, they can be prone to all kinds of failures, like physical failures or other, they can be impacted by the environmental factors. And the second aspect is that malicious attackers, they might control some devices. We will say it's not easy to compromise all of the devices, but it can be for a malicious attacker. They can in the scenarios that in some scenarios they can compromise part of the sensing devices. And the third aspect is that especially in the wireless sensor networks, that most of the information are transferred over wireless channels, and so this kind of transformation, the information transfer between the IoT devices and the IoT fusion centers, they can be this kind of information exchange channel might be poisoned or attacked. And the fourth aspect is that many of the fusion or the aggregation decisions in IoT systems and many other fusion centers, they are based on machine learning algorithms, which this kind of machine learning can be taken advantage of by the attackers. As we can see from nowadays the machine learning community, that there are the machine learning algorithms itself can pose a lot of problems for the attacker to take advantage of. So we give the simplified attack model in this kind of decision fusion center in IoT systems. We assume that the attacker can knows the reports of manipulated devices please pay attention that here what we say the manipulated devices is only a small part of the devices. What we consider here today is we want to know where if we only consider a small part of the devices are compromised or taken advantage of by the malicious attacker, can the attacker launch a successful attack towards the IoT decision fusion center? Intuitively, we can know that when the attacker can manipulate a large part of the devices, it's very easy to attack the fusion center to flip the decision output. But what we consider here is that when the number of controlled devices is only a small part, how can the malicious attacker take advantage of the all of those vulnerabilities we have mentioned earlier and launch a successful attack? So we assume that the attacker only knows the reports of manipulated devices and the decision outputs of the IoT fusion center. So the attacker will know the decision output and the input of the manipulated devices. So here we give we use the machine learning and propose a partial model attack. In this framework, we have the manipulated IoT devices will report their sensing results to the attack model, which is also a machine learning model that we will learn based on the outputs of the IoT fusion center and the manipulated inputs of the manipulated IoT devices. And from the IoT fusion center perspective, the input will come from two parts. The first part is the normal IoT devices, which are not controlled by the malicious attacker, and the other port is come from the attack model, which will generate the manipulated sensing reports and input to the IoT fusion center. We think this is kind of a reasonable attack model that in real world the attacker can do have the possibility to know the decision outputs from the IoT fusion center, but please make sure that we want to make it reasonable that when the malicious attacker only controls a small part of the IoT devices, there's no sure thing to launch a successful attack towards the fusion center. So it is more like an probabilistic way, or we can say that it has a higher possibility to launch a successful attack. And in our work, we want to maximize this kind of attack possibility. So so in order to maximize this kind of successful probability, the attacker has to take advantage of the vulnerabilities we have stated earlier. So for an attacker, it does not launch their attack at every time slot. We denote each decision for the IoT fusion center as one time slot. So in real world, the IoT fusion center will will have a huge amount of time slots, and then each time slot is a decision, and the attack model or the malicious attacker, it will not launch the attack at every time slot in order to maximize its attack utility. Because if the malicious attacker launch the attack every time slot and it fails many of the time, then the Fusion Center can easily detect the malicious attackers that might present in this kind of decision process. So the smart strategy for the malicious attacker is to detect the vulnerabilities in the system, and then when the vulnerabilities are detected, and then it will launch the attack. So how to detect these kind of vulnerability is the core problem in our framework. As we know that in convolution neural networks, the output, the second last output of the layer of the CNN layer is the softmax layer. The output value of the softmax layer denoted the confidence value of this learning model towards the decision output. For example, the first in this model we have three class of the output, and the value for each neurons of the softmax layer denotes the confidence value of this learning model towards a specified class. So we can take advantage of this confidence. We denote it as the confidence value. We can take advantage of this confidence value in our framework to measure the vulnerabilities in the Fusion Center. As we know, in the Fusion Center, when the classification model is used in this kind of framework, the attacker model, we can learn a CNN model, and based on the input of the manipulated IoT devices and the output of the IoT Fusion Center. However, in our attack model, the input of the attack model is not the same as the input of the IoT Fusion Center, because the dimensions, they are the input of the attack model is only the manipulated IoT devices. But here we can use this kind of simplified model, the attack model, to measure this kind of confidence in the IoT Fusion Center. When the confidence value of the attack within the attack model is below some kind of threshold, then we can launch an attack and towards the Fusion Center to see if the attack can be successful or not. And then based on the attack results, we can adjust the parameters of our attack model. So here we use numerical experiments to validate our proposed framework. We use 20. We enumerated the real-world IoT decision process using 20 sensing nodes, and each of the nodes, they are designated a mean value and a random mean value and the deviations. And then when we controlled part of the devices, for example, here in this result, we control the 1 IoT devices, and 2 and 3 and 5. We examined all of the 12 scenarios of the manipulated device and examined the attack successful ratio here, which is also known as the hit ratio. When we performed this kind of attack scenarios on the different threshold of the within the attack model, which is like 0.6, 0.75, and 0.9. And the results, we can see that when we controlled like the threshold is 0.7, when we control 8 of the out of 20 devices, the attack successful ratio can reach almost 0.8. And on the other hand, we also can evaluate the difference, the hit ratios on the different confidence thresholds.
Sorry to interrupt you. I really appreciate if you can wrap up in 2 minutes so that we can have 1 or 2 questions.
Okay.
Thank you.
Yeah.
Sorry.
Okay. So here we give the hit ratios on the different confidence thresholds and different number of manipulated devices. As we can see from when we have a larger threshold, confidence value threshold, or a smaller, too smaller confidence value threshold, the hit ratio can be impacted seriously. So here we give the results when the confidence value threshold is around 0.7. The attack successful ratio when controlled only 8 out of 20 devices, it can reach around like 80% of the successful ratio. So we also discussed the potential countermeasures in our paper. The first aspect is like deploying robust anomaly detection mechanisms, and the second aspect is improving privacy protection in each layer of the IoT infrastructure. So I give the conclusions about the paper. In this paper, we introduced a machine learning-based partial model attack in the IoT data fusion processes, and we also present the numerical experimental results to validate our proposed framework, and also the potential countermeasures are discussed. And that's all. Thank you for your time, and open for questions.
Thank you very much, Jimmy, for the interesting talk. Are there any questions for the speaker? Do we have any questions? Okay, I don't hear anything. I may ask one. So in your experiments, you have 20 IoT devices, right?
Mm-hmm.
Okay, so are you planning to scale this out to a larger scenario where you have more IoT devices and a more heterogeneous environment?
Yeah, that's a great question. In our future work, we aim to like enlarge the sensing devices and in a real world scenario. And yeah, as we have said, that's our one of our major future work.
I see. Okay, there's also one question I see here from Xiu Wang, and the question is this poisoning attack for the fusion model?
This as far as I know, that poisoning attack is like the input can be poisoned, but in our attack scenario, that we only poison a small part of the input. So it is a kind of poisoning attack, I would say. But in our paper, I would say it's a very special poisoning attack because we only can poison small part of the input dimensions.
I see. Okay. All right. So we will take other questions if there are any more questions. We'll take other questions offline, and we'll continue with the fourth presentation. Now, thank you very much, Jimmy. You can stop sharing your screen.
Okay. Thank you.
Thank you. Fourth paper is titled Investigating a Spectral Deception Loss Metric for Training Machine Learning-Based Evasion Attacks. And the paper is from Hume Center for National Security and Technology at Virginia Tech. And the paper is going to be presented by Matthew Del Vecchio, He is also with Center for National Security and Technology at Virginia Tech. So Matt, please go ahead. Floor is yours.
Awesome, thank you. Hopefully everybody can hear me, but like he said, my name is Matt Vecchio from the Hume Center at Virginia Tech, and I will be presenting a paper discussing the spectral deception loss that we're proposing for machine learning-based evasion attacks for RFML applications specifically. So really quickly, just an overview of what I'll be talking about. So first, I'm going to present a little bit about the background, previous work, and just sort of set the stage for the environment that we're considering. Then I'll go into the contributions of this paper. And namely, this is the deception, or our contributions are the spectral deception loss. So I'll first talk about why we believe that this is necessary in the context of evasion attacks for RFML. And then I'll go into our approach to how we implemented it for this work, followed by the results and then future working conclusions. So this is the environment that we're considering during this work, a very standard environment for RF communication. So we have a transmitter trying to communicate effectively with a friendly receiver. However, there is a malicious eavesdropper that is listening in and intercepting these communications. And in this scenario, the eavesdropper is classifying the signal using a automatic modulation classifier that deploys a CNN, kind of what's been discussed in previous work during this workshop. And in this work, we're assuming that the signal has already been detected and isolated and that the eavesdropper is just classifying the signal with the AMC. So the goal of the transmitter is to successfully evade not detection, but classification by the eavesdropper. So that in this work, we're doing untargeted classification or untargeted attacks. So as long as it misclassifies as some other signal or some other modulation scheme. And so it's trying to do that while still, and this is important in the context of RF communications, able to maintain a strong communications link with the receiver. So it's fine, it's great if the eavesdropper is fooled, but if the receiver is also fooled and can't make sense of the communication, then the attack is not successful. So some previous work in this field, traditionally gradient-based approaches have been considered, such as the fast gradient sign method or momentum iterative FGSM. And these have been focused on a lot in this field where the loss is calculated based on the success of the signal to evade classification. And with this loss, a gradient is calculated and that's back propagated to help create an adversarial signal. And this has been successful in a variety of different use cases, not only just RFML, but image classification, those sorts of things as well. Unfortunately, when it comes to the context that we're examining this in, the gradient-based approaches fall a little bit short because when trying to maintain that strong communications link, the real only way to do this within this concept is to limit the perturbation size. There's not really a intelligent way that does this more so than just making the perturbation smaller and therefore making the signal closer to the original signal. So with that in mind, one of the previous grad students from our lab, Bryce Flowers, introduced what he called a communications aware attack. And that's what the work in this paper is really built off of. And so what this does is instead of using a gradient-based approach, it uses a separate CNN. In this work, it's called an adversarial mutation network that learns how to make the perturbations itself. So what happens is you take the original signal, send it through this network, and it outputs an adversarial signal to be transmitted. And the way it does this is through the use of very tailored loss functions that get used during the training process. In this work, we're considering previously we were considering three different loss functions, namely the power loss, communications loss, and adversarial loss, which I'll get into the next slide. So the adversarial loss, as the name would kind of indicate, is used to decrease the eavesdropper's classification accuracy. So in this case, it's represented by sort of like a log likelihood-based representation, similar to other machine learning applications. But in this scenario, P represents the confidence that the eavesdropper has that the modulation that it's classifying is the source modulation. If you were trying to do a targeted attack, you could rearrange this to fit that use case as well. Second loss is the communications loss. So this is used to try to decrease the bit error rate of the receiver and therefore improve communications. So in this loss, the BR there is the bit error rate, but unfortunately, due to the fact that this is actually training a network, all of these loss functions have to be differentiable so that they can backpropagate. And unfortunately, given the circumstances that we're considering for this environment, the bit error rate is not differentiable due to the necessity for a hard decision to be made on the symbols. So to get around this, we use what is called the error vector magnitude of these clean symbols and the perturbated symbols. And this sort of acts as like a proxy for the bit error rate, because this is differentiable. So that way a gradient can be calculated and the communication loss can actually be represented during training. And the third and final loss that we used in previous implementations of this attack is the power loss. This essentially, it's similar kind of to what gradient-based approaches do, but it minimizes the power of the perturbation to try to keep the signal to be more similar to the original. So these three sub-losses are then summed together with each other using weight constants. And the reason for these weight constants is that you can actually tailor the network to meet the scenario that you want. So for example, if you care more about adversarial success and evasion, then you would increase the value in this scenario of alpha. Whereas if you care more about successful communications, you would increase beta and so on. So this allows for a better tailored fit to the scenario that you are using it for. So that was the previous work that was done in this field. However, we noticed that in these attacks that have been implemented before, the resulting adversarial signal exhibited significant out-of-band content. So looking at the plot here, the original signal is the very clean, just blue, and this is a PSD plot, so showing the frequency content. The blue is the original signal. And then for two former implementations of this attack, you can see that the perturbation is has significant content in the side outside the main lobe. And this could potentially be a limitation of the attack, because if the eavesdropper realizes that this is happening, they could use pre-processing stages such as a low-pass filter to take out the perturbation. And if significant portions of the perturbation are in the side lobes of the frequency content, then this could potentially make the attack ineffective, which is not something that you would want. So we, to address this problem, are introducing what we are calling a spectral deception loss. And this instead operates in the frequency domain, whereas the previous losses operated in the time domain. And the result of this is that the signal is better to, is more easily able to spoof the frequency characteristics of a normal benign signal. So just going into some of the necessity for why we need this loss. In previous work, there was a little bit of question about whether or not the communications loss and the power loss were both needed. And the reason for this, and you'll be able to see it a little bit more on the next slide, is that these two losses generally trend to push the network in the same direction for the two metrics primarily considered, those metrics being bit error rate and evasion success. So both have the same effect on both of those metrics. So there was a question about whether or not both were necessary. And it wasn't really until looking at the power spectral density plot here that you can see the difference between the two metrics, or the two losses. So in both of these, for the two cases considered here in the figure, both are trained with different networks. One trained with only power loss and one trained with only communications loss. No other losses are used. And you can see that when looking at the perturbation, the communication loss still exhibits significant out-of-band content that could potentially be filtered out, but the power loss is only in-band. And then when looking below, when you add the perturbation to the original signal and inspect that PSD, the power loss is completely, looks very benign, whereas the communications loss still exhibits that side content that, like I said, like we've been saying, could be filtered out. So this is the reason that the power loss was important in the previous design. However, this raises the question about why do we need the spectral deception loss if the power loss is able to force the signal into the shape that we want. And the reason for that, kind of going into it more on this slide, is so previously the two, like I said, pushed the two losses pushed the network towards these convergence of the bit error rate was more like the theoretical value, and the evasion success really just mimics the original classification and accuracy of the eavesdropper. So obviously you need to incorporate the evasion or the adversarial loss into the network during training. And when you do this and combine it with the power loss and communications loss, even though the power loss exhibited strong or good structural content when it was the only loss considered, when combining it with the adversarial loss, it starts to show that side frequency or that spectral characteristics that we saw in previous PSDs, where there is some side content that we don't want, which is why the spectral deception loss was introduced, because we want this loss to be able to still maintain this in-band adversarial signal while successfully evading and communicating with the receiver. So this work is really just meant for a introduction into this aspect of evasion attacks and really just introduce it to the RF community. So what we're proposing is an early stage of what this could be, but there's many ways that this, or many directions that this could go. And so our loss looks to minimize the difference between the fast Fourier transform of the original signal with that of the perturbation. And the reason for this being that if the perturbation is in band, then the resulting adversarial signal should be in band as well. And the way that we determine the difference between the two FFTs, we tried two different methods. So we used two very traditional machine learning based loss functions. So one being mean squared error, which takes the squared difference between 2 points and averages that, and the Huber loss, which is more of a hybrid between mean squared error and mean absolute error L1 loss, where if it's below, if the difference between 2 points is below a certain delta value, in our situation we used a value of 1, then it acts more like mean squared error. But if it's above this, it acts more like mean absolute error. And this is beneficial because it's able to converge better around the minimum, but when it's when there's outliers, it's better able to handle this and be less biased than mean squared error. So we tested out both of these methods within the attack framework that I discussed earlier. And as you can see by the plot on the left that shows the perturbation frequency content, the mean squared error method it did slightly better than the power loss, but really was similar in concept to how that behaved. However, the Huber loss was able to more closely mimic the shape of a traditional signal, which is the expected or the desired outcome that we had of the spectral deception loss. The reason that we believe that this was the case, why Huber did better than MSC, was really just because it's better at handling outliers than MSC, which given the which may be an important thing for frequency consideration when you're comparing different bins of an FFT, which could vary significantly. So then looking at the adversarial signal comparison, so what would actually be transmitted, you can see that the Huber loss methods, and we tried two of them, two different configurations of the constants here, both very well mimic the characteristics and behavior of a normal signal, whereas MSC still does okay and better than some previous methods, but still has some frequency content outside the main lobe. And one important takeaway is that between these two Huber methods that we implemented, one has slightly more prioritization on the spectral deception and one has less. But even when it is less prioritized, the spectral deception loss is still able to force the shape of the signal to be that we want, which is more of a benign signal appearance. So obviously, when you have this type of behavior, there's probably going to be some sort of detriment to other aspects of the attack and communication. In this scenario, the thing that was most hit was the communications. So the upper right plot shows the bit error rate of the seen at the receiver that's receiving this adversarial signals. And the blue line shows the Huber loss or the Huber method that more prioritized spectral deception. And as you can see, it really doesn't do well, and it starts to asymptotically approach about 10 to the -3 and isn't going to really go to 0, it appears, which is not the behavior that you'd want for a traditional communication system. MSC does slightly better, but still not great. However, you can see when you start to prioritize communication more and take away some of the weighting on the spectral deception loss, the bit error rate starts to become a more tolerable value. Obviously, it's still not theoretical. It's never going to be an evasion attack, but this is a much more tolerable range of error. And as we showed in the previous slide, even though that the deception loss is less weighted than it is for some other configurations of the attack, it still was able to maintain that structural shape that we had desired, even if the bit error rate is improved in this scenario. And then the lower right plot shows the evasion success of these. And while the yellow line showing the more desirable attack for communication success does do worse for evasion, it's still a very reasonable level. It never really goes above like 21%. And there is always going to be a trade-off between communications loss or communications evasion and the structural shape. So this is a good approach and a good success for the attack. And like I mentioned, you can use the weights to adjust to whatever attack you would want. So just in conclusion, we saw that the Huber-based spectral deception loss was able to successfully shape the perturbation in the frequency domain like we wanted, so that the resulting adversarial signal appeared more benign. That way it could maybe fool a detector or the eavesdropper if it's pre-processing. So we saw that while this harmed communication reliability, the weights of the network can be, and during training can be changed to establish a better trade-off between communication and the spectral shape. And it seems like even when adjusting to have better communication, the spectral shape does not really take that much of a hit. More of the hit is in the evasion success. Future work should look into more approaches for this deception loss. As I said, this was really just an initial probe into what could be done here. One potential change could be that instead of using the FFT for the loss, you could use the PSD directly, since this is really the metric that we were using for success. So this might have a better impact. Additionally, instead of Huber or MSC, which do more point-to-point based calculations, which might not be really translatable in the frequency domain where you're comparing bins, something like the Fouquet distance might be a better solution and show better success. And then finally, we mentioned having an eavesdropper, like that this would be used for an eavesdropper that has more pre-processing stages like filtering. However, it would be better in future work to actually show the success that this has against such defenses. So with that, I open the floor for questions, either here or in Mattermost. So thank you.
Thank you very much, Matt. Do we have any questions? We have time for just one question because the next session is about to start in 5 minutes almost. So yeah. Please go ahead. Hanif Rahbari has a question.
Yes. Yeah, thank you for the talk. I actually have a question about the approach that you have selected. If I understood it correctly, you want to basically hide the modulation scheme that the transmitter is using from the eavesdropper without impacting the bit error rate performance or the performance in general at the intended receiver. So a few years ago, the notion of modulation obfuscation was proposed in the literature, and that approach had the same goal, hiding the modulation scheme from the eavesdropper without impacting the performance of the signal at the receiver. So I wonder what's the reason for adopting this approach that you have, that has side effects, as you explained, has some challenges, whereas this problem looks like has been solved more or less in the past.
Right. So thank you for your question. So in the past, it was desired that the communication success be maintained, because obviously you want to still be able to communicate with your receiver. But we saw in results that as you start to complicate the scenario, you make it targeted, you do something like that, the required perturbation, like an FGSM, would have to be maybe a ratio of 1-to-1 as far as perturbation power to signal power. And as you start to consider these scenarios, if the perturbation requires more power, the communication is not going to be nearly as good, especially because it's not doing anything directly to help that. You're just sort of trying to limit it. So the reason for this framework was really to try to get a network to learn to perturbate it in a way that was able to do it more directly and explicitly. So in this scenario, it seems based on previous results that it was using the oversampled nature of the network or of the signal to sort of hide the perturbation, which is something that a gradient-based approach wouldn't necessarily learn how to do. And so that's why we expanded this work to try to address the issues with oversampling.
So I think if I may, to just a quick follow-up. So there's a big debate between model-based approaches and machine learning-based approaches. So I guess my question was that when we have some very good solutions, model-based solutions, what's the motivation, what's the justification to use machine learning and any sort of learning to tackle this problem? I understand that we might have limited time for this session, and I can have the discussion offline, but that was basically my question.
It might be a good idea to take that discussion offline or through the chat screen, because the other session is just about to start and we have already overused our time for this session. It will be very unfair for the speakers of the other session and also the chairs of the next session. I apologize for interrupting the discussion, but that's the situation, unfortunately.
That I understand. That's perfectly fine.
Yeah. Okay. Thank you very much. Many thanks to all speakers, all presenters of this session, and also the audience for the discussions and inspiring questions. And also thanks to my co-chair, Chris Hadley. Thank you very much, everyone. So the next session is starting in a few minutes, machine learning for wireless situational awareness. Chris, if you have anything to add, please go ahead.
No, thank you very much, everybody. And I will just say, Hanif, as one of the co-authors, I'm happy to talk offline with you too about the question that you had on the final paper. Thank you.
Well, thank you, everyone. See you in the next session.
Hello? Hello? For some reason, I saw that I'm unmuted, but obviously there was some problem. Okay, so we're starting the session on machine learning for wireless situational awareness. The first talk is deep learning based wiretap coding via mutual information estimation. I see here that the presenter is Rafael Schaffer.
Welcome to my talk, Deep Learning-Based Wiretap Coding via Mutual Information Estimation. My name is Raphael Schäfer. I'm from the Technische Universität Berlin, and this is a joint work with my colleagues RIC Fritzek and Gerhard Wunder from Freie Universität Berlin. This talk is about how to use deep learning or machine learning based techniques to secure communication via a very specific approach of mutual information estimation. If I want to talk about communication, I basically want to start with going back to the origin of Shannon, who first studied the communication problem in a rigorous way. So basically, Shannon, he looked at a very simple communication problem with a transmitter, a receiver, a channel in between, and basically he phrased the question or the problem of communication as that of reproducing at what point either exactly or approximately a message selected at another point. If I want to formalize it more rigorously, then my communication problem, if I'm looking at a very simple point-to-point channel, it looks like follows. So basically we have a transmitter, a sender, who takes a message M, encodes it into a code word XN, which goes over the noisy channel to a receiver who receives a noisy version YN. And based on that observation, he tries to decode the message M. At best, he do it with a small probability of error, so that the decoded message M hat is the same as the message M we have transmitted. If you look at this problem, then basically you may have certain communication constraints, such as an average power constraint. So however, in what way we encode the messages, we are limited by some transmit power P. And in the end, our communication system is specified or qualified by a communication rate R given here, which determines how fast we can transmit over that channel. So how it is done today is that these transmitter and receiver blocks that you see here and here, they are highly complicated and highly non-trivial. There are a lot of specific tasks to be done, and all these tasks are basically decomposed into multiple blocks. And each task is individually designed. This includes, but is not limited to, channel coding or modulation, shaping, synchronization. So there's a lot of engineering work in there to optimize and to design each specific task by itself. And we are basically driven by the question whether or not it is basically possible to learn such good transmitters and receivers. So instead of designing each task individually, we're asking, can we learn the transmitters and receivers at all? And the question or the answer is basically yes. So what you can do is you can use neural networks for encoding and decoding. So basically what you've seen before, the transmitter and the receiver are now replaced by neural networks here and here. And that noise layer within that overall neural network, that represents the noisy channel. So basically, but you have a part that stands for the encoder, and you have a part that stands for the receiver or the decoder. And it has been demonstrated that this approach, which is known as autoencoder, that this is very powerful and basically achieves bit error rates or performance qualities that are close to practical baseline techniques. If you look at this very simple setup, or the first approach of learning an encoder and a decoder, you realize that this noise layer here in between that has to be put in to account for the channel, but this basically requires you that you have to know that channel beforehand. And this might be problematic if it is unknown or if you're not perfectly aware of how the channel exactly looks like. And therefore, we want to resort to another approach, which is basically based on mutual information estimation. Since if you're familiar with a communication problem, you know that the capacity determines the maximum transmission rate, and the capacity of a communication system C is for the very basic point-to-point channel given by this expression here. So the maximum of the mutual information between the input signal X and the output signal Y. And since the capacity, the maximum transmission rate, is determined by this quantity, the mutual information, it may be worth to think about that instead of obtaining the channel itself, it may be sufficient to get the mutual information expression. and based on that, design your encoder and decoder. So our idea is now that we want to approximate the mutual information via these neural networks and use this neural network then to train the encoder instead of using that specific channel. On the good side is that now we only need samples of the channel instead of the channel law itself to optimize the encoder. And intuitively, this might be a good approach that it requires not that many samples as potential other approaches. When I say mutual information estimation, you should be aware that there are a whole bunch of different mutual information estimators out there. The most common one are, for example, MINE or NWJ estimator, NCE, the SMILE estimator, RJA. So there are quite a bunch of different estimators, each with its own advantages and drawbacks. And in this talk, we basically want to resort to the MINE approach, which stands for Mutual Information Neural Estimator, which has been proposed a couple of years ago. So basically, the MINE estimator is given by basically this expression here. And it uses the Donsker-Baratan representation of the Kullback-Leibler divergence to lower bound the mutual information. If you increase your sample size, then this one converges to the true value of the mutual information, which is good. However, since we have a logarithm here outside the expectation, you may end up having a bias in practice, which yields neither a lower nor an upper bound. So you have some advantages. Here's one drawback of this particular estimator. And in the following, we will use this estimator to tackle the problem we are interested in. So how it is then realized or incorporated in the overall setup is the following. So again, we have the transmitter neural network, the receiver part. Here we have that channel, which may be unknown, but basically on the samples of the input X and the output Y, we are trying first to estimate via the MINE estimator the mutual information and use this knowledge here of the mutual information to then learn or train the encoder network. If we're doing this, we realize that this is quite good, since if I'm, for example, comparing the block error rate for an AWGN channel, we see that all these curves here, they are quite close to each other, and basically there's no significant difference between them. So you see that the autoencoder approach with the mutual information estimation approach performs equally well as, for example, a well-known standard 16QAM encoding symbol. And also, if you look at the constellation points that come up if you learn the encoder and decoder in that way, you see quite a nice constellation points here, which kind of resembles what we're used to if you're using 16QAM, for example. So we see that this performs quite well, but what I haven't done so far is I didn't talk about security or secrecy at all. So right now, I was only concerned of a point-to-point channel where I have a transmitter, where I have a receiver, and I want to reliably transmit over the noisy channel. And I wanted to use neural networks to learn the encoder and decoder. So now I'm asking the question, can I kind of extend what I've done so far to incorporate security constraints as well in this setup? So what I'm now interested in is the following setup. Again, I have an encoder or a transmitter, which I now call Alice. I have a receiver, let's say Bob. And as before, I have a message M, which should be encoded into code word X and goes over the channel. Bob receives the noisy version Y and tries to decode the right message. Now, in addition, I'm assuming that I have a bad guy around here, an eavesdropper, who gets an even noisier version of what I've transmitted. And the eavesdropper also tries to get some information about the message I've transmitted. And of course, that we want to prevent. So, with this extension, we now basically have two different goals. First, reliability, of course. The legitimate receiver Bob should still be able to decode the message correctly, so we want to minimize the probability of error. And at the same time, since we have a bad guy around, we want to further minimize the information leakage to the eavesdropper. So we have these two tasks. I know you ask, yourself if this is in principle possible, and you may tend to the answer that yes, this could be possible, since if I'm looking at this particular setup here, I see that the eavesdropper gets a strict noisier version of what the legitimate receiver Bob gets. So the legitimate receiver Bob has a clear advantage about the eavesdropper, which is a better channel in this case. And also this setup, what I call the wiretap channel, has been analyzed or studied from an information theoretic point of view, and the secrecy capacity, which determines the maximum transmission rate, such that Bob can reliably decode the message, and the secrecy criterion is satisfied, meaning that Eve gets no information about what I've transmitted. This maximum transmission rate, the secrecy capacity, has been established and is given basically by this expression. So we see again, here you have some mutual information expressions, IXY, that is the exact expression that I've seen before, which accounts for the legitimate channel from Alice to Bob, X and Y. And now we have a penalty, XYZ, XZ, which can be seen as the channel to the eavesdropper, which accounts for the leakage to the decoder, which we have to prevent. And we see that basically compared to the case without eavesdropper, we have a clear loss or a reduced rate. And this comes from the eavesdropper, and we have to pay a price to keep the eavesdropper ignorant of what we transmitted. And how it is done intuitively, I'm telling you now. So the intuition behind this wiretap coding setup that we've seen can be roughly seen as follows. So let's assume we have some messages. So let's assume we have 4 different messages. Let's assume we have a triangle, a square, a circle, and a rhombus. These are my messages. But now I'm kind of duplicating these messages, let's say 4 times. So we have 4 quadrants, and in each quadrant we have all these messages. So I'm seeing here where the loss in rate comes from, because now basically this is the same message, right? These red dots all corresponds to the circles. So we have basically 4 constellation points which refer to the same message. This is where the loss in rate will come from. But now the idea is that I want to achieve the following, that the legitimate receiver, that Bob can basically decode any constellation point here without problem, and therewith getting the information back, while the eavesdropper is hopefully only able to decode kind of, let's say, these quadrants. Right? So the eavesdropper can only say that, oh, whatever has been transmitted is within this area here. Then the eavesdropper knows as much as he knew before, because in each quadrant here, we have all possible messages available. And this ensures me the security or the secrecy, because then the eavesdropper does not learn which of these messages inside this quadrant I've actually transmitted. Right, so you can say that the goal is that Eve can only distinguish between clusters, while the legitimate receiver can distinguish between every code word. Okay, and this idea I want to carry over to the deep learning based approach that we've seen so far. So instead of simply learning a good encoder, we now say that the encoder should be trained such that the eavesdropper, let's phrase it like this, sees the same distribution for all messages in a cluster. This means we cluster the code word space into equal subgroups, right? That each cluster will contain all possible messages. And with this, we define basically the loss function, which is our target function in the training process, as a weighted sum of 2 quantities now. First, we have the mutual information estimation, mine, of the legitimate link. So basically, to account for the reliability constraints that Bob, the legitimate receiver, can successfully decode the messages, we resort again to the mine approach that I've discussed so far. And in addition to that, to incorporate the secrecy constraint, I'm using a cross-entropy constraint. This one here. Notice that here we have a minus. So it's the other way around. Based on a new artificial input distribution assigning equal probabilities to code words in the clusters. This will kind of enforce that the learning will ensure that at the eavesdropper, all the messages or constellation points within one cluster will have the same probability. Let's do an example. So let's assume I have some messages I want to send. Let's say I want to send 1, 2, 3, 4, and let's say 2 again. So converting this into a one-hot encoding matrix, it may look like this. Now, if I'm forcing this security constraint, this matrix may look like this. And now you see that basically here you have some ambiguities, and here you cannot distinguish anymore between these quantities. If I'm doing this, we see that this approach works very well. For example, you see in this simulation here where we looked at an AWGN channel, we have 32-dimensional code words. And if I'm not doing the security encoding, what I've described, then the symbol error rates of the link from Alice to Bob and the link to Alice to Eve, they look like the blue and orange curve. Of course, the orange curve is worse because Eve has a worse channel than Bob. Now, if I'm applying or incorporating the secure encoding approach that I've discussed, then you see that, of course, you may also lose something at the Bob link, but you see that clearly the eavesdropper link gets really worse and does not show the nice behavior. So you see that there is kind of a security incorporated into this encoding procedure. If you look at the constellation points, then you clearly see that our intuition that we've tried to build up in the beginning becomes visible. So if I'm not enforcing this structured security encoding, the constellation points learned by the mine approach, they look quite regularly. If I'm including this clustering behavior, I clearly see that now my trained encoder ends up with clustered constellation points. And now it exactly resembles the motivation I tried to build in the beginning. In each cluster, you have, let's say, 4 different messages. Here, 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 and here. And now the eavesdropper, he may only be able to identify the clusters, but he may not be able to really, let's say, look into the clusters to determine which exact point of this within this cluster has been sent. This is one example. Here's another one. Also here we see a very regular pattern for the case without secure encoding, and afterwards you see clear clusters of constellation points. This brings me to the end, to my conclusion of this talk. And to summarize what we've done is we looked at the channel coding framework based on autoencoders and mutual information estimation. And we have seen that basically we can learn good transmitters and receivers based on this framework, that they are quite good in the sense that they achieve similar performance as practical baseline techniques. And if I'm even using this mine approach or mutual information estimation approach, I can even circumvent that problem of knowing the channel model. We then added a security communication constraint by enforcing a fake distribution to enforce this specific coset structure. And also we see that this works very well. Of course, there are still quite some work to be done. This is only a first step. For example, you might be interested in extending this further to incorporate or to look into different estimators. I'm only talked about mine, but there are other ones like I said, NWJ, NCE, SMILE, RJA, and others. We only looked at the simple AWGN channel. There are other channel models, relay fading, to be looked at. And if you paid attention, so basically I had a very kind of hybrid loss function composed of a mutual information constraint and a cross entropy constraint. And it would be nice to understand if it is possible to, let's say, to have a pure mutual information loss function. Okay, that's it. Thank you for your attention.
Hello. So the speaker here is still not available to take questions. So we'll possibly move the question part for the end of this session. And do we have the next speaker available?
Yes.
Okay, so we have the next talk is wideband spectral monitoring using deep learning. And I have the speaker here, Horacio Franco. I hope I pronounced it well.
Yes, that's correct.
Okay.
Good. Good afternoon, everybody. I am presenting this work, wideband spectral monitoring using deep learning. This is work with my co-authors, Chris Cobo-Kroenke, Steph Welch, and Martin Glaserena. So the goal of this work was the detection, identification, localization in time and frequency of multiple signals of interest. And all this in a background of RF activity within a very wide range, very wide band of 666 megahertz. And this band could be located anywhere between 0.5 and 6 gigahertz. And this task was part of the spectral awareness task of DARPA program, the Radio Frequency Machine Learning Systems program. So the challenges on this
sorry, I cannot see your slides.
You can't? Oh,
no.
You cannot see the slides. I'm sharing the screen. And how this could be? Let's see. Share screen. Can you see? Can you see now?
No, I cannot. I don't know about the other attendees.
Let me try again. Share. Okay.
Oh, yeah, something is changing now.
Okay. Now, hopefully.
Yeah.
Can you see this? Can you see the?
Yes.
Can you see the screen now?
Yeah.
Okay. Okay. Sorry about that. So the proposed approach was to use a spectrotemporal representation of the wideband radio frequency signal, basically a spectrogram, because it's the only way that we can segregate multiple signals, given that in this ultra wideband of 666 megahertz, there might be many, many signals present. And at a very reasonable resolution where we can restore different signals, this produces a very high dimensionality input. To deal with that, we apply a hierarchical approach. At a lower level, we analyze the spectrogram with a sweeping spectrotemporal window using a deep convolutional neural net to compute local probability estimates about whether the signals are present in local areas. And at a higher level, we use an estimate of bounding boxes for the signals of interest that are hypothesized using a region proposal network. And this region proposal network basically hypothesizes a region, and in this region, we basically aggregate the local probability estimates from the previous network over two-dimensional areas, and that's where we can compute a score which is based on a segment. Okay. So this is a kind of a simple diagram of how our system could be. Basically, here is the front end where we compute this very high dimensional spectrogram that has basically 16,000 points in the frequency domain and 15,000 power spectra along time. So this is a spectrogram that has about 250 million pixels. It's very large as an image to deal with the conventional techniques. And basically what we do is divide this input spectrogram across bands. Every band could be about, or what we call a frame, about 10 megahertz of, between 10 megahertz of bandwidth. And so we would have, with 50% overlap, about 127 columns along the frequency axis. And also, basically, every frame is defined like a 256 by 256 image, in which the multiple spectra are in the time direction, along the time direction, 256 and 256 spectral points. So we use this input, this frame, as an input to a frame probability estimator that computes the probabilities of basically a signal being present in that frame using a ResNet, and that allows to compute the posterior probabilities for every signal in that frame. Then the bounding box estimator uses the posterior probabilities outputting from this network for every position, what we call a posteriogram, and estimates potential bounding boxes. And then a scorer basically computes an aggregation of the posterior probabilities within these bounding boxes for every signal. And that's the generation of a score that we use for detection. And there is a potential refinement if this resolution of 10 megahertz is not good enough. We also have multiple resolutions adding adjacent bins, so we can have different scales to better recognize signals with wider bandwidths. So the wider band is up to 83 megahertz and the narrower 10 megahertz. So here we can see some examples of how this works. So we have here the large wideband spectrogram I was talking before. Here we have a signal which is a drone, and the frame probability estimator generates for a particular for this particular signal this posteriogram, and the bounding box estimator generates potential bounding boxes for signals, and then basically the score computation basically selects the one that has a good score, and the ones that have a bad score are eliminated. And here is compared with the ground truth, and we see the relatively good detection. See, here we have another case for a Wi-Fi. Here is the Wi-Fi present in the spectrogram. Here is a posteriogram for the Wi-Fi, and we see the high probability for the signal, but there is a lot of other activity in the background. And then again, the bounding box estimator and the detector generates this detection, which is coincident with the target. And here we have a case where we have two signals, Wi-Fi and drone. And here we have a high activity for the Wi-Fi. And here is the detection estimation with a bounding box. And similarly, now we see the posteriogram for the class for the drone, and here we see the activity and the bounding box for it. So to train the networks to do this task, and to have this to be robust, we use multi-condition training. Basically, what we want to do is build invariance to particular variabilities such as SNR, behavior of the signal, location within the frames and within the backgrounds. And basically, here is an example of how we have backgrounds of basically 120 seconds where we insert signals. We insert about 500 signals per background, and we take a 0.75 second length of this long background, And this is the one for which we compute the spectrogram of 25 million pixels. And here we randomly choose these 256 by 256 frames, which are used to train the posterior estimation network. So this training frame for a particular signal. So how we do annotations for these signals? Basically, we use an energy detector that was provided to the program. And this energy detector works because it's actually annotating the boundaries of the signals and the locations of energy of signals at two levels. Basically, bounding boxes that give like a human or analyst level of where the signal is, and detailed energy annotations. But these are obtained, for the baseband signal before it's inserted in the background. So it's, the signal is clean and it's in the baseband, so it's relatively easy to do these annotations based on energy because there is an ad hoc processing for every type of signal. But then the annotations, when the signal is inserted in any position, the annotations are also translated in frequency and time to match where the signal has been inserted. Basically, the training data set for this type of networks use about 500 SOIs per every 120-second background. And we have multiple recordings on real operational locations that we use to insert the signals of interest and train models that way. The SNR ranges for the insertions were between 5 and 25 dB, and we generated about 50 environments that accounted to about 16 terabytes of data. And from those, we extracted about 1.25 million features all SOIs. And the evaluation data sets were similar. We used 120 seconds backgrounds, inserting about 500 SNRs. And we had 4 environments with increasing difficulty. And basically, the SNR for the test was 10 dB. The frame posterior estimation network was a ResNet that here is a reference of the network we use, to which we added additional layers in the input, convolutional layers, and additional layers in the output to basically classify 11 type of signals of interest, plus one. Basically, the ResNet has 4 stages of residual blocks, and basically at the end of every stage, basically the feature map is half spatially, but double on the number of features extracted. So we end up with about 512 plus 512 features, which are actually processed by a gap layer, obtaining average and max pooling over the spatial dimensions. And this goes to 2 dense layers that produces the posterior probabilities for 11 signals of interest. Basically, this net was trained from scratch on the data that we generated on the 1.25 million frames. We also did online augmentation using random crops and frequency rolls to improve generalization that amounted to 2 times augmentation. Basically, this is kind of a classification on the cross-validation set, and we see 0.26% accuracy classification. But this is not really what matters. What matters is the detection across multiple frames, which we will see later. So for the bounding box estimation, we use some network called MaskRCNN. This network produces a hypothesis of a box around the activity for every SOI. And basically, to use this network, we actually wanted to train it from scratch. This is actually trained normally using millions of frames, millions of images. So what we did is to basically apply transfer learning. We converted our posteriogram, where we have the posterior probabilities for the 11 classes, into an image, basically marginalizing this posteriogram over 3 classes, generating a 3-channel image. And the classes were background, wideband signals, and narrowband signals. And so in this way, we created like an image that can be input to this bounding box estimation mask RCNN network. So it becomes similar to an image. So we don't train, this is kind of a summary. We can see the reference of how this mask RCNN bounding box estimation works. It has a convolutional backbone that is already pre-trained, a region proposal network, and a classification and regression heads that locate the boxes and give also a score for the match of the signal that is inside the box. So we didn't train the network, we only retrained the final layers using basically the images generated from our spectra, where we converted the posterior probabilities from the first network into images of 127 by 64 pixels obtained from every 0.75 seconds corresponding to every background. This generated basically about 8,000 RGB images that correspond to actually a huge amount of training data because every image is actually based on 2 gigabytes of IQ data. So then, after we have the hypothesis for every signal computed by the mask RCNN, we compute a score using this segmental scorer. We want to basically compute a score based on the whole length of the signal, which is a segment in the spectrotemporal region, for what we basically add the log probabilities of all the frames within the bounding box, plus a score produced by the mask RCNN network that somehow is giving an idea of how good the activity in the spectrotemporal pattern of that image matches the signals that have been trained. With this segmental score, we produce a detection when the score is above a given threshold. And we apply this approach to the detection of the signals as we saw before. Here we have the ROC curves on a development set where we choose the values of the thresholds to detect the signals. And on the evaluation set, this is just examples of across several signals and several environments. We see the detections, for instance, for drones was very good with about 100% probability of detection at a false alarm of about 40%. For other signals like Bluetooth, also we got very good detection performance. And here we see the ROC curves in the order of 88% at a false alarm of about 21%. Same for Wi-Fi in a different environment, about 92% and 30%. And so for the wideband signals that evolve in the spectral temporal pattern, which is extensive, this actually worked pretty well. For signals that are more narrowband, the performance wasn't so good, but still acceptable, like for LTE, 70%, ADSB, about 95%, but higher false alarms. For DECT, about 76%. And for ATSC was basically about marginal, 50% false alarm, 50% detection. So we can see in the paper all the results. But basically overall, we found that we obtained very good detections of the wideband signals, Bluetooth, drones, and Wi-Fi. For the other signals, detection was reasonably acceptable, like for DECT and LTE. But for the very narrowband signals like BULOS, the performance was relatively poor. So that requires more work. So in conclusion, basically we presented a system for wideband spectral monitoring. It uses a hierarchical architecture to deal with the extreme large range of signal bandwidths and durations that we found in this type of problem. We generated large amounts of training data in a multi-condition fashion for invariance to SNR, signal variability, signal location, and background environment, and used state-of-the-art deep learning approaches inspired on image processing and also on segmental scoring inspired on speech processing. The system was effective at detecting these elaborate wideband signals with high accuracy, capturing the large-scale spectrotemporal patterns that occur along several frames, such as drones, Bluetooth, and Wi-Fi signals. So there is more work to do. This clearly only worked for signals with positive SNRs, and we didn't use phase information in the representation, and but this was kind of an initial approach to this difficult problem. That's all.
Thank you very much. So this was a paper by SRI. Sorry, I forgot to mention at the beginning. We do have two questions. Can we access the big RF data set? Was the first question. And the second question says, different from image object detection, the RF signals detection needs to consider the size of packets in the time domain. My question is how to set the window size for RF data set. Did you have answers to those questions?
Yeah, for the first question, the data set was provided to us by DARPA, and I think, I'm not sure if it will be available. It's not something I can say, but maybe. Can you repeat the second question? I wasn't.
It's I did not understand it. Maybe the person who asked questions can elaborate. It says that how to set the window size for RF dataset, and it has to do to packet sizes being the actual features that macro features that distinguish one waveform from another.
Yeah, I can say that basically we use a kind of a compromise resolution. Our window 256 had 256 by 256 components, kind of similar to what a typical image in image processing is. The bandwidth was, like I said, 10 megahertz in the highest resolution and about 12 milliseconds length. But inside any activity that is can be resolved by these 256 by 256 points could basically be differentiated, depending on what are the temporal and spectral patterns within that window. And then larger excursions of activity that would actually occur across multiple frames were captured by this second network that basically model a larger scale of the movement of the signal across the time. Yeah, the mask RCNN.
Okay. So have you I have a question. Have you considered maybe using the object segmentation algorithms such as UNet?
Well, I mean, the segmentation, to apply this, we look for the best segmentation network that was available at the time in the community in image processing, and that was a mask RCNN. I know there are many alternative, segmentation approaches for images, but we use that one. I'm sure others could be also used. I think the main point is that, to deal with this high dimensionality, ultra wideband representation, we really needed to do this in like 2 stages. And so anything that could process a posteriogram as an image could be used to do object detection and then signal detection in that space.
Thank you.
Thank you.
I think we should move to the next and I guess final talk of today's workshop. We have open set recognition through unsupervised and class distance learning. This is work by Expedition Technology and I believe University of Virginia. And the speaker is Andrew Dragunov.
Yeah, hi, can you hear me?
Yes. Go ahead, please.
Okay, and I just started sharing my screen, so hopefully you can see that as well. Can you?
Yes. Yeah.
Perfect.
It's okay.
So today I'll be talking about the work we did under the DARPA RIFML's TA1 program. We did open set recognition in the RF domain using class distances and unsupervised learning. The work was done by myself, Andrew Dragunov, Carter Brown, Enrico Mattei, Cass Dalton, and Jaspreet Ranjit. So just as a little bit of context, here is the outline of what we are going to talk about today. We're going to talk a little bit about how we use neural networks for RF device fingerprinting. Then we'll discuss an introduction and some motivation for what the open set recognition problem is, why we would want to do it. We'll then move on to the data sets and metrics we use to train an open set recognition model, as well as what we use to evaluate our performance. We then will dive into the details of our approach and present some results. So RF device fingerprinting is the task of recognizing a specific emitter based on the imperfections that occur in the digital to analog conversion. These imperfections are unique to every device, so we can learn them through traditional classification approaches. In our case, what we are going to somewhat gloss over for the purposes of this presentation is the exact details for how we do that, but the main idea there is that given an input burst, we can segment it into multiple FFT windows. Once we have those FFT windows, we have a sequence of those that we can represent as in some other latent space. And from there, we can train a classifier to classify which device this came from. So what we're looking for are the subtle details of how the information is shared rather than the information itself. The reason we use multiple FFT windows here is that it allows us to integrate the extracted features to find the fingerprint. And so we get some more processing gain from using multiple bursts in tandem. And so given that we have a classifier that performs RF device fingerprinting, our question then is, how do we expand on that so that it can recognize when there is an RF device communicating that it has never seen before? So traditional classification models can only predict within their known class distribution, but they will predict within their known class distribution even if an input does not come from that input distribution. So if we have 100 known classes and we're presented with class 101, it'll be predicted as one of the 100 classes. And then if we're presented with class 2000 that's totally different from anything we've ever seen, it'll still be predicted as one of the 100 classes. So therefore, operational classification systems have to be able to recognize two separate decision boundaries. The first is still the traditional classification task, but the second then is the open set recognition task of recognizing when something is from the open set, all of these new samples that we didn't train on. And we posit that a good open set recognizer should have three qualities. It should still perform the traditional classification task well. We don't want to sacrifice our classification performance in the RF emitter identification task for the purposes of open set recognition. We want to recognize these out-of-library open set examples consistently, and we want these open samples to still somewhat cluster by device. We don't want to just force all of the open samples to a single point because then we can't differentiate them from one another. In the literature, this is traditionally done one of two ways. There are what we'll refer to as statistical methods. So these model distances within the closed space, within the devices that we know, and they will use this to identify heavy outliers as likely novel samples. So if we have our 100 known devices, then we are going to know generally how close a sample is to some of those known devices. And if we receive a sample whose extracted features are significantly different, then we can statistically assume that with some confidence that that sample is going to be novel, and we will label it as such. So those are the statistical methods. Then the learned space methods are focused more on learning a separable space between the open and closed samples. So actually learning different features for the open samples versus for the closed samples. What we do here is we're going to unite these two approaches by providing our open set recognition model with both the signal's encoded latent representation, so we can learn where in that space the open samples land versus the closed samples. But we will also provide this open set model with the distance of that latent representation to all of our known classes. This will allow us to learn the open and closed decision boundary in terms of both the signal's features and its relative similarity to the classes that we already know. As a quick overview, we're going to get into more detail on this later, but here's a brief overview of our architecture. So given a received signal, we've received it, we've channelized it, all of that. We split it up into the FFT windows. So the encoder receives a sequence of FFT windows. It encodes them through using a set of complex convolutional layers. And we land in our learned latent space here, where we have class centroids for all of our known classes. So those are the X's in the blue clusters. We then, given that learned representation, we'll do closed set classification, which is which class is it? We will do openness metric learning, which is this sample from the closed set or the open set? And we'll have an unsupervised head that will enable better feature representation, which we will get into later. So before we dive into the details of our approach, for a little bit more context, we want to focus on the data sets and metrics that we use to both train this model as well as analyze our results. So we now no longer just require the regular train test split. We are going to add additional data sets towards the goal of learning multiple decision boundaries. Our first data set is the closed set. This is the classes 1 through 100 that I've been talking about. They are accompanied by 2 labels. They have a class label and an openness score of 0. So this is just all of the devices that we know. We then add onto that an auxiliary open set, which serves to represent to the network examples of what an open sample could be. These do not have a class label, and they have an openness score of 1. And the whole purpose there is just to be classes that are different from the closed set. As such, because they're unlabeled, these can be ambient collected signals that we will use as a means of learning better feature representations down the line. And lastly, we're going to have a true open set, which also does not have a class label and has an openness score of 1. And these we are going to use as a way of evaluating our open set recognition performance. So these are classes that we've truly never seen. They weren't even in the auxiliary open set. So how well do we generalize to true novel samples? Given that discussion of the data sets, let's look at a flow example for how we train the network. We start with an input from the closed set. It comes with a class label, C, and an openness score of 0 because it's closed. We encode it through using the encoder, and it lands in this bottom cluster right here. Given that location in the latent space, we can then determine the distance of that sample to all of our known classes. So we have means representing each class that we know, so we can then use those means to say, okay, we've landed here. Here's how far we are from everything that we've seen before. Given both of those pieces of information, the location of the latent space as well as the distance to all of our known classes, we can then predict the class label as well as our openness score. So our class label we hope is predicted C, and our openness we hope is predicted close to 0, meaning it's a closed sample. Then when we receive an input from the auxiliary open set, it comes without any class label and an openness score of 1. What we are going to do is it's going to get encoded the same way. We're going to have a latent representation, that location in the latent space, as well as distance to all of the means for the classes that we know. We are going to, again, pass it through. But this time, our openness gets predicted as 1, we hope, and we ignore the class prediction because we know during training that this is an open, auxiliary open sample. Therefore, we're going to not care about the class prediction because we know that it's not one of the classes that we know. This lets us learn a decision boundary between the open and closed subspaces so that when we receive a truly novel input, we can encode it, it will land somewhere, we have our distances to all the classes that we know, and we hopefully predict it as an open sample, and therefore we know to ignore the class prediction. Lastly, before we get into the details of our approach, we also want to mention some metrics that we use in order to analyze our performance. It's no longer sufficient to simply state classification accuracy because our purpose here is both classifying and recognizing when samples are novel. Therefore, we have the closed classification accuracy, which is the percent of closed samples that we both identify as closed and classify correctly. So what that means is it's a harder task than traditional classification because we might classify something correctly, but misidentify it as an open sample, which means we've accidentally said that it's not one of the things we know, and then we're going to ignore the class label either way. So we have to now take into account both of those predictions for our accuracy metric. Additionally, we have a true positive rate, which is the percent of open samples to which we assign the correct openness, and the false positive rate, which is the percent of closed samples that are identified as open. So our objective here is we have our 100 emitters that we know. We know how to recognize them. We want to consistently classify them well, but also recognize them as closed. And any other emitter that we receive, we want to recognize as open. So we want to have a high closed classification accuracy, a high true positive rate, and a low false positive rate. Now we can get into the meat of our approach. Only took 20 slides. So our first thing that we found when we attempted this was that if we let the encoder simply learn to the open set recognition task, then we significantly overfit to the auxiliary open set. Said otherwise, supervising the encoder on open samples encourages it to think that only those samples are open. What this means is if we have, our classes 1 through 100, and then classes 101 through 110, which represent the auxiliary open set, we're going to train our encoder on those 101 to 110. It will learn that only those 10 classes are open, and it will not generalize to the true nature of the infinite possibilities of what it could mean to be a novel sample. Due to this overfitting, we need to therefore learn a good representation that separates the open and closed samples without overfitting so that we can generalize to the novel examples. There's a field for this called unsupervised and semi-supervised learning, and it's particularly used in the image domain. NLP is where I've read the most papers about it. These techniques are great for us because they leverage ambient data to achieve their tasks, and our auxiliary open data is ambient, unlabeled signals that we can simply use to learn better feature representations. But we have an issue, which is that a lot of these image-based unsupervised learning techniques don't have a direct translation in the RF fingerprinting task. This is because a lot of these unsupervised learning techniques exploit large-scale features in the input. So if we have a picture of a dog, the dog takes up at least a large majority of that picture. However, the RF fingerprint is a subtle detail that we're looking for. So a blind unsupervised learning technique like minimizing mean squared error will ignore that in favor of the payload. To get around this, what we do is we exploit the fact that the same burst must have the same fingerprint. So if we take two samples from one burst and encode both of them, they should be near one another in the latent space. But if we take two samples from different bursts, they should be far away from one another. That way, we don't need labels, but we still enforce the fact that they must have the same fingerprint, even if the payload or the data transmission is different. To walk through this in a little bit more detail, we have input burst 1 in the top left here. We are going to FFT a bunch of the windows that we take from that input burst. We pass them all through the encoder, and they all land hopefully near one another because they all have the same fingerprint. We then take input burst 2, which is from a different device. We receive our new FFT windows, pass them through the encoder, and again, they should hopefully land near one another. What our contrastive loss is going to encourage is high inter-burst distance and low intra-burst distance. So said otherwise, all of the samples from a single burst should cluster, but they should be far from all of the other bursts. And again, this doesn't require labeling any of the data, so we're good to go. To showcase what this provides us, we have a little toy problem that we demonstrate this on. We used a toy data set of 10 closed classes and 5 auxiliary open classes. And we plot the latent space in 2 dimensions. So here we have the open space is shown in red and the closed space is shown in blue. And we see that there's a clear decision boundary between the two, but it's not very consistent between the x-axis versus the y-axis, for example. However, when we add the unsupervised loss and our class distances, we now receive a much more consistent class boundary. And what this leads us to believe is that our generalization to truly novel samples should be better because we're no longer making decisions that are very kind of geared around the specifics of where some samples might have landed in the latent space. So let's look at some of our results. We have the standardized tests that were provided to us by DARPA and Crane. And for all of these experiments, we use the same auxiliary open set. So we had 400 classes in the auxiliary open set. We then ran 3 experiments, one with 100 closed classes, one with 500 closed classes, and one with 1,000 closed classes. So what we see is we have our traditional classification accuracy, right? But our closed classification accuracy, which is a harder task, falls from the traditional classification accuracy, which is what we would expect to see. If it went up, then something's wrong. But what is interesting, we think, is that if the misclassifications and the samples that were incorrectly identified as novel were independent of one another, then our closed classification accuracy would be significantly lower than what it is right now. So what this leads us to believe is, or it must be the case, right, that a lot of the samples that we are misclassifying are the ones that we're misidentifying as open. So that means if we don't know anything about it and we can't classify it, our network is going to accidentally call something open because it couldn't pull out any relevant features about it at all. Additionally, we ran some experiments to investigate the effect of the number of auxiliary open classes on the open set recognition performance. So what we have here is a closed data set with 100 Wi-Fi devices in a multi-burst setting. We have 20, 50, 100, and 200 auxiliary open classes. And what we see is our traditional classification accuracy is about the same, oscillates a little bit, but that's within the variance of the data set. But what is interesting is despite the fact that, as we would expect to see, our true positive rate increases as we provide more examples of open devices, our false positive rate also increases. So what this means is we become better at recognizing open samples when we provide the network with more open samples, but the network also becomes a little bit more trigger happy in calling things open, even if they are closed. So it has a better idea of the open-closed divide. However, that comes at the expense of sometimes having closed sample misidentified as open. Okay, and lastly, some takeaways that we want to kind of mention one more time is that we found that having more auxiliary open, simulated open classes leads to better open set recognition, but also to slightly higher false positive rate. There's a significant overlap between the misclassified samples and the false positives. So if the network can't extract any features about the sample, then it's going to likely call it an open set example because it doesn't know what it is. And lastly, adding the unsupervised loss provides an immediate boost on the open set metrics. So what we see in this plot is we turned on the unsupervised loss at step 25,000, and we immediately received a much better open set accuracy. And that is what I had to discuss with you today. So
okay, we need to wrap up. Okay, thank you so much. We need to finish in 3 minutes. Do we have any questions for Andrew? Anyone? So, Andrew, you said, hello?
Yeah, hi. I'm having a little trouble hearing, but.
Yeah. So just so quickly, one quick question. So you said you use the encoder that's implemented in a complex valued, it's a complex valued implementation. Is it actually a complex valued autoencoder that you used? And then you're talking just in terms of the encoder?
Right, so part, what we used is we had a neural network that we used for the classification problem originally that was a complex valued autoencoder with a Gaussian mixture model in the latent space. But then what we did for this problem is we removed the decoder part. So there's still an encoding element and we are receiving a compressed feature representation, but there's no decoding aspect. So it's not technically an autoencoder, although, right, we are encoding down to a significantly compressed feature space.
But you actually trained the latent space based on the autoencoder structure.
That was the original motivation before we moved on to the open set recognition problem, where now we still have that latent space, but we're not decoding from it out to the signal space.
Okay, thank you. Anyone else? Okay, so I conclude that there are no more questions. This is the end of our session, and I guess the end of our workshop, unless someone, some organizer would like to have a concluding word.
Yes, thank you very much, Silvia, for chairing the session. So hi from my side. I'm Mark, one of the organizers of the workshop. And on behalf of my colleagues, the workshop chairs, I would really like to thank you for participating. I would like to thank the two keynote speakers for very interesting talks. Thank you very much to the speakers. Thank you very much to the participants for being active in the discussions. And of course, also thank you very much to the organizers of the main event for having us here. And for making the best out of the circumstances that we have, so that we really are able to have a perfectly organized virtual conference. So thank you very much for that. It was really great participating. So yeah, time to close the workshop. I'm really looking forward to the workshop next year, hopefully that there will be no virtual conference, so that we will be able to meet in person. I think the recording of the workshop will be available via the YouTube channel. So thank you very much again. Stay safe, stay healthy, and hopefully see you all next year. Bye-bye.